So, good morning, all of you, and a very warm welcome to IIT Bhubaneswar on behalf of our director, Professor Karmalkar, and head of the department, Professor Niharika Mahapatra. We are very glad that so many participants are here. In fact, most of the even Indian faculty members from Indian string community, it's a first visit for most of them to this institute. So I'll not take too much time, just a couple of words before I hand it over to Sachin. So this institute started in 2008, and IIT Kharagpur was given the responsibility to be the mentor for this institute. And now there are around 23 IITs in India, continuing the legacy set by the first 5 IITs. And why are there so many IITs? Because we have to thank the first generation of IITs, around 5 of them, who produced brilliant students and the teachers and the researchers from those institutes. And you don't have to look very far. In this very room, there are several distinguished and accomplished string theorists, and most of them have been trained in IITs. Fortunately, in this institute also, the institute has been very supportive of continuing high energy physics and string theory, and we hope in future we'll hold more schools and conferences here. This is one of the first conferences we are holding in string theory here. So once again, welcome to all of you, and have a nice stay here. Just one announcement, just before the tea break, there will be a group photo session outside. So please don't take tea, just once the photo session is over, you can take the tea. Okay. All right, thank you very much, and Sachin, please take over.
The first of start from here. You will not be disappointed because you have to come here and see. As soon as anything. It's really hard impediments.
Okay, it's really nice to be here. The last ISM was also at an IIT, and because of this introductory talk, I gave maybe one of the early talks, maybe the first talk in the last ISM. It was preceded or postceded by some dean who was going on and on about IIT Bombay. So I came and said, I'm also from an IIT, but from a better IIT. He was so mad afterwards in the tea break. He didn't understand it was a joke anyway. Okay. Anyway, so my talk is titled Semi-Universality of CFT Entropy at Large Spin, and is based on this paper, together with my students Harsh Anand, Vipul Kumar, and our postdoc Jyotirmoy Mukherjee, Shridip Pal, Ashikur Rahman, and also Nathan Benjamin. Okay, Vipul and Jyotirmoy are looking for jobs, and they're fantastic. Okay. As you will see, this work touches on much older, earlier work, and some newer work. We'll come to that. Okay. So let's start. Suppose I handed you a CFT and asked you what you wanted to know about the CFT. Different people will want to know different things, but on almost everyone's wish list, would lie the following want: is give me a list of the spectrum of operators of the CFT and its scaling dimensions and angular momentum. Okay, the spectrum of the CFT is basic data of the CFT. Now, using the state operator map, the spectrum of operators of the CFT is in one-to-one correspondence with the spectrum of states of the CFT when quantized on the sphere. So, through this talk, I'll work with 4-dimensional CFTs, though our paper examines every dimension. Okay, and so in 4-dimensional CFTs, we're interested in CFTs on an S3 and then living in time. So the spectrum of states of the CFT on S3 and living in time is famously in one-to-one correspondence with the spectrum of operators of the CFT. For this reason, you get complete information of the spectrum of operators if you know everything about the partition function of the theory on S3 as a function of temperature and various chemical potentials. So this partition function of the theory on S3 as a function of temperature and the two angular velocities, chemical potentials for angular momentum, will be the subject of this talk. Okay. Now, beta is the inverse temperature and these omega 1 and omega 2 are angular velocities. We sometimes will find it useful through this talk to work with these redefined quantities. Beta and 1 minus omega 1, beta, which I call nu 1, sometimes I call this a reduced angular velocity. Beta and 1 minus omega 2, and the charge E minus J1 minus J2. I will sometimes call E minus J1 minus J2 the twist. Okay, we will use the word the twist for this quantity. Why this quantity is relevant will become clear as we go. Okay. Now, this quantity Z is a function of these three chemical potentials, beta, omega 1, omega 2. And we can study it as function of chemical potentials for all values of chemical potentials, even complex values of chemical potentials. But one question you can ask is it well defined no matter what your chemical potentials are? If you think about it for a minute, you will see immediately that if beta is negative, or the real part of beta is negative, this quantity makes no sense. Okay? This quantity makes no sense because the spectrum of the Hamiltonian is unbounded from above. So if you weight that spectrum with a positive weighting, you get a divergence. Okay? This is of course very familiar. It's the statement that temperature has to be positive. If beta, real part of beta, if beta was a real number, real part of beta was negative, the temperature is negative. Negative temperatures make no sense, of course. Okay? Now, there is a second phenomenon like this, which have been highlighted by recent studies of gray galaxies. And the second phenomenon is that this partition function also diverges if this quantity nu I is less than 0. Or more, maybe more physically, if omega 1 or omega 2 become greater than 1. Okay? And the reason for this divergence, once again, is the same. Okay? There are quantities that carry positive values of the charge that nu couples to, and nu couples to the charge which is like energy minus omega times angular momentum. So omega becomes larger than 1. Something like a derivative, a del z derivative, contributes in a divergent manner to the partition function. And so this partition function makes no sense if omega becomes greater than 1, or equivalently if this nu 1 becomes less than 0. Okay? So there is this range of chemical potentials for which our partition function is well defined. And interestingly enough, it's a bounded range. Please. Yes. It's not good. Okay, so let's take it here. Let's just don't redefine. Just look in terms of omega. Suppose omega is greater than 1. Now this weighting is E minus beta into H minus, let's say, 1.1 into J. Now if you have modes that carry E equals J, then the E gives a suppression, but the J gives an enhancement. Okay? And the modes, such modes, have more enhancement than suppression. Okay? Now, are there modes with E equals J? There are. Derivatives are such modes. Okay? So, this thing here, if omega becomes larger than 1, causes a divergence, for instance from derivatives, also from other things. Is this clear? Okay. So it's the same argument along a different axis. Okay. Excellent. So now as beta and nu I, beta equals 0 and nu I equals 0 found boundaries on the space of allowed potentials, it's clearly of interest to study what happens as you approach these boundaries from allowed values. Okay? So let's first look at the simpler and older approach, namely approaching beta equals 0 from allowed values, from positive values. That's the same thing as looking at the high temperature. Okay? So what can we say about conformal field theories and the high temperature limit? So suppose I take beta goes to 0 at fixed values of omega I. Now, What is special about conformal field theories at high temperature? Physically, what's special about conformal field theories, any reasonable theory at high temperature, is that at high temperature the theory is described by fluid dynamics. Okay, so if we're interested in this partition function with these omegas, what this partition function is going to be dominated by is by some solution of hydrodynamics. If you think it through carefully, you will, okay, firstly, now what kind of solution of hydrodynamics are we interested in? It's going to be some equilibrium solution of hydrodynamics, right? Because we're looking for the dual of equilibrium. Now, in equilibrium, entropy production stops. But if you look at the formula for entropy production in hydrodynamics, there is a term which is viscosity times sigma mu nu square. Sigma mu nu square is a positive square. Only way that can be zero is sigma mu nu is zero. Now, you can look at the conditions. So this is a strong constraint on velocity, sigma mu nu equals 0. You can look at that constraint and prove the following theorem. The theorem says that the only velocity field take an arbitrary manifold, the only velocity field on that manifold that has sigma mu nu equals 0 is a velocity that is proportional to a conformal killing vector of that manifold. Where on the manifold S3 times S1, S3 times time, the conformal killing vectors of the space are just the conformal algebra. So the velocity field has to be proportional to one of the killing vectors of the conformal algebra, and then normalize so that it's a velocity field. And by SO4, 2 rotations, we can put all such velocity fields in the following form: del t plus omega 1 del phi 1 plus omega 2 del phi 2. Okay, this vector has to be everywhere time-like. That requires that omega I is less than 0. Okay, so all equilibrium solutions of hydrodynamics, totally trivial to classify. Up to rotations, it's these. And by doing some work, you can convince yourself that these solutions are in one-to-one correspondence with the chemical potentials of equilibrium. And in fact, I've chosen these numbers so that they reflect the chemical potentials of equilibrium. So omega 1 in equilibrium to some chemical potential becomes physically the angular velocity of the fluid as it swirls around. Okay, now any such fluid flow is characterized by its gamma factor. You know, velocity has a special relativistic gamma factor, time dilation factor. And this gamma factor will play a key role in my talk. Okay, and just this was a reminder that we're studying a fluid on time and a free sphere. Okay. Now, so far we've done microphone. We've characterized the velocity field. We're left to, hydrodynamics is specified once you specify. Go on. What does laminar mean? It's not turbulent, if that's what you're saying. Not at all. It's doing nothing. It's just going. Shh. Yeah. Okay. Okay. Excellent. We characterized the velocity. Now, what about the temperature? To get the temperature field, you put this velocity back into the equations of hydrodynamics. You get to look at one of the hydrodynamical equations. They all give the same thing, and you get the temperature is proportional to gamma of it. Okay. Completely characterizes the fluid dynamic solution. Because the solution you can find is energy, you can find its angular momentum, you can find its entropy, you can find anything you want. And so you've got everything about the theory. And from the solution you deduce that log z of this, log z as a function of beta omega 1 omega 2 takes the following form. Okay, there's some undetermined constant, dimensionless constant you cannot determine on general grounds. And then the rest of the dependence on t and omega is completely determined. Okay. This is a sort of higher dimensional version of the Carney formula. The partition function in any conformal field theory is completely universal. Okay, this formula was first derived on these universal grounds in 2007 by our group in TIFR and was recently reviewed by the people at Caltech. Okay, now one quick small aside before we get to the real content of this talk. Okay. The aside is that this answer already contains something a little non-intuitive if you have a certain bent of mind. And the non-intuitivity comes from from the study of unitarity. You know, in conformal field theories obey a unitarity bound. And if you work out the structure of the unitarity bound in D equals 4, you find the following thing. You find E is equal to, you find E is greater than or equal to J1, maximum of J1 plus maximum of J1 and J2 plus 2 if J1 is not equal to J2, greater than or equal to J1 plus 1 if J1 is equal to J2, and is greater than 0, and 0 if J1 equals J2 is equal to 0. Now, this unitarity bound tells us that E minus omega into J1 plus J2 is bounded for below this unitarity bound, let me say it again. This formula here makes sense for all omega up to omega equals 1. So this tells us that our partition function is well defined for all omega up to omega equals 1. Okay? Now that tells us, because the Boltzmann factor, the partition function is E minus omega 1 J1 plus omega 2 J2. Let's set both omegas equals for simplicity. E minus omega into J1 plus J2. The Boltzmann factor is that quantity has to be bounded from below. That quantity has to be bounded from below for all values of omega up to 1. Otherwise, this partition function wouldn't have made sense. Now, does this result follow from unitarity? If you stare at this result, you see that it doesn't. Unitarity at large values of J's, large values of J assures us that this thing is bounded from below for omega up to half. But between half and 1, unitarity does not guarantee the boundedness from below of this quantity. Okay, that comes because it's just one factor of J. Okay, so already the fact that this partition function makes sense all the way up to omega equals 1 is telling us something about the spectrum that is non-intuitive from the unitarity bound. Okay, interestingly though, Cordova and collaborators had argued that, there's some fine print, but argued that E must actually be greater than or equal to J1 plus J2 in any conformal field theory using Anek-based arguments. Arguments I won't review. The point of that paper was that there are bounds that go beyond the unitarity bound, and precisely the bound that Cordova and friends argued for is, necessary and more or less equivalent to the fact that fluid dynamics makes sense all the way up to the point where the fluid moves at the speed of light. So I think that's quite cool. Just the fact that you can spin a fluid up to the speed of light gives you more information than the unitarity bound. This argument just tells you about boundedness from below. Right. So it tells you that there shouldn't be arbitrarily unbounded states. Okay, Cordova's is stronger. Gives you a number. Yeah, please. That's right. So fluid dynamics just says I can swirl a fluid up to the speed of light. That would have made no sense unless E minus omega J1 plus J2 was unbounded from below all the way up to omega equals 1. So just this simple criterion gives us a unitarity type bound, and in fact one that's more powerful than unitarity, but roughly equivalent to the Anek bound. I thought that was cool. Anyway, let's move on. That's not the main point.
This is at high energy or this is absolute bound?
This is an absolute bound.
I see.
The Anek bound is an absolute.
Okay.
Okay, of course it makes some assumptions in the proof. But yeah, it's a very precise bound. It has numbers. Yeah, go on.
The bound in non-unitary theories for the real part of the energy?
Okay, as this argument doesn't work at all if non-unitary. This will work provided the average null energy condition is true. Okay, so now that might be true without unitarity. That's slightly separate criteria.
But the arguments you gave earlier about
my arguments are pretty insensitive. They will just work. As long as fluid dynamics works. Yeah, go on.
Shiraz, can you give me some intuition about the choice of the velocity profile in equilibrium that you made? Like usually I would align my velocity profile along Del-T, but you chose to include the angular moment as well. So.
Excellent. First, I didn't make a choice. I just found the most general velocity profile that had sigma mu nu equals 0. This was the most general choice. Now, had you just had Del-T, then it would have been a fluid at rest, wouldn't carry angular momentum, wouldn't have enough parameters to describe the partition function that we're interested in. can't be the most general equilibrium solution because we've got a conserved quantity, namely angular momentum. So I take a fluid, I give it some angular momentum, let it settle down. Has to settle down into a configuration that carries angular momentum. So there have to be more. These are the ones that are more. Clear? Excellent. Let's keep going. Okay. Now, that was a nice, simple physical argument for a pretty, in my opinion, deep result. A very old result, I emphasize. 20 years old, though Caltech people don't seem to have got the memo. Okay. Okay. Anyway, but now that we've got we've got this old result, let's find a better way. Another way, and a way that will prove more useful for me in what I really want to do, to derive the same thing. This is a little more involved, a little more convoluted, but bear with me. Okay, so this way was a method that was developed again long ago and reviewed by Caltech. Was developed by TIFR, by Amos and friends. Okay, so many people in the audience, Sachin, Jyotirmoy, I'm missing people who are involved in developing this. Okay, consider conformal field theory on any Lorentzian spacetime, okay, which has a time-like killing vector. Every such spacetime can be put in the following form. Note that it's got, if this was plus, this would be sort of like a Kaluza-Klein form, with where AI is a Kaluza-Klein gauge field. Okay, now because we've got a time-like killing vector on this manifold, we have a conserved charge, the thing that generates translations in this time-like direction. Because we have a conserved charge, we can ask, take a quantum field theory, put it on this manifold, what is trace e to the power minus beta h of this quantum field theory? It's a well-defined question. Now, this, of course, is evaluated by doing the path integral of the quantum field theory after Euclidean rotation. So you compactify time, periodicity beta, move to Euclidean space. So we work on this space. Now, the key point of this method of equilibrium functions, or as is now sometimes called thermal effective field theory, is the following. If I take a field theory and I put it on at finite temperature, the effect of lower dimensional field theory is almost always massive. Okay, this is familiar from familiar examples that can be argued on general genericity grounds. Correlation functions at equal spacetime, spatial locations at finite temperature die off exponentially. Because this is massive and very similar in spirit to the talk we heard yesterday, because this is massive, the answer to this partition function is a local function of geometrical data of the compactification of our field theory. What's the geometrical data? Well, the geometrical data is the geometry of the base manifold, the Kaluza-Klein gauge field, and how the spatial circle, compactification size of the spatial circle is varying in time. All clear? Since it's a local functional, it can be expanded in power series of derivatives. So there's a zero derivative term, just a function of this circle size. Then there are two derivative terms, and so on. By dimensional analysis, the zero derivative term comes with a t cube, the two derivative term comes with a t, the four derivative terms will come with a 1 over t, and so on. So this expansion is an expansion in derivatives, but it's also an expansion in 1 over the temperature. Better and better at high temperatures. Okay, so this is some formal gibblety-gook. Now, let's take this manifold and specialize this manifold to the manifold of interest to us, S3 times S1. Okay, this is our manifold, S3 times S1. Now, our general procedure required our identification to be in the tau direction. We're on S3 times S1, but our identification is not quite in the tau direction because we've got a twisted compactification because of the chemical potential. Just 1 second, finish saying. Okay, but if you make this coordinate change, okay, now you make the identification just tau is equal to tau with no other shifts in phi. The price for that is that the metric becomes more complicated, but so be it. So this simple metric, these new coordinates, is this metric with tau goes to tau plus beta. And now we can apply the formalism of this setup to say that the partition function on this manifold must take the form I explained in this derivative expansion. If we're at high temperatures, and that's the point, We only care about the leading term in this partition function. Okay, so we can just evaluate it. Okay, I've just given some of the algebra here, e to the power minus sigma is gamma, blah, blah, blah. We can evaluate it, and it turns out that log z is proportional to gamma to the 4, where gamma is the same special relativistic factor we talked about before. Okay, and when you do this integral, you get 1 minus omega 1 squared and 1 minus omega 2 squared. This term had a t cube, so it's t cubed. That times a dimensionless constant. Same result as we got from hydrodynamics, of course. Not a coincidence, we developed this formalism long ago to constrain hydrodynamics. Okay, question. Yes? Go on.
So here when you say that that the temperature comes in when we are having derivative expanded quantities, right?
Yes.
So is it because it's coming like to balance the dimensions?
Yes, just dimensional.
Just that.
Just dimensional.
Okay.
Okay. Yes, go on.
Do you see the effects of while anomaly with derivative ordering?
Yeah, it depends on dimension. I think 4 dimension, I think it comes at 4 derivative. I can't remember. But this has been worked out. Loga is one of the people who worked this. Those parts will be non-local and will not matter. They don't contribute to leading order in the limit of interest. Okay, so in neither of the limits of interest do they matter. Yeah, all these things you can work out. You can also work out things with other anomalies. You know, when you add charge. This has been worked out in great detail. Doesn't affect the story. Okay, but thank you for the question.
Shira?
Yeah.
Can I ask this?
Yes.
So you are going to put this theory on S3 cross R, right?
Yes, yes.
So which has a non-zero curvature. So,
Yes.
So then how?
These are non-zero and so on. But you see, we were interested in leading order and temperature.
Right.
So this term dominates so far.
So but not strictly in a derivative expansion.
I agree. There are some leading terms. But we were interested in this question of finding the leading order behavior in the high temperature limit. This result is only true at leading order and high temperature.
Okay.
So for that, the first term dominates. But hang on for 5 minutes. We're soon going to look at the subsequent terms. Okay. Thank you. Okay. All good. So there's a more complicated, more formal way of getting the same answer. As I said, not a coincidence. Excellent. That was review. Review of material that was old. Okay. Now we come to the new stuff. We're still focusing on S3 times the S3 times S1 partition function log z. But now we look at the other limit. You remember we had 2 bounds. One place where it diverged was beta negative. Second place where it diverged was nu negative. So instead of taking beta to 0 from above, let's take nu to 0 from above. What can we say in general about partition functions of conformal field theories in this limit? That's the question. Okay. Now, as I said, this gamma square is going to play a key role in this talk. As preparation for this, for the analysis, let's focus on a particular limit. Let's take the limit nu1 goes to 0, nu2 goes to 0, nu1 by nu2 held fixed. They go to 0 in the same way, and beta held fixed. Importantly, in what I'm saying now, beta is not small. We're not in a high temperature limit. There is no obvious reason for fluid dynamics to apply. Okay. Now in this limit, what happens to gamma? Well, gamma was wherever it was. It was this thing here. Sorry, somebody. Do I do something? Slideshow, file, view, full screen mode. That should do it. Great, thank you. Excellent. Okay. So gamma was here. It was this quantity. Now look, if omega 1 and omega 2 are both set to 1, then this one becomes 1 minus sine square theta minus cos square theta becomes 0. So gamma blows up in the limit omega 1 and omega 2 both 1. So when omega 1 and omega 2 are both near to 1, it's large. Okay. So let's look at it here. When you work it out to leading order, gamma squared becomes this large quantity because nu's are small times a smooth function of theta. Smooth because these ratios are held fixed in the limit that that the nu's are going to 0. Okay. So gamma becomes large in this limit. This is what's going to control our expansion. Okay. What we want to do in this now say what we can to leading order in gamma. Note that gamma and all its derivatives are same order of largesse. Okay, now we're going to do this calculation once again in this partition function method. Okay, and to do that we're going to do some algebra. So none of this is very important, but okay, the way we did the calculation was we set up a Wehrbein on this three-dimensional base manifold. The Wehrbein was chosen in a way that suits the problem. One of the vectors of the Wehrbein E2 was in the velocity direction, another in the d theta direction, and the third the unique direction that was orthogonal to both of these. Okay, once we set up this Wehrbein, in this Wehrbein formalism, we just work out all the geometrical invariants of this manifold. The Riemann tensors, the field strength for the Kaluza-Klein gauge field, and spin connections of this manifold. Okay, so every geometrical quantity you want to know about is here. We're working it out, we've worked it out in general in the paper, but we're interested in the answer only at leading order in the large gamma limit. Okay, and you look at something here, you look here. All Riemann tensors here scale maximally like gamma square. Moreover, at leading order, the gamma squares are gamma squares. They're not gamma times gamma prime. There are no derivatives, just gamma square. Similarly, all field strengths here scale maximally like gamma square. Once again, no derivatives. And all spin connections scale maximally like gamma. Once again, at leading order, no derivatives. Okay? What does that tell us? Gone.
Compactification in this limit, is it getting big or small?
It's becoming small.
It's becoming small.
It's
becoming a null circle.
Exactly right, sir. Yeah, exactly. So the way that's happening is that we're compactifying Euclidean in time, but Lorentzian in theta, because we want to work with the real angular velocity, real omega. That's an imaginary distance in the phi directions, and these are almost equal in size. So it's almost null. Okay, so you might think it's secretly high temperature. But you see that though the temperatures are high, curvatures are also blowing up. So leading order will no longer dominate, as you will see. Okay, so but excellent question. Okay, please. Beta's 1, beta's half. Don't think about beta.
Okay, so you are not taking any asymptotic value of beta.
No. Okay. Exactly. Beta is whatever it is, irrelevant. Later, very late in this talk, we may take a low temperature. But okay, excellent. So is this clear? Every geometrical quantity is known. The important point is that they blow up. Okay. Now, by examining the formula in the previous slide, we note the following: no component of Rij, Kl, or Fij scales faster than gamma squared, and every term that scales like gamma squared is gamma squared. It's not gamma times gamma prime. Okay. Similarly with the spin connection. Now, finally, ordinary derivatives acting on a function of gamma don't change the scaling of gamma, because gamma was a smooth function. Okay, so if you take an ordinary derivative and it acts on some function of gamma, which is going to be the structure of what we're finding, it's always dominated by the spin connection action, because the spin connection was gamma, but ordinary derivative didn't increase the scaling. Okay, and so because of that, when you think about this, you conclude the following. Consider Lorentz invariant quantity Q built out of NR Riemann tensors, NF field strengths, and ND covariant derivatives. And these covariant derivatives could act on Riemann, could act on field strengths, could act on sigma, whatever. Okay, such a quantity scales no faster with gamma than gamma to the power 2nr, because each Riemann scale like 2, plus this should have been NF, plus 2NF, because each F scale like 2, plus ND, because each spin connection spin like 1. Clear? Okay. Now, note I've always worked with quantities with lower indices. Okay. So now the total number of lower indices carried by Q is 4NR, because Riemann has 4 indices, plus 2NF, plus ND. Okay. I'm going to build a scalar. So I have to contract these indices with G upper. How many G uppers do I need? Well, number of indices divided by 2. Now, Riemann has while weight 2, G inverse carries wild weight minus 2 and F and D mu nu carry 0 wild weight. And examining this, you see that this quantity Q that is built out of these things carries wild weight minus 2 NR minus 2 NF plus, wild weight, minus 2 NR minus 2 NF plus ND. Okay, just adding up the wild weights of the Riemann, the field strength, and where did I get the ND? ND. This ND is probably shouldn't be. And that carries no wild weight. Sorry. I probably added in these number of indices. Yeah. So I take these indices. I've taken the wild weight of G inverse and added the wild weight of these explicit quantities and summed that up. So that's where the ND came from. Okay, great. Okay, so this G inverse carries wild weight of minus 2, right? So that's where the ND came from. This quantity times minus 2. Okay, so you just work it out. Add the wild weights up, you get this quantity. Thus, square root G3 times Q has wild weight which is 3 minus this quantity, because square root G has wild weight 3. Okay, and so while invariant contribution to thermal effective action proportional to Q must take the form square root G3 times e to the power this number times sigma, because it has to be while invariant. Okay, the scaling with sigma under Weyl transformations cancels the wild weight that we had from the other quantities. Okay, and now this e to the power sigma here was related to gamma. Moreover, maybe I said that here. Moreover, G3, square root of G3 in this funny metric is gamma times square root of the round metric on the sphere, when you work it out. So you put that together, you take the extra factor of gamma from square root G3, that makes 3, 4. You substitute what e to the power minus sigma is in terms of gamma, switches a sign, and you get this quantity. Okay, so sorry for the ugliness of the algebra, but this quantity then scales like square root G3 times gamma to this power times Q. But we just found here that Q scales at most like this quantity. And notice that what appears here is exactly minus of what appears here. And so we prove that no term in this effective action scales faster with gamma than gamma to the 4. Moreover, we can find terms, it's easy to find terms at all orders in this expansion that scale like gamma to the 4. Okay? And so, in this expansion now, unlike the high temperature limit, it's not like only one term in this effective action contributes. All terms contribute equally. But equally. It's not like, the contribution grows as you go to higher orders. Okay? And so, now when we look at the partition function in this limit, you have to take the power of temperature associated with any given term. Different terms in the derivative expansion have different powers of temperature. And so, but all of them contribute gamma to the 4. So you get some number times beta to the minus 3, and some number times beta to the minus 1, some number times beta, blah, 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 times gamma to the 4. The only part of this action that depends on theta is the gamma to the 4. But the important thing is that the only part of the action that depends on omega is also gamma to the 4. So this omega dependence of this action is completely determined. And in fact, it's completely determined by the same integral we encountered in fluid dynamics. And so it's completely determined to take this form. H of t times 1 minus divided by 1 minus omega 1 squared and 1 minus omega 2 squared. Is this clear? So this is our final conclusion, one of the most important conclusions of this talk. The conclusion is that in the limit nu I go to 0, the limit that I was studying, the partition function of every conformal field theory universally develops a single pole separately in omega 1 and omega 2. The residue of the single pole is an unknown, non-universal, cannot be determined on general grounds function of temperature. Okay, excellent. You're sounding like my collaborators, Ashok. We have to assume all that. Okay, or it is Borel. There's some It does not, and there's a Borel sum, whatever. We have to assume what we usually assume. Okay. Good.
Just from Lorentz invariance, would you have expected Z to scale like gamma to the 4 if I just took it on a planar thing and okay, afterwards?
It's exactly correct. The intuition is exactly correct in hydrodynamics. Okay? But the thing here is that it's more complicated because it also played with the curvatures. So in the hydrodynamic limit, it did scale like gamma to the 4 and your intuition exactly gives it right. But now we're going to arbitrarily high order in the curvature expansion. So it's not some flat space Lorentz intuition that will give it to you. Okay? So it's a little more involved. Please.
Like the hydrodynamic, but then you...
I don't want to apply hydrodynamics. Okay, good. You see, let me reword your question. Your question was, you're trying to take the nu goes to 0 limit, but you analyze the nu goes to 0 limit in a power series expansion in beta. What the hell are you doing? Beta is not small, why are you doing a power series expansion? This is all we could do, because we can use locality when we do that. But you see, since our result was true at every order in beta, it seems reasonable to assume that it's true for the exact function, modulo the kind of concerns Ashok had. Is that your question?
Yeah, could you not have done the series in J? Like that is...
I didn't know how to do it. You will see. As we go along, you will see that there are... Hang on, sir. In the free theory, we will see potential. Yeah, hang on. A better argument. Of course, it suggests there's a better argument. We will see that it also applies in places where my argument does not apply. Hang on for 5 minutes.
Sorry,
Please.
You said there is no dependence on omega at all in the rest of the thing?
None at all, at leading order.
At leading order.
At leading order.
So the gamma to
The gamma to the 4 completely at leading order encapsulates the omega dependence.
Okay.
100%.
Not just the pole part. So
It is just the pole part, because the pole part is at leading order.
right. So, but in some sense, you have set omega equals to 1 in the rest.
In some sense, I've said omega equals 1 and the rest. So, good. So, Rajesh is asking, look, we were near omega equals 1 anyway. So, you've got a particular dependence on omega, okay. But you've got an unknown dependence on t. So, what have you really learned? Roughly. See, once you allow for singular behaviors in omega, you could have had more singular behaviors. Okay? So you could have had a full Lorentz expansion in one over. So in some sense, we've constrained full function worth of behavior. There's a full Taylor series expansion in 1 over 1 minus omega. But to see really what physically we will get, it's clearest in the microcanonical ensemble. What the physical content of this. So hang on for a minute. Okay? But just to ask Rajesh's concern again, see, what we had is an unknown function of 3 variables. We're expressing it in terms of an unknown function. Have we learned anything? The point is, we've expressed it in terms of an unknown function of just 1 variable. The dependence on the other 2 variables is completely fixed. Therefore, it carries information, and this will become clearest in the microcanonical ensemble. Hang on for a minute. Excellent. If you take omega 2 to finite value and omega 2 to 1, then this, like Rajesh suggested, will become h of t comma omega 2, but it will have a pole in 1 minus omega. Okay. So in our paper, we worked out all the various possibilities.
Just one question. So
Yes.
in the thermal effective action, if you didn't demand parity, you could also construct invariance using the Levi-Civita symbol, right? Would that violate this universality?
It does not. You can do the same counting involving Levi-Civitas because it has a square root of g. The same while argument. But excellent question. Yeah. Excellent questions, but you have to remember this at the end. Okay, go on.
Sir, I am the theory, right? So I'll give you some extra time for my questions.
Okay.
Is it that the pole in omega just stops there, or there are more subleading is possible, or this is the only thing?
This is the leading pole.
But
There could be more singular behaviors, like the next singularity is suppressed by 2 subleading powers of omega. That I think will make this a square root in one of these things. So there could be other singularities. Okay? We haven't carefully analyzed, the nature of those other singularities. But this is the leading guy. Exactly. Ayan is wondering about dimensional analysis. What the hell is going on? T is T times R. Radius is 1, therefore T is dimension.
Page from here.
Hang on. We've come to 30% mark in the talk. Hang on. Okay, excellent. Fine. So now that we have this result, we can try to figure out what happens in the microcanonical ensemble. Okay, we do an inverse Laplace transform. Because things are becoming large, it's a Legendre transform. You go through the algebra, you find the following. That thing implies the following. If you take the following limit, J1 goes to infinity, J2 goes to infinity, J1 by J2 held fixed, go to infinity in the same way. And you take tau to infinity, but tau divided by J1, J2 to the 1/3 held fixed. Okay? What does this mean? Suppose you said J1 equals J2. This means tau is scaling like J to the 2/3. So less fast than J. What we are studying is a limit in which the twist is going to infinity, but less fast than the angular momentum. It's a high angular momentum. Okay? So in this limit, the Legendre transform of that previous result tells you that the entropy of the function of tau J1, J2 takes the following form. J1, J2 to the 1/3 times S int, some unknown function, roughly a Legendre transform of that h of t, of tau divided by J1, J2 to the 1/3. This is the claim for the entropy of any conformal field theory in the world, okay, as a function of J1, J2 tau in this limit. Now, what the hell does this mean? If you think about this, you've seen something like this before. Consider a theory on a large space as a function of volume and energy. The entropy takes the form by extensivity. S is volume times function of energy density. That's what's happening here with J1, J2 to the 1/3 playing the role of volume. So the main result from the microcanonical point of view is that there is a new non-obvious extensivity in this theory in the large J limit. There is a new emergent extensivity associated with the large angular momentum, and the thing that plays the role of volume is J1, J2 to the 1/3. We'll come back to this extensivity as we go on. Okay, excellent. Yeah, it's a scale, but the scaling is just the extensivity. It's the extensivity scale.
Rotating so fast that it's all at the edge, and that's why that's the extensivity you are seeing.
I don't know. We will see some of these ADS results in 2 minutes. There is some extensivity, but it's more like the number of states. It's not just at the edge, it goes all the way to the edge. You know, somehow, at least in the gas phase, you can see where it's coming from. It's coming from everywhere, but including near the edge. So maybe yes, I don't know. I don't know the answer to that question. We will see some formulas in a bit. Okay, excellent. Now, though it's on a less firm footing, in our paper we've also presented a conjecture for the form of the stress tensor in this limit. Now, where does this come from? Remember, I presented the main result in this form, but actually we had a more powerful result. The partition function was the integral of a local quantity, and we knew what the local quantity was. So this tells us that we should be getting universal results, not just for global quantities, but also for local quantities. And the most natural local quantity to look at is the stress tensor. And we conjecture that the stress tensor also takes a universal form in this limit, governed by the same h of t function that we had in the partition function. Takes this form. This, for anyone like Sachin who knows about hydrodynamics, knows that this is the hydrodynamical form for a conformal fluid. So basically, hydrodynamics has, gone a little ahead of itself. It's working where it shouldn't be working. And this is our conjecture. Now, the conjecture has some evidence. It works at 0th order in the expansion, but that's just hydrodynamics. It works at second order in the expansion. That's second order corrected hydrodynamics. And it works in both the examples we've studied. It also gives all the right charges if you integrate this. I think it's true, but we haven't really proved it. It would be nice to get a proof at arbitrary orders in this expansion that this is the case. I have an undergraduate working on this at the moment. Okay, fine. So that ends the general part of the talk. This is our main result, our main claim. Now, is it correct? That's what we're going to address through the rest of this talk. So in much of the rest of this talk, we will check our central prediction against two independent computations of L and Z in tractable field theories. The field theories we'll study is first the best field theory in the world, namely N equals 4 Youngman's theory at large N and strong coupling, and second the trivial theory, namely free theory, or roughly N equals 4 at weak coupling. Okay, we will actually first do the strong coupling analysis for reasons that I'll tell you about as we get there. Okay, so let's work with a very strongly interacting theory, namely N equals 4 Youngman's theory. We work in the bulk description using the ADS-CFT. Okay, so at least at high enough temperatures, and this is related to Ashok's question, it's reasonable to expect that this theory is dominated by a Kerr ADS black hole. Now, just an aside, there are other black holes in ADS 5 times S5, including black holes that are localized on the S5. But those black holes are expected to exist and be dominant at low energies in order n square. Roughly speaking, these black holes become too big to fit in the S5 at high energies. Doesn't seem relevant for this problem because we are very high energies. Okay, so these Kerr ADS 5 times S5 black holes, at least in some range of parameters, seem like the dominant solution. So let's study them. Now, about half of this audience probably has looked at these solutions and worked with them. In the classic papers, these solutions are parameterized by 3 parameters, A, B, and M. Very, very, very crudely speaking, angular velocities and mass. Okay, and the event horizon, the outer event horizon, is the largest root of the following equation. Now, everything we want to do will be in terms of the event horizon, and solving a cubic equation is not fun. So instead of parameterizing our black holes by A, B, and M, we'll parameterize our black holes by A, B, and R plus, and let M be determined in terms of R plus by this nice linear equation. Okay, so black holes are come in a three parameter family, parameterized by A, B, and R plus. Okay, now just by looking up the usual references, you can determine all the thermodynamics of these black holes, and you find the following. You find that the angular momentum in the A direction, the B direction, this A and B are 1 and 2, okay, are given by these formulas. Now, what is delta A? The limit of interest, as we will see in a minute, comes in these solutions comes by taking A and B near 1. Oh my God, I did something wrong. Okay, comes by taking A and B near 1. When we take A and B near 1, delta A and delta B are small, and all our thermodynamic quantities will diverge at this limit. And okay, you can check, okay, you can check that in this limit J becomes large, tau becomes large, but in such a way that tau divided by J1, J2 to the 1/3 is held fixed, independent of this delta A and delta B, which tells us we're doing the right thing. Tells us we're doing the right thing by working with this in this limit delta A, delta B becomes small. Now the point of the transparency, yes.
If you want to take R plus instead of M as your parameter,
yes.
So is it fixed from the boundary conditions? M was fixed from the boundary conditions solving the Einstein equations.
No, it was a parameter. M was mass.
Yeah, but I would have, so that's related to the boundary data, right?
Okay.
So is R plus, because R plus is square, the equation.
Yeah, so you could, it is fixed in the same way that M is. Like you could read off M from there and then use that to solve for R plus. You've got a cubic equation, you have to find the largest root.
Related to the asymptotics now, right?
Asymptotics. The ADM energy will give you the mass and then you can use that to solve for R. Just write mass in terms of mass. It's just some parameterization of the same data. The new coordinate on that same data, 3 parameter data. Okay, let's just keep going. Okay, so the thing that I wanted to say on this transparency is the following: when you work out the entropy, of the black hole in this limit, you indeed find that S takes the form J1, J2, or S divided by J1, J2 to the 1/3 is a function only of the scale twist, tau divided by J1, J2 to the 1/3, as we had predicted. So our microcanonical prediction is correct and works out very nicely. Okay, now we can also study the same thing, the same black hole limit in the canonical ensemble. Okay, and when you do that, you see some sort of nice formulae Yeah. Yeah. Dimension meaning? Extensivity. You will see. For n equals 4 Yang-Mills, you will see how it works. That quantity picks up an extra n square. Yeah, you will see.
Live. Live. On আছে? On করো না, সাইড সুইচটা মারি ফেলে অন করো।
Hello, check.
ହଉ ହେଲା ଆଇଲ ତମେ ଟି ବ୍ରେକ୍
ওই জিনিসটা তো করা হবে সে আইলে হয়তো সবার মতো 14 যদি করে কমিটি টোটাল সিস্টেম মুখে এটা খারাপ হচ্ছে না তোমাকে আমরা খারাপ আছে আসলে কটিলা রইতো সেদিকে কেবল লুজ হচ্ছে আসলে তো বন্ধ আছে কানেকশন মজিটা হলো সেই ল্যাপটপ
आईवी पड़े दो
Yes, let's see.
हो गया?
हाँ सर.
हाँ? लाइव चल रहा है.
Abhishek has it, no? Email has come, PPT. That's what Shamit says. I sent to Shamit. He said, yeah, he said he has forwarded to you. I don't want to again forward it to your mailbox.
भाई ଟିକେ ଫ୍ରିଜ୍ କରିବା ଟିକେ ଚେକ୍ କରିବା ତମେ କରିଦିଅ ମାନେ ତାପରେ ପୁଣି ପଡ଼ିଯିବ ନାଇଁ
Should I send it? Yeah.
ପଡ଼ିଗଲା ଆଉ ପୁଣି both the tops now. You know? Both the
Check.
ये मैं दबाया गलती से, ठीक है ना? ठीक है ना? ठीक है, शुरू ही रखते हैं।
so speakers take a note. Okay, Abhijit, please.
Okay, thank you. Let me start by thanking the organizers for putting together a very nice meeting and inviting me to the talk. So today I'll talk about multipartite entanglement and how one could go about measuring it. So this is part of a series of papers that we've been writing on multipartite entanglement. And this work is in particular in collaboration with my student Shreyans Jain, who has graduated and gone to Taiwan to Hsinchu for his postdoc, and Harshal Kulkarni, who was an undergrad when he was at TIFR when we did this work, and now he's a graduate student at Oxford. Okay, so let's start with some motivation of why one would want to study multipartite entanglement. It wouldn't be an overstatement if we say that Rita-Kanagi formula and its quantum generalizations, so-called quantum extremal surface formula, it has really revolutionized our understanding of holography. In particular, of the local aspects of the holographic encoding map, and as a result, it has offered us insights into black hole information puzzle. Now, whatever we learn from the RT formula and these quantum generalizations tells us that the gravitational degrees of freedom in the dual description are encoded in a very interesting way into the boundary degrees of freedom, the CFT degrees of freedom. And this encoding is reminiscent of quantum error correcting codes because it is encoded in a very redundant way. And one would like to understand how precisely this encoding is done. And motivated by this understanding from the RT formula, certain simple models, one can try to model this encoding, and certain simple models such as the so-called happy code have been proposed as toy models for holographic encoding. Now these models do capture very interesting aspects of this encoding, in particular this redundancy of encoding of how local degrees of freedom in the bulk are encoded in the CFT, but these are mainly related to bipartite entanglement. But it is known that such simple toy models fail to capture higher partite entanglement. In fact, they fail spectacularly in capturing higher partite entanglement. To give an example, recently there was a paper by Balasubramaniam and collaborators where they showed that a certain multipartite quantity has to be greater than 0 for holographic states. And my student Sriram recently showed that that quantity is precisely less than 0 for happy code or more general stabilizer codes. So not only is it, it spectacularly fails to capture these higher partite properties of the holographic encoding map. So this makes it clear that if you want to understand more refined local aspects of holographic encoding map, we should study multipartite entanglement in quantum field theories. Holographic.
But now you said that quantity has to be less than 0.
I did not, my student did.
Sorry. And then in that case, what's the conclusion that?
So that tells you that these codes are too toy. They don't capture the holographic nature of the state. Not the correct one if you are interested in more detailed properties. Random tensor network, yeah. No, that I think has the properties, at least the simple properties that one could check. They do mimic holographic states, but they are not quite, a particular encoding map, right? As you are saying, the word suggests it's an ensemble of maps.
Yeah, I see.
So it does capture some
I see.
of the holographic encoding. But certain features are not, because from random tensors, the entanglement spectrum is flat. All the Renyi entropies are the same, but we know from gravity that is certainly not the case. So, yeah, certain aspects are captured, but not all. Okay, so what do we mean by this? When I say that we should try to understand in multipartite entanglement quantum states, what do we mean by multipartite entanglement? Now, in the bipartite case, there is a very distinguished role played by von Neumann entropy. And we always want to understand von Neumann entropy if you have a bipartite state. And the reason is that it's a measure of entanglement. Now, this word measure is used with care in quantum information literature. The sense in which von Neumann entropy is a measure is because if you have a state with von Neumann entropy S, then you can distill from it using local operations S number of bell pairs, which then can be used if you want to teleport certain quantum state that you might have. So they can be used as a resource for quantum teleportation. So in that sense, this S is telling you what is that resource in an entangled state. Okay. Now, unfortunately, for higher partite state, there is no such distinguished measure of multipartite entanglement. This resource theory is difficult to develop. So, and we know that in the holographic literature that many multipartite quantities have been studied, such as entanglement, negativity, reflected entropy, and so on. And they have indeed yielded fruitful results. But you could ask, a priori, what is the reason that I should go about studying these quantities? What properties do they have from a quantum information theory point of view that makes them special? So that is a priori not clear, especially given that when you look at multipartite states, there is really a wide zoo of local unitary invariants that you can a priori study. So in this talk, what I will do is I'll take a step back and try to understand what local unitary invariants for multipartite state have some nice meaning from quantum information theory point of view. In the absence, excuse me, yeah.
Von Neumann entropy that you can distill some S bell pairs. I guess for a tripartite there are these G and Z states, right? So can one say that if I ask for a quantity such that you can distill S such these things, is there a unique one? Is there no unique one, or are you saying no one has found one which can do that? Or
No,
I
mean,
wanted to know the
you can,
status.
you can certainly ask, if you have a tripartite state, you can ask how many GHZ states can you distill from it? Or in the four-partite state, similar questions of this type. But it so happens in many cases that the answer might be 0, because these states may not be in what is called the same SLOCC orbit as these states, as these GHZ states and so on. So in that case, you will get 0, but that does not mean that there is no entanglement, because you may be able to distill some quantities that are close to it, but not, some states that are close to that GHZ state, but not exactly the GHZ state. So in that sense, this kind of a question, it's difficult to make sense of its answer. So that's why we often use an axiomatic approach to quantify entanglement, as I will say soon. So these quantities that are defined using this axiomatic approach, these are called entanglement monotones. So what are they? Very easy to understand. So let's say I have some state, Q-partite state. By the way, it turned out that when I was exporting from a Keynote to PDF, all these this pipe has gone. So all the states you will see, you will not see this pipe in the PDF. Okay, so let's say you have some state psi, which is a Q-partite state, meaning it lives in a vector space. So what I'll mostly concern myself with finite dimensional vector spaces, but this should go in general, and you can apply these things for quantum field theories also. So this lives in some vector space or Hilbert space that's a factor of Q Hilbert spaces, and each of these Hilbert spaces are thought of as a party, as a separate party. So we would like to define a function for these Q-partite states which are valued in positive real numbers that characterizes this multipartite entanglement. And we want this function to obey the following properties. First, it should be invariant under local unit transformations. Now, this is an obvious requirement that you might have from any sort of quantity that claims to characterize multipartite entanglement, because this simply leads to a change of basis for individual party, and under the change of basis, this quantity better not change. And moreover, you also require that if psi is completely factorized, meaning if psi is psi1 tensor psi2 ... psi q, each of these parties, then you want this function to be 0. Okay, so that you know that what it is characterizing is really entanglement. Now note that you can impose a slightly stronger condition here, that this is the 0 if psi is factorized, not completely factorized, but psi is factorized in any way. Okay, but we will not be imposing that condition. That is a significantly harder question. Now, and the third property, which is the most non-trivial property, is that under local operations, a pure state. So let me first say, in order to explain the third property that it should obey, let me first say what I mean by local operations, because this third property will involve these local operations. So if you have a state, a q-partite state q, psi, let's imagine that you are one of these parties in these one of these q parties, and you have some control over your Hilbert space factor in your lab, and then you can what you can do is you can probe your state with various apparatus. So that means you can bring in some auxiliary system, auxiliary Hilbert space, and do a joint unitary transformation and measure a particular measure the auxiliary system in a particular basis. And as a result, what you will get is an ensemble of pure states, right? Because it may be that your apparatus will show its spin up, and then that will be with some probability p1, and spin down with some probability p2, or you could have a basis that's not just two-dimensional but multiple dimension, in which case you will get a ensemble of pure states where you get pure state psi1 with probability p1, psi2 with probability p2, and so on. So this is generally the feature of this generalized measurements, that it takes the pure state and gives you an ensemble of pure state depending on the measurements outcomes. And then we require that under such a local operation, this function that is characterizing entanglement must be monotonically non-increasing on average. So what I mean by that is that if you evaluate nu on this state psi before the measurement, and you evaluate it after on this outcome, but by that I mean you evaluate it on individual size and take a weighted average. That's this part on average, that it should not increase under after this generalized measurement. So this is what is called the monotonicity property. That's what gives it a name, that entanglement monotone. Yeah. This is the general CPT, local CPT. Yeah. So this is just about local operations. But it can be local operation on any party. So one party can do this, then next another party can do this. So this is true for every party. No, this locality is important. If you want to quantify entanglement, then you only require this to be true for local operations. I mean, local operations that are done in a given party. Not a local operation, not an operation that is done by two parties or multiple parties together. Okay. Now, you may say that this somehow looks somewhat esoteric to define such quantities, but you can already see that there is a very interesting consequence of these definitions. Say if you have a function nu which satisfied the previous conditions, and then if you want to transform a multipartite state psi to another multipartite state phi, then you can show that the probability of success has to be bounded by this quantity, nu of psi divided by nu of phi, for every nu that you may have. Okay, and this follows very straightforwardly from the definitions that we had, and this goes as follows. If you want to produce phi from psi, it must be result of one of the measurements. So let's say this psi2 is phi, and this happens with probability p. Then we know that nu of psi must be greater than or equal to this weighted average, and because nu is positive, this must be greater than p times nu of phi. So that gives you this bound. Okay, so you can use these entanglement monotones to bound the probability of transformation through local operations. Okay, so what we will do is in this talk is to construct such entanglement monotones for multipartite systems. For bipartite systems, the theory of these entanglement monotones is quite well understood. In fact, a complete class of entanglement monotones is known, so that you can just minimize over those and obtain a probability bound which is actually optimal. So in that sense, this theory of monotones for bipartite case is quite well understood. but that is not the case for 3 or higher number parties. So we will try to construct quantities that are easily computable and have these properties. Yeah, same dimension as psi, just different outcomes. Exactly. They live in the same Hilbert space as psi.
What is the explicit form of nu?
So for now, I'm just defining it through these axiomatic conditions, and we will construct such functions.
If
in this talk.
okay, if nu is acting on psi and it is not equal to 0, then state is mixed, right?
No, so all this discussion is going to be about pure states. I'm not going to talk about mixed states.
Okay, thank you.
Yeah, when it is not 0, you would say that the state is entangled, not mixed. No. There are many news, and one would like to find these news so that you have various measures of entanglement. So in fact, that kind of tells you that there are multiple types of entanglements in higher parted systems, because there are many measures of it. So it must, one way of interpreting it is that different types of multipartite entanglements. No, for two parties, there are, so it's Renyi entropies. Well, not quite Renyi entropies. We will see what they are. Entanglement entropy is one of them. And also, you can define quantities using the eigenvalues of the reduced density matrix. So you can define 1 minus lambda max, where lambda max is the max eigenvalue, and that turns out to be an entanglement monotone. 1 minus lambda max minus lambda next max, and so on. So all these things are entanglement monotones, and what was shown is that, in fact, if you take this finite set of entanglement monotones, one of them saturates this bound. Vidal actually constructed a protocol that saturates one of these bounds that are given by these finitely many entanglement in the bipartite case. But in the multipartite case, there's some examples of these functions that are known, but they are very difficult to compute because they involve minimization over large dimensional spaces. So what we are after is to remedy that and try to construct something simple. And we will also have in mind that they should help us compute, they should also be computable in holographic theories, where we can try to learn something from these monotonicity.
I have a question here.
Yeah.
So this partition into various subsystems is up to us, right?
Yes.
So now the question is, suppose you divide in, let's say, 3 parts, I divide in 5, and someone in 2.
Yeah.
So is there a notion of some invariance across these divisions? What I mean to say is, could it be that these higher divisions in some form be ultimately reduced to like the smallest unit, which will be here is like 2? So so could multipartite, this entanglement, be thought of as pairwise?
No. That is the whole point. I mean, there are types of entanglement we cannot think of.
But then how do we reconcile it with this fact that this division is user dependent? Like one could just choose to divide in 2 parts.
And you could ask questions along these lines. But that doesn't necessarily lead us to that particular issue that you're pointing out. And you can talk more about that. That's a different direction that one can pursue. It is related to the first comment that I made, that the second condition one could also impose as 0, not just that when the state is completely factorized, but just when the state is factorized. So that in some sense would capture what one would call genuine entanglement, multipartite entanglement. But I'll be happy to talk to you.
Thanks.
Okay, so now a different criteria could have been used in looking for measures that are convenient for our purpose in understanding entanglement properties of quantum states, or in particular holographic states. And that different criteria one would look for is as follows. So the Ryu-Takanagi formula doesn't just tell us what is the entanglement between various spatial regions, quantum field theory. but rather it ties it to a geometric quantity in the bulk. And this relation between entanglement geometry is what makes it possible to understand local aspects of the entanglement map. So one could look for multipartite quantities that are geometric in the bulk. Okay, so this could be different criteria that one would use to look for nice multipartite measures. So this condition of getting quantities that are geometric, that are interpreted geometrically in the bulk, this translates the question of so-called bulk replica symmetry. So we have investigated this question quite in detail recently in this paper with Vineet and Jonathan. Vineet is in the audience, and I will not talk about that, but rather restrict myself to quantum information theoretic approach and construct these monotones that I talked about. And interestingly, it turns out that the answer to both of these questions is the same. So we classify using this condition, classify using this monotonicity condition, and the class of quantities that we end up is precisely the same. So this is at this stage the curiosity, but it would be nice to understand the reason for this. Okay. So for monotonicity, the most non-trivial condition to solve is this monotonicity condition. Now this is a bit difficult to deal with, but there is one gets a handle on this using this theorem by Vidal, who proved this for the bipartite case. It turns out to be true for multipartite case also. Is that if you take a q-partite state psi, trace out party A to construct the density matrix rho A bar on the rest of the parties, and then if you have a local unitary invariant function f of psi, you can equivalently think of it as a function on the reduced density matrix f of rho A bar, right? And then the theorem says that if f of rho A bar is a concave function of rho A bar for all parties A, then f of psi is monotonic under local operations. Okay, so we'll use this theorem to get a handle on this monotonicity. So what we will look for are the functions which have this property, that they are concave functions of rho A bar for all parties rho A. The way I have written, yeah. This reduces the problem to construction of concave functions of rho A bar. Okay, so let's warm up with a bipartite example. So let's consider the simplest local unitary invariant that one could construct out of a reduced density matrix. So you have a state living in party A and B, and we trace over A, we get rho A bar, which in this case is just rho B. So I'll just write rho B, and the simplest non-trivial local unitary invariant is trace rho B squared, because trace rho B, of course, is 1. Now for any quantum state, trace rho B square is less than or equal to 1, with inequality saturating precisely for factorized states. So if you want to look for a monotone, the candidate function that you should look for is 1 minus trace rho B squared, because then it will have the property that is positive and it's 0 only when this state is factorized. So the first two conditions are kind of satisfied. Now the question is whether this is a concave function of rho B. So that means whether this is a convex function of rho B. And how would you go about saying that? Well, you just take any function of rho B and you differentiate it with respect to rho B, right, by adding a small piece epsilon times delta rho B, and we want this to be density matrix still. So and we know that this is a trace 1 and Hermitian, so you want this to be trace 0 and Hermitian. So delta rho B is a trace 0 matrix and a Hermitian matrix. Okay, and then you expand this and look at this epsilon squared piece, and you want the coefficient of that to be greater than or equal to 0 for any delta rho B. Okay, so now in this simple case, f of rho B is trace rho B, the second derivative is just trace delta rho B squared, and this is indeed non-negative because trace delta rho B squared is delta rho B times delta rho B dagger, because it's Hermitian, and this is then the norm of this matrix norm of delta rho B, which is positive. So so this indeed is a convex function of rho B, and because it is symmetric in A and B, because rho B is the same, trace rho B squared is the same as trace rho A squared. This is also true for party A, which was also another condition that we want, because the convexity condition must hold for all the parties. Then we see that this is indeed an entanglement monotone. Okay. In fact, it turns out that trace rho B squared to the power half is a convex function of rho B, not just power 1. And this is a stronger condition, because the convexity of power 1 follows from the power half, because the monotonic convex function of this quantity.
Sir, you mentioned that entanglement entropy is also, I'm here, sir.
Yeah.
Entanglement entropy is also can be measured like a monotone like this, right? So is that entanglement entropy defined in terms of von Neumann entropy only, or is there any other generalization of that?
Yeah. So entanglement entropy, there is, yeah, I mean, usually von Neumann entropy is what we call the entanglement entropy.
Yeah, but for multipartite system, is there any generalization of that? Means apart from von Neumann entropy, is there any other measures of entropy which can be considered as a measure of entanglement?
So that's what we are talking about. We'll try to construct these entanglement monotones for multipartite states.
Are they in a form of an entropy? Like, is there any entropy kind of measure that we have for multipartite states?
Not entropy type, but whatever comes out of this, I would say, are good measures. Okay. So in order to see that this power half is also convex function of rho b, let's introduce the following graphical notation for rho b and delta rho b. So rho b I will denote like this. So this is a matrix with two indices, right? One fundamental, the other anti-fundamental. So I'm denoting it like that. One index going in, one index coming out. And then delta rho b is also a matrix of the same type, but it's a different matrix. I'll just denote it with this dot here. Okay. Now the state, look at this state. So I'm defining this matrix state, which is just this with these two indices. And now if you take the norm of this state, you get this quantity, which is positive, because it's which is delta rho b squared, which is the second derivative. But on the left hand side, you will see that it's a norm, so it must be positive. Okay. So that is just rewriting of the previous understanding in terms of graphical notation. And now, in order to understand this, consider this state, which is this previous state tensor rho b, the state rho b. Okay, and now we use that this state chi norm is greater than or equal to chi u chi for any unitary. You can think of it as an absolute value here. Okay, so this is just a form of Cauchy-Schwarz inequality, and let us take u to be a permutation operator. So now you have two copies. So when you take the norm, you just glue this with itself. So you get this, and this u, we take it to be the permutation operator, which takes this copy to this and this copy to this. And with that, you get this on the right hand side. So if you read this off, this is just trace delta rho b squared, trace rho b squared, and here trace rho b delta rho b whole squared. Okay, and this condition is nothing but the condition of convexity of trace rho b squared to the power half. Okay, so this tells us from this graphical notation that this is indeed a convex function of rho b square. And you can see from here that this is indeed a stronger condition, because the previous condition just meant that this left hand side is greater than or equal to 0, but here we are saying the greater left hand side is actually greater than or equal to this positive quantity. Okay, now let's go to tripartite monotones. Now, so instead of going about constructing them systematically, which we did in our paper, I will just consider an example and show indeed that it is monotonic, meaning convex. So consider this quantity nu equal to 1 minus z, where z is constructed like so. So here, what does this mean? You have a two-partite density matrix now, because now I'm considering a tripartite state. I have traced out one party. I have constructed rho a bar, which is a row on B and C party, and it has a B index, fundamental, anti-fundamental, and the C index like so. And once I have that, I could contract indices in this pattern and construct this quantity, whatever this quantity is. We don't quite have a matrix notation to talk about it, so I just denote it graphically. And 1 minus that, we will show is indeed a monotone. So now if you take the second derivative, you know, two of these things will be replaced by delta rho b, and on all combinations, so I've put all these terms, the 6 terms that appear here. Okay, and now we want to show that this is positive. So the argument is going to be very similar to before, but here it will involve two states rather than one. So here we will take one state chi1, which is this plus this, okay, and chi2, which is just this. Note that here these lines are green here and these lines are red. So they are cut in some sense in a different way. So now if you do chi1 norm, you get 4 terms, this times this, and this times this, and then cross terms and so on. These are the 4 terms that you would get. And then if you do chi2 norm, you will get these 2 terms, because both of them are the same. This is just twice. And then because these are norms, you add them up, they must be positive. So this equation is exactly telling us all the sum of all these 6 terms is positive, which is exactly what we had here. So we showed the positivity of the second derivative by writing them as sum of norms of various states. Okay. So the idea was to cut these pictures either along the green, either by cutting these green lines or the red lines, so that you get a reflection symmetric picture, and you understand these terms as sum of norms. Now, just as before, you can strengthen this convexity and show that, in fact, z to the 1/4 is convex. Okay, and for that you tensor this with this state, which is just a rho b and a rho b, and then consider this inequality, that 1 minus the permutation operator when sandwiched between chi1 chi1 is positive, because permutation operator will have eigenvalues +1 or -1. So 1 minus that will be a positive, will have, when sandwiched between these two states, will give a positive number. And over here, this is also positive. And exactly as before, this proof will tell you that z to the quarter is convex. Hence, this is an entanglement monotone. Okay. Yeah. No. No, it's important that this is 1/4. In fact, you cannot push it below that. The log you cannot do. Now, similar construction tells us that for 4-partite case, you can consider this type of Z, where now you have a 3-partite density matrix, which looks like so, and you can construct this quantity here, and again take 1/8 power, because there are 8 dots. It turns out that you can take 1 over the number of rows that you use in this computation, and then you can show using similar arguments that this is indeed an entanglement monotone. Okay. Now, these are just examples that we have in our paper. Sorry. But let me just quickly say that what we did is we went about classifying this systematically, and the main condition here is, as I was saying, that the second derivative will replace 2 of these vertices by these delta rho b vertices, and in that case you need a cut which separates the figure into 2 mirror pieces, two mirror pieces given any 2 labeled vertices. So this condition is quite non-trivial. It's called an edge reflecting, condition. It turns out that you can solve for all graphs which satisfy this condition. In fact, all these graphs correspond to regular polytopes. So let me skip this. So regular polytopes are in 1-to-1 correspondence finite Coxeter groups. We checked that this is, so this was a necessary condition, and we checked that this is also sufficient for all but 6 exceptional cases for Coxeter groups. You know, these EF type of cases for Coxeter groups, we have not checked that, but for the infinite series, we made sure that they are indeed they're sufficient. So as I remarked in the beginning, that these are precisely the invariants that have this nice property that the bulk replica symmetry preserved for holographic states. In fact, that's what had inspired this picture. Would have told you more about it, but in the lack of time, let me not do that. No, in general, this is a general proof. Yeah. For any quantum state. So, so in holographic situations, these invariants that I talked about are computed by geometries, conical geometries of this type, where you have singular loci in the middle meeting each other like so, and these numbers, they tell you what the conical angle is across each conical locus. And now that we have established their monotonicity, the natural question is, what does it mean for holographic states? What does this monotonic property mean? So it would be nice to understand that. What does it translate into for conical geometries? So, yeah, any general dimension. Yeah. So I mean, our analysis for this holographic analysis was for 2 dimensions, but I think this should go to any general dimension. That I have not worked out explicitly, but I suspect that this is going to be true for it. So this remark also I have made, that instead of requiring that vanishes in a fully factorized state, one could just require that it vanishes in a state that's factored in anyway, and this would be a measure of then genuine multipartite entanglement. And now another thing that folks from quantum information theory would be interested in is to have these evaluate these monotones on mixed states, and this is somewhat of a difficult task because they are given by this convex group construction. Now these are usually difficult to evaluate, but given that our monotones are kind of easy to compute, perhaps these loop extensions are also tractable. Okay, so let me stop here. Thank you.
Sir, this why is this only for like factorized in any way and not fully factorized? Why are you considering that? There can be like entanglement even if, let's say, there is a factorization between two states. There can be entanglement between these parts itself, right, separately.
Yeah.
So why are you not considering that?
Meaning this condition, the second one?
Yeah.
Yeah, one could consider that, but it's harder. Question is harder. Whether it's not quite clear whether such monotones exist. No such, as far as I know, no such monotones are known in the literature.
So when you take, for example, a tripartite case in the bulk, you have these three regions will be a partition of the full circle. So in this case, the root Takanagi, the entanglement wedges have something to do with, do you know, like some understanding of how the entanglement wedge actually fit into this kind of partitions that, like you take like four-partite, or do you have some understanding of that? Like,
yeah, so the entanglement wedge are kind of sit inside these triangular regions that are carved out by these higher particles. So in this case, for example, you are talking about this.
Exactly.
Yeah.
So for B, the entanglement wedge of B would be inside one of these polygons.
Chambers, yeah. But there's a, it's a bit tricky because these guys are heavy and they're back reacting. So the geometry in which the standard entanglement wedge would live is different one.
Yeah, that's
what.
yeah,
so it's difficult to compare directly with this.
But is there a way to prove it that the entanglement wedge should always be contained inside one of the polygons?
But that's what I'm saying. These are different geometries.
Yes.
One could look at the lengths or areas and say that it's
because
smaller.
you're looking at back reactor geometry,
Yeah,
so
the
different
back-reacted
geometry.
Thank you. Hello. Okay.
Okay, so Sandeep, you can.
Thank you. Okay, so it's really wonderful to be here. Thank you very much to the organizers for the invitation. And if I come to this part of the country, I have to, my mind always goes back, and Professor Gyan Maharana is here, to the wonderful meetings we have had in Puri and Bhubaneswar, going back now 30 years. And I remember the string community then, there were maybe 8, 9 faculty. And to see where we have come, and all the young people and their great talks and the wonderfully diverse, excellent international participants we can invite, I somehow feel really, really happy and proud. And I really want to thank, all the organizers over the years for this wonderful meetings, and especially this year. Okay, so now I'm on a clock, and my talk is Aspects of Holography in De Sitter Space. I'll give you some introduction, tell you in a sort of summary of what we know by and large about the topic, then a little bit about some of the work we have done in terms of understanding the holographic map a little better, tell you about how to map the behavior of black holes in De Sitter space onto the holographic map we consider, and then end with some comments. I'll try to interleave the more review aspects with what we've done so that it kind of tries to make for some kind of coherent story. Okay, now, De Sitter space is interesting just from the point of view of studying quantum gravity because it's a frontier. We understand holography, for example, in ADS space quite well, and in De Sitter space, more or less not at all. So this is fun to do. It's also of great physical interest because As you know, although the data hasn't settled down, there's very good reason to believe, I think, that we might very well be living in a space-time of positive cosmological constant, in which case it will get increasingly like de Sitter space as time goes by. And there's also very good reason to believe that in the early universe there was an epoch of exponential expansion, well described by approximately de Sitter space. So both from the point of view of a theoretical study of quantum gravity and from the very important point of view of trying to connect with nature, de Sitter space is very interesting. Holography, I don't have to tell you, is a very important principle that has emerged in the study of quantum gravity, and so we want to understand a de Sitter space, if we can, from a holographic perspective. And well, this is the Penrose diagram of de Sitter space. This is Scri plus, which is the future space-like boundary. There's Scri minus, and these are two what are called static patches. And the version of holography we will explore is one where the hologram lives on Scri plus. Okay, and there are other versions of holography which have also been discussed, but I won't discuss them today. Now, in anti-de Sitter space, as you all know, this is a picture of anti-de Sitter space. The boundary is time-like, and here it's the boundary of the cylinder, instead the boundary in de Sitter space is space-like, and this is going to be the crucial difference between the two cases. Because it's time-like in the ADS case, and time in the hologram can be identified with time at the boundary of ADS space, this leads to a lot of conceptual clarity. You can identify the Hamiltonian of the bulk with that of the boundary, states map to states, and so on, and that leads to a lot of conceptual clarity when we think about holography in ADS space. And here in de Sitter we have a very different setting. In de Sitter the boundary is Euclidean, and time in the bulk must be the emergent direction. In some mysterious way, time must emerge from the hologram. How this happens is very unclear, but it's one of the fascinating things we hope to learn as we understand holography. Okay, now despite these differences between ADS and DS, there are some sort of similarities. This is the metric of DS space written in what's called Poincare coordinates. This is the metric of ADS also written in Poincare coordinates. And you see, if we take various coordinates to I times themselves and take r ds square to minus r ads square in a formal sense, you can map this metric into the other one. Okay. Well, in holography, we miss one direction in the boundary, and the idea is somehow the information of that direction is in the bulk, from the CFT somehow. Yeah, that's right. Okay, so you can do these transformations and in a formal way convert this metric of ds to ads or vice versa, and that suggests a kind of manipulation you might want to do to try and build a dictionary in the DS case relating a putative hologram to the bulk. But of course then we have to investigate whether that dictionary can be made precise, does it make sense, and so on and so forth. But based on partly this kind of reasoning, but of course a lot of physical insight also, Maldacena already in 2003 proposed the basic elements of the kind of holographic dictionary I will try to explore today. And the idea was that you look at the wave function in the bulk, you look at the wave function in de Sitter space as a functional of the boundary values various fields take, and that wave function would then be equal to a partition function of a boundary theory living on this Euclidean boundary as a functional of various sources. Now here, just for simplicity, I've shown the boundary values of the bulk fields to be the same as the sources. Actually, as you all know from the ADS case, some manipulation has to be done. You have to strip off some factor and so on. How that is to be done is partially clear in the DS case for some fields and not clear in some other cases, and we have tried to clarify that. That's one of the things I'll try to tell you about. But basically the idea is you have some bulk theory, there's a wave function which governs the universe in de Sitter space as a functional of the boundary values field state, and that is given to you by the partition function as a functional of sources in the hologram. Okay, so that's the basic idea. It's very similar from ADS CFT, with one key difference, that in the bulk you don't have a partition function, you have a wave function. Yeah, go ahead please. The right hand side can also be complex. This is not a unitary CFT or anything, you'll see that. Okay, so now, well, you take the wave function, you take its log, and you can expand it out. If you didn't do that, you would have an exponential, which I don't want to keep writing. And this is like a Taylor series expansion, except in the sources. And the coefficient functions, you know, at the moment, I've written them suggestively, but this is just the wave function being expanded. So these are coefficient functions. They, of course, completely then characterize the wave function. For example, if it were a Gaussian theory, there would just be a 2-point function here, or a correlation. There'd just be a quadratic term in phi hat, and then with interactions cubic, and so on and so forth. So these are just coefficients for now, which if you knew completely, then you would know the wave function of the universe. And the idea is that these coefficient functions actually are correlation functions then in the boundary theory. Okay, so that's the basic idea. Now, very little is known about this kind of duality. No explicit known example of such a duality has been found. And so this is, you know, just what we'll try to do is just explore the nature of the correspondence. So can we make such a correspondence at least precise, setting the stage for trying to find duals? Towards the very end, I may not have time. In a very, very simple example of 2 dimensions, I can tell you a little bit about what we are trying to do in terms of finding explicit holograms, but it's a very simplified setting. And the idea is that in the dual theory, then of course you would have some sources and you would obtain these correlations. Okay, now one can argue that all correlators which are finite in the, so as you know, in ADS we often think of first doing calculations with a cutoff and then taking the cutoff to 0. Similarly here, it's useful to think of computing. We finally want the wave function at Scri plus, but more precisely we calculate the wave function on a late time slice shown here at eta c, and then we take the eta c going to a 0 limit to come to Scri plus. And one can argue that all correlators, those coefficients which are finite in the eta going to 0 limit, satisfy the Ward identities of conformal invariance. Okay, and you can do this, and one can argue that. I'll give some references as I go along. Let me just say it here. This result follows very generally just from the fact that the wave function must be a physical wave function. That is, it must satisfy the constraints of time reparameterization and spatial reparameterization. That gives rise to a set of constraints which, for the correlation functions which are finite, become Ward identities of a conformal field theory. Okay, so that's also sort of similar from ADS CFT, but here for the wave function in the de Sitter case. Now, the correspondence and these aspects have been studied to some considerable extent for the Bunch-Davis state, but actually because the consequences that the correlators satisfy these Ward identities just follow from the physical nature of the wave function, the fact that they satisfy these in very time reparameterization, Wheeler-DeWitt constraint and spatial reparameterization constraint, they are true for every physical state in asymptotically ds spacetime. Okay, so there's a map. For every state, you have a putative conformal field theory or a field theory at any rate, a different field theory as you change states, which encodes the information in its correlation functions of the wave function of that state. So that's the idea. And as I said, this follows from the fact that you satisfy these Ward identities follows from conformal invariance, from the time reparameterization and spatial reparameterization, and the fact that you have the conformal Ward identities actually all require that the geometry is, has the isometries of de Sitter space, which are the conformal group for a d-dimensional Euclidean theory. Okay, And this was very beautifully sketched out by Tunir, who's here, right? And his collaborators, including Survat Raju, and studied in more detail for the kind of fields also that I'll talk about in the principal series, in work I did with Indranil Day and Kanu Nanda and Akashdeep Roy, and Akashdeep is at least here in the audience. Okay, so in this way you get an equivalence between the bulk wave function and a CFT on the boundary, different bulk states corresponding to different CFTs. That's the idea. Now the work I'll tell you about is with these authors. Some of them are my students, former students, and Deepak is a beginning grad student who is an undergraduate here in NISER, brilliant guy, so something great being done by my friends in NISER, and one unfinished, so one paper is written and one is in preparation, and some things have not been fully sorted out. Now the slightly new thing which hadn't been spelled out in this kind of map has to do with a class of fields which we'll call underdamped fields, which arise in de Sitter space. They don't have a direct analog in ADS space. And so if you look at the asymptotic behavior as you go close to the boundary, it is of this form, which will again be sort of familiar from ADS space. But this exponent nu here goes like d square over 4 in ds d plus 1, d square over 4 minus m square. So the sign becomes minus. That means if you have a sufficiently massive field, then nu becomes imaginary. And if it's imaginary, both fall-offs are equally fast, And so when you want to choose how to map it, the asymptotic value of the field to a source, you don't know which one to choose. For the case where it's not imaginary, you can proceed more or less analogous to ADS space, choose the less rapid fall off as the source. That's not quite true if you want to get all the word identities to work. It's a little more delicate, but anyway, that's roughly what happens. But here, because both fall offs are at the same rate, you don't know quite what to do. So what do we do? These fields are, in terms of representation theory, they belong in the principal series. Okay, so, yeah. Yeah, so actually it'll turn out they'll be like positive and negative frequency.
Yeah. So
that's right. That's actually the key point. That's right. So the idea is that we work in a coherent basis for the wave function. So, I was showing the wave function implicitly in the field basis and then relating the values of the fields to sources. But instead for these principal series fields, what we argued was that if you look at the wave function in the coherent state basis, so a coherent state, I remind you, is an eigenstate. So if I expand the field, say asymptotically, as Rajesh was mentioning, then what happens is you have two different ways in which you oscillate corresponding to positive and negative frequency modes. And of course, the annihilation operator comes with the positive frequency mode, right? E to the minus I omega t. And the creation with e to the plus. And coherent states are eigenstates of the destruction operator. And if you write the wave function in the coherent state basis, then it naturally chooses one particular fall off over the other. Okay, now you can't write it in the destruction, in the annihilation operator basis, because those states are not, as you know, normalizable. In the harmonic oscillator also, the destruction operator A's eigenstates are normalizable, but not A daggers. So that chooses A over A dagger. And if you write it in the coherent state basis, then you can argue that the wave function has this kind of form you might expect from conformal invariance, where these are are the source terms, and this is really the expectation value of some operator which is falling off, and you choose one of the two fall offs because of the reasons I mentioned. And what you can argue then, and this is what we argued, that in fact all the word identities etc. of conformal invariance and what you want from a correlation functions of a conformal theory are also true for the principal series when you express the wave function in terms of the coherent states, and you regard the coherent states, a value of the coherent state as the source term, as we are doing here. Okay, and so everything goes through once you go to the coherent state basis. And if you have both underdamped and overdamped, you can keep some in the field basis and some in the coherent state basis, and everything works out all well. Okay.
Switch the positive and negative. Would the word idea have been able to see the difference?
I don't think so. I think they would have, but I think the wave function would be kind of badly behaved. Yeah. Now, I think I might have gotten rid of a slide here. Why? Oh, I think it'll come. It'll come. Okay. Now, couple of properties, and we'll go ahead. How much time do I have? This is not ticking. Okay. Excellent. Now, yeah, because we worked in the eigenstates of the destruction operator, and that chooses a particular fall off as opposed to.
I see. Okay.
Yeah. If you'd chosen the other one, then you'd get the other. Okay. Now these correlation functions are strange. They violate a property called reflection positivity. If you have Euclidean theory, you can, there's a property called reflection. You can do reflections about some spatial direction and examine the behavior. And because they violate reflection positivity, you can argue that the Euclidean theory of interest on the boundary cannot be obtained as a continuation starting from a Lorentzian theory, as long as that Lorentzian theory is of a conventional type. Either the Hamiltonian of that Lorentzian theory should not be Hermitian, or the Lorentzian theory in the first place cannot be unitary. Okay, so one or the other or both must break down if you want to try and obtain the Euclidean theory after continuation from Lorentzian space. So that is one thing, a general feature. Both in general, for example, you already saw that the anomalous dimension was complex, but also the coefficients. Even for cases where delta is real, the coefficients are complex in general. Now, why is this happening? The underlying reason for these complex phases is that we are working on the expanding branch of the universe. We are working at Scri plus. Instead, at least if you're at eternal de Sitter space, we don't know if we can have eternal de Sitter space. Liam might have a view. I think it's unlikely in string theory. But anyway, if you did, then you could also look in the very far past and try to construct a hologram at Scri minus, and that reverses all the signs you can see, you can argue, and complex conjugates all the fields and the dimensions and so on. So this breaking of complex conjugation symmetry is related to the breaking of time reversal in de Sitter space. Okay. Second, I focused on the eta independent terms, the cutoff independent terms, but actually there are cutoff dependent terms also, and in fact they are extremely important. You can argue, and in fact I'll come to the references again, that these cutoff dependent terms cannot be removed. In ADS we remove them through a process of holographic renormalization, but here we are trying to describe the physical wave function of the universe, and it is what it is. And the cutoff dependent terms, the dependence that survives on time even at late times, is extremely important. In fact, without keeping these terms, you can argue that the wave function does not satisfy the Wheeler-Dewitt equation. Okay, so they're extremely important. And the more correct correspondence actually is between the wave function and a cutoff CFT. It's not a CFT per se, because these cutoff terms are also present. And the fact that this cannot be removed was emphasized by Maldacena and very beautifully analyzed their general nature and so on in this paper that I referred to. But what you can argue, because the underlying arguments for the word identities involve the invariance of the wave function, what you can argue is that if you also vary the cutoff, okay, as you change, as you do scaling transformations and so on, if you also scale the cutoff appropriately, in other words, if you allow it more generally to fluctuate, then the word identities continue to hold. Okay, so it's like a theory which has a kind of spurion-like field, if you like. Once you endow that field with appropriate transformations, you recover the conformal invariance of the correlators in this cutoff theory. So it's a slightly interesting structure. Yeah. Sorry?
The usual renormalization with local counter terms, right?
Right.
And
you can still, of course, put in local counter terms. All the cutoff dependent terms are accounted for, are of a local type, but the wave function, you know, is a physical object with this cutoff dependence. And if you're trying to recreate the full wave function, then you have to keep the cutoff dependence.
Okay, so if you want to recreate the wave function
Yeah.
at a particular...
But it is true that all the cutoff dependent terms have a local nature and they can be understood in that way. All of that carries forward with coefficients being appropriately complex.
Thanks.
Yeah. Not at the crude level of analysis I'm doing here, but it would show up in that in the first place, I would not be able to go to Scri plus. The idea would be that if you have a long enough lived de Sitter, we construct a boundary before it decays, and then you would have to do it. But how would it show up in the CFT? I don't know. Maybe as some, I don't know, decay amplitude of the wave function. But yeah, it's something worth thinking about. Yeah.
Typically, these de Sitters can be foliated by spheres. So is this so is the boundary? Firstly, I have two questions. Is this boundary introduced by setting a particular value for t? And if that be the case, then is the boundary just a compact sphere-like surface?
So for my purpose, if you wanted to do it in that way, which is in global, as we say, de Sitter space, then you can think of de Sitter 4 as having the topology of R cross S3.
Right.
And you're going very far along the time direction and constructing the boundary.
So finite t value.
Finite but large
t. And so the boundary would be given by a sphere, like a compact space.
The boundary would be a sphere, three sphere. Okay. I'm drawing it like a plane here because I was working on in Poincaré coordinates just to make the analogy with ADS. But if you did it that way, it would be a three sphere. Everything goes through in that case. The late time behavior is very similar.
Thank you.
Okay. So now I really have to proceed. I have 10 minutes, which is a little less. You can define a stress tensor through the Brown-York construction here as well. And there's one non-trivial feature, which is that it is I times the quantity you obtain from the extrinsic curvature. The reason for this I at root is that the wave function is e to the is, okay? And you obtain the stress tensor by varying the boundary metric, and that I survives. And this I is around, and if time remains, we'll come back to it. It's a bit strange, but it's there. And so you have to take it seriously. What does it mean? We don't fully understand, but I'll come back to that. Okay, now the other thing to say is that, as was mentioned, you can choose to add local counterterms, but you know you can't add them in the wave function, but just to define a renormalized version of the stress tensor, you can add them. And I'm doing this because when I map to thermodynamics of black holes, this is the quantity which I will map to, but we have to remember that these counter terms are just added, otherwise there are extra cutoff dependent terms in the stress tensor. Okay, now let's go on to talking about black holes, and for simplicity I'll talk about Schwarzschild black holes in de Sitter, but you can add angular momentum and all the key lessons go through, but I won't do that. So here is the Schwarzschild metric in de Sitter space, and you see that d by dt is a killing vector. These coordinates don't cover all of de Sitter space, just the static patch. You see that t is a time-like coordinate here, but across horizons it will become space-like. And there are in fact two horizons corresponding to roots of the emblackening factor. One is a cosmological horizon and one is a black hole horizon. And in fact, if you draw the full Penrose diagram, it's one of these bewildering ones which go on both sides to infinity. Think of it as Reisner-Nordstrom maybe turned on its head. But of course, that's too much for me. So we are going to make identifications, and we'll identify two edges, and we come to something like this, which is more manageable. And in fact, what will be useful is to further simplify by moving this part of the second square here. So now think of the entire spacetime as extending from O to O, and it consists of two diamonds which are static patches, a forward Milnor patch and a past Milnor patch, and we identify this end with this end. Okay, so that's the space-time, black hole space-time, and we want to understand its description at Scri+. And in particular, what we'd like to do is understand the laws of black hole thermodynamics from the holographic perspective. Okay, what do they mean? Okay. Now, I'll skip some of the details. You can calculate the of particular interest for us will be the two cosmological horizons, because that's what you directly would see sitting at Scri+. Okay, these are the black hole horizons here and here. If you cross them, you go into the black hole singularity. Once you cross the future horizon, then you go all the way up to Scri+. Okay, and you can compute, of course, all quantities, the areas of the horizon, the surface gravity, so on and so forth. I won't go through it, but the important thing is that the geometry only depended on one parameter m. I'm setting the cosmological constant to be equal to 1, and so only depends on m, and the area is a function of the mass, and so on. So everything is determined. And one important difference is, in the de Sitter case, as the mass parameter increases, it's not really a mass, but let's call it a mass parameter, increases the, as the mass increases, the area decreases, or the other way around. The biggest area for the cosmological horizon is that of empty de Sitter space, right? So empty de Sitter has the biggest entropy, and this anti-correlation will be responsible for some peculiar signs which will show up. Okay, now I can define a pressure from this stress tensor by taking the TT component. T was a killing vector, and integrate it on the 2 sphere, and that gives me a notion of a pressure. I drop the I because I don't want to deal with I's when I'm going and trying to connect with thermodynamics. We'll come back to the I. So I define something called a pressure, which is basically the Brown-York construction rendered finite by adding counter terms, and then define a pressure. And this pressure for a black hole is equal to the mass. Okay, so these are correlated. As m increases, the pressure increases. P, the actual stress tensor will be I times m. And so I could have written everything that way, and then in my thermodynamics, wherever I'm getting P, I'll get I times P, and so on. It'll be a little more ugly, but you could state it like that. And that's one of the peculiar things that we'll have to try and see. If it does it make sense or not, then in the end, and I don't know what to say about it, but just to make it at least seem to me more plausible, I drop and I define the quantity. If you're trying to interpret the Euclidean path integral as a density of states, then that's an issue. But here you get what you get. Here you get what you get. Okay, now let's have something falling in, say from one of these horizons. Resolution here has gotten bad. On to Scri+, and let's examine what happens. So of course you can use Raychaudhuri's equations for the horizon, and that just cares about the horizon, doesn't care too much whether you're in de Sitter or not. And well, the surface gravity times the change of the area is the energy flux. If there was angular momentum, you could easily incorporate it. So that is easy enough to do. But now let's try to relate that to what happens if you see, I'm sorry, this resolution's gotten so bad. Okay, but let's try to see what that means on the boundary. And the key thing is that you have a conserved quantity. So, you know, we are going towards the first law. In the first law, you make small changes. So to leading order, even though you have this matter falling in, you can take the killing vector to be still, the original killing vector to be still a killing vector. You have a conserved current. And because of that, the energy flux through the horizon can be related to a flux of a suitable quantity of the matter or the stress tensor at Scri+, and then the Einstein equations allow you to relate that the flux to the change in the extrinsic curvature, and therefore to a change in the pressure. Okay, so I'll skip the steps because I don't have the time, but this is the version of, this is the way the first law looks then, that kappa times delta A up to this factor is related to minus the change in the pressure. The origins of this minus sign are if the mass parameter went up after stuff fell in, or rather, let's say you had a black hole, some stuff came out of it, passed the cosmological horizon, hit the boundary, finally the mass is smaller. Mass is smaller means area is bigger because they are anticorrelated, but pressure is smaller, and that accounts for the minus sign. Okay, little strange. Had I kept the I, it would be even stranger. But okay, this is already pretty strange, but okay, that's what you get. Okay, now the interesting thing is you could look at stuff falling in from the other horizon. This is the new feature in de Sitter. We have two future horizons from which the boundary receives signals. So if something can fall in from the other horizon, you ask, we derived a first law, kappa times delta A is minus delta P, looking from one horizon, does it hold for the second horizon? Okay, now I didn't give you time, let me just explain it. I didn't give you time, but okay, here delta P was, say you're going along the boundary, which is Euclidean, you measure right value minus left value. Okay, you choose one direction, measure delta P as mass to the right minus left and area, then you get this minus sign. Okay, now you look here, this is left to right, and you ask, do you get the same rule? And the answer is yes, and the simplest way to try and tell you, but then one should think it through more carefully, is let me reverse left and right. If I reverse left and right, then this boundary, this horizon begins to look like this one, and you mirror the situation. But of course this law doesn't, both terms change sign, and therefore the law as such continues to hold. Okay, so this one law then accounts for the behavior of all kinds of stuff, whether coming in from one horizon or the other and reaching the boundary. And so this is a general formulation of the first law as seen in terms of quantities on the boundary. Okay. T is real, S is real, but P is imaginary.
P is imaginary, I see.
P is imaginary. So the pressure, the stress tensor you would get for a Schwarzschild black hole itself would be imaginary. And then its change would be. So you would say, if you use that stress tensor, it's I times that stress tensor, a real quantity, which is.
I see.
So that I is peculiar. Already the minus sign is the I. Is
I'm not sure why you're worried about the minus sign, because I could have declared minus I as one, right? When you have dropped the I could have dropped a minus I.
You could have dropped a minus. I'm coming to the I. You can't drop either. So actually it's the I times minus that you have to keep it. I was trying to make it semi-plausible before I gave it away. But you're right. The I is there. I'll come to that very soon. But anyway, you do get a general law. It's got a funny I. You don't know how seriously, but there is a general universal law. The time is over. Yeah, but I'm getting 5 minutes more. Have some parity. Sorry. Okay, but I'll finish in 5. Okay, so the general nature of the law then suggests that, okay, now I'm taking a jump, going from the semi-classical theory to a more quantum one, still sort of semi-classical, equating temperature with surface gravity, area with entropy in general, to state the first law in this form, where we would now like to associate these quantities all with the boundary theory. Okay, so associate an entropy also with the boundary theory. The area was a function of mass. The mass was equal to the pressure, and here the area up to whatever usual factors is the entropy. So we would like to say that the boundary theory has an equation of state. Okay, S is a function of P, which just arises from the fact that the area was dependent on the mass, and the mass was equal to the pressure. Okay, so that's the general formulation. This law allows you now to deal with situations which are more complicated. Things fall in from both sides. You have a quiescent phase. The entropy here is not the area of any horizon, but that's what you're led to just from the general formulation. And you can check these more complicated cases in 2 dimensions, JT gravity, etc. In some cases, spherical symmetric cases, and so on. So it works in a wider setting. What about the second law? And then I'll conclude. No second law, because you don't have an arrow of time on the boundary. It's a Euclidean theory. You can go left or you can go right. So if you were increasing inevitably in one direction, you would decrease the other in the Of course, for each horizon, you have a second law just from Rai-Chaudhuri's equation, but nothing in the boundary theory. The only version we could find is that if you wait long enough, ultimately any black hole will evaporate because the temperature of the black hole horizon is bigger than that of the cosmological horizon. So you'll be just left with empty de Sitter, and that has the biggest entropy, and the entropy is the same all along. So whether you go left to right, right to left, the entropy here at this end and this end are the biggest values after you account for all the stuff that streams out, and that's a left-right symmetric statement. So the fact that everything finally decays to de Sitter and de Sitter maximizes the entropy has a reflection on the boundary, as the entropy you would associate on the extreme left and extreme right being equal and the biggest values. Okay, so that's it. So that's the only version we could get, but there is at least that. Now I'll just end with two comments. We haven't been able to include bulk entanglement and derive a generalized kind of second law even for black hole horizons in de Sitter space. That kind of is an irritating fact. I feel I haven't understood, but I can tell you more if you're interested. The I got away with, I dropped, but I should include. You might say, hey, who told you? Maybe the correspondence is without the I, but you can't drop normalization coefficients in conserved quantities. They are sacred because the word identities hold with a particular definition. This is a word identity, say, for translational invariance. If I suddenly drop the I here, then I'm going to not be able to preserve the word identity because these don't have the stress tensor. So normalization of conserved currents is a sacred thing. That means, as Ashok was emphasizing, I should have actually kept, if I was working with a really renormalized stress tensor and stated the law, then the law would have had an I in it. And well, what do I know? I don't know how to make sense of it, but this is a general fact. It is a general law, but it's got an I in it. Maybe this is a strange theory, but can be so strange as to accommodate this kind of a law? I don't know. Okay, last. Well, at least you have this kind of general law. So you might say, let's take de Sitter entropy and more generally the entropy of black holes seriously. Is there a microscopic explanation? And here, what we have been able to do is in two-dimensional JT gravity, we've been able to map the theory very precisely to a matrix model, which actually is the Saad-Schenker-Stanford double scaling matrix model. And you have both de Sitter space, the Hartle-Hawking wave function of de Sitter, as well as black hole states present in a precise way, and the number of states in the bulk when you quantize properly agrees with that in the matrix theory. But because the matrix theory is in the double scale limit, both number of states in the bulk and boundary are infinite. So there's a one-to-one map, but it's not a very good counting just to say infinity equals infinity. So we're trying to deform the matrix model to a finite n version and see if there can be gravitational duals, and hope then that there can be some kind of counting of states. But at least there's a one-to-one map. So we hope that we will have some kind of a map emerge in terms of a microscopic counting of degrees of freedom. I'll stop there. I'm very, very sorry to go over time, but just to say there is a kind of holographic dictionary. It has all the elements in place. The behavior of the laws of thermodynamics is a little strange, but there's some universality to it. And maybe that's enough motivation to at least try and press on ahead and try to find microscopic versions of this duality. Thank you, Sachin, and sorry for that.
Super interesting talk. Since we are following factors of I, do you, for say DS3 CFT2, do you have say like any comment on the central charge? Because many years back there was this idea that the central charge is imaginary.
It is imaginary. Central charge is imaginary for the same reason. You can obtain the central charge as a Casimir term. And well, here you have e to the IS. So when you look at the response, you get an imaginary term.
But
and so,
sorry, I just meant it also shows up in the 2-point function of the stress tensor.
It does show up. It does show up in the 2-point function, and it also shows up in the Vera-Zero algebra. So now you want representations, not unitary, or with some other notion of, I don't know, but at least with a I in the Vera-Zero algebra. Yeah. So that's interesting. What are such representations? Nobody knows.
The O 2-point function also has a vector Y.
The O 2-point function can have also complex phases in it.
coefficient of that is totally determined by the coefficient of OO because it's a non-homogeneous whole vector, right?
Yes.
So TOO will not be like it's not a data independent data.
It's not independent
So
data.
the I factor over there should come from OO to point function I factor.
Yeah. So the T with the I satisfies that word identity. The proper, the proper stress tensor satisfies the word identity. And that word identity inherits its coefficient from the OO correlate.
Get this black hole thermodynamics from Euclidean space.
Oh, that's a great question. I don't know how to do it. There's no time circle, and that might make you suspicious about the thermodynamics. But there's anyway a kind of universal map, but I don't know how to get it from Euclid.
But if you just analytically continue the black hole solutions to Euclidean space, you get some nice manifold.
So the way one could try to do it, there is a d by dt killing symmetry, and put that on a circle. You could try to do it. If you do it, I haven't thought about it so much, you do get some kind of a Euclidean geometry. Just let me think 1 minute. You do get a geometry, and it becomes a little bit singular where the emblackening factor goes to 0. Now in the Euclidean case, that would, it'll cap. It should cap.
I was thinking that if you just had a particle, it looks like it's just going on an equator on the sphere. Now the black hole will eat out a tube. It's like a tube on the sphere. I was imagining that that's the kind. But
It's a good question. Let me think more about it. Of course, just Euclideanizing pure ds gives a nice map to the S4. But good question, and
I was wondering if that would back to this question, because if it is something like a particle, then maybe its fluctuations also have additional
it's certainly true that I see. It's certainly true that you could try to incorporate a Euclidean version.
which would suggest like an I might come from a 1, 2.
Yeah, you might. I think is the reason I'm hesitating is you might want to keep the static patches and Euclideanize them as a more natural way to do it, rather than the Milne patch that I was using. And I think in the static patches, what you say is true. If that was in the static patches, what you say is true. And there it's d by dt is really a time-like killing vector. And there it's the natural thing to do. And
So then it should be like fluctuations of a geodesic. And we know that that has an I. I was wondering if that somehow plays a role.
No, certainly the Euclidean versions with black holes, where you analytically continue the static patches, get rid of the i's up to the sign. They do, and you can check that. And that's certainly the case.
And if the one would determine
the one, because you have to, you have to rotate the conformal mode to make sense of the one loop determinant. And when you do that,
the fluctuations of the positions play.
If you did it in terms of particles, if you didn't do it in terms of particles, just black holes, then you just have some geometry. And
The black hole in the end is also a particle. So its position
probably, although when you do the small determinant, you just do it about the black hole background. Probably, okay, maybe for light enough. I haven't thought about it like that. Probably. But I haven't thought about it like that. But
I just had a question about the fact that your CFT is not reflection positive, right? So things like crossing symmetry and stuff are less powerful. But is bulk unitarity in some sense going to still give you some constraints?
So there are many interesting questions. What constraints can you put on the boundary theory? Just first of all, from the fact that it should make sense as a CFT, a boundary. You can check things like OP, stuff like that, what's up. But then there's a very interesting question of bulk unitarity and, maybe some approximate notion of locality. So those have largely not been explored as far as I know.
I see. Even the OP, you still have some oscillating things because of the.
You have some oscillate, but it squares up with the fact that the dimensions themselves are imaginary. So one way to think about it is that the machinery of bulk to boundary propagators actually goes through. I didn't get a chance to talk about that. And then in that language, the OPE gets more reasonable to see just geometrically, because when things come together, you construct the relevant propagators that way. So the singularity structure seems to be okay. We tried to analyze it in general. I didn't talk about it. But bulk constraints from bulk unitarity remain to be understood. Sorry. It's
last talk before lunch.
Can you all hear me? Yeah.
Okay, so please.
Okay, so there's something last 4-5 years I've been looking into more depth on divergent series. Earlier we used to worry if it is divergent, it might be something to worry, but it looks like there are more and more hidden things which shows up. So I'll take you on a tour of what I have seen, but this is some details pertinent to three manifolds in Chern-Simons. We have discussed in this paper, and Aditya will give a poster presentation with the details, but I will kind of give you a background of what is happening in this field. But before I start, I should thank all the organizers here, and it's really wonderful to be back at Bhubaneswar after the earlier Puri visits. So it's nice to be here. So I'm really enjoying this place. Okay. So if you remember last year or 2 years ago in ISM, I wanted you to take you on a excursion, see flamingos, but I didn't really mention swans because swans are like, the additional pieces which we don't need to worry. But when we say swans, we always think it is white swans. Okay, so that's what is the conventional saddles in any theory. Whether we do quantum mechanics or quantum field theory or string theory, the conventional saddles are like you just wake up, you extremize, you do things, and those what you call as saddles. So like white swans is what it comes into your mind when you look at swans. Surprises, there are more than these saddles. Like the presence of black swans are also there. Okay, so you can go and check in the Wikipedia, there is black swans, but we generally don't look into it. Okay? But it can topple many of the information about the system, even though it looks like a tiny piece. Black swan information can topple many things, or it is very important to look for making convergent series, all this. Okay, so in some sense, we kind of overlook this information. So they are not saddles, but they are still classical solution, which means equations of motion will be satisfied by them. Okay, so that is what it means, which will be the theme of my talk. Not anymore on swans, but somewhere the parallels can be drawn in the theory which I am going to discuss. The brief overview of what is called resurgence, where these information can pop up. So does classical solution, when we say, does it refer only to the conventional saddles which you find by extremizing the action in a theory? Let's show you a toy example where you can see black swans. And then many of these things are not that easy to track in general quantum field theory. Okay, so it appears that Chern-Simon's theory is a good playground where we could check many of these things. And what are our results for some three manifolds? Okay, so this is something which I teach in quantum mechanics course, WKB approximation. I'm sure all of you know this. That the main theme is you have to look for turning points where energy is equal to the potential energy. And we have a quantization condition which comes from the connection formula between region 1, region 2, region 3. So this automatically gives us a quantization condition on P, and then you can interpret it in terms of the energy. The simplest example, so and I should also emphasize that this P will have a series expansion in H bar, and usually in the lowest WKB we don't really go beyond P0, but technically you can start writing the higher order terms. Okay, so quantum harmonic oscillator, you all know that if you just take it as half kx squared, the saddle is at extremizing, the potential is at x equal to 0, and then you have plus or minus 1 in term, if you take the energy of the particle to be 1, or in terms of energy, square root of energy plus or minus, right? So that is what we understand. And even this expansion, if you do, interestingly it truncates. So P0 and P1 are non-zero, and P2 onwards it's 0. Yeah. So suppose you slightly modify the moduli, is the way we call it when you turn on A0, A1, A2, that changing the moduli does not change the physics, at least for the harmonic oscillator, in the sense that the 0 of the energy will shift depending on this A0 and this A1, but it's equally spaced, but the saddle is not at x equal to 0, but it is going to be slightly shifted. This is something which you all know, that shifted harmonic oscillator, but it's still one saddle and two turning points, no change. Okay. So that, let's continue for the higher quartic harmonic potentials. If you start doing this, and if you want to restrict yourself to be on the real x axis, then you will claim that there are only two turning points, right? But if you do order by order calculations here, it turns out that the PNs grow like n factor. This is that Bender and Wang paper where this has been detailed. So what is the puzzle here? The puzzle is harmonic oscillator, the turning points are exactly on the real line, but here the turning points can be also in the complex line, complex coordinates. All the roots of unity, 2nth roots of unity are all the turning points. Right? You take x power 4, you will have e to the 1/4 times plus or minus I or plus or minus 1. So those turning points we never look at. When we do the quantization, we look at a cycle which is on the real cycle. We don't look at the complex cycle, and that is the reason why you start seeing divergences. The series is not a convergent series, it's a divergent series. Okay? So this kind of indicate that we are missing some of the cycles and we can't work in the real line, we have to go to complex line. Okay? So there's no option. So adding moduli, if you do, this is also something which we all do, Higgs mechanism. You know, there are more turning points, more saddles emerge when you slightly shift by adding moduli. Here when I did it, there were no more saddles added, but here more saddles gets added. So there is a trading between cycles being seen in the complex plane, or you can also choose your moduli in such a way that all the saddles are in the real line, but then you have more cycles. Okay, the number of cycles could be different, but things are happening. Okay, and these are the reasons why you start seeing infinities It's not a convergent function, it is going to be infinite. Okay. So which means there is some kind of secret information being passed from looking at perturbative series around one cycle can actually give you information about those complex cycles in the complex plane or cycles in if you open up this model. So this is what happens, and that is what we call it as resurgence. Okay. Which finite model? No, you have to take all orders. You have to take all orders. There is no option. Right? For harmonic oscillator, it doesn't matter. It's a finite function. Is that clear? You see, in all our quantum mechanics course in perturbation theory, we keep the coupling to be small and say do first order, second order. But technically, you should do all orders and show that the nth order and n plus 1th order, that ratio is, converging, right? It's not happening. Huh? Yeah. So it's systematic. Yeah. Systematically can be done. Yeah. Okay, so I'm just stressing the fact that we have to be on complex Z plane, at least in the quantum mechanics. When I go to field theory, I'll start looking at complex Chern-Simons and so on. So this is the reason why I'm trying to stress the fact that just working on a real line will not capture all the physics. Okay, so just to summarize here, so I've said that you can write this power series, and this for any higher potential, higher monic potentials, they will all diverge, and series is divergent, indicates the presence of other classical configurations or other saddles or other cycles. Okay. So complex WKB is the route to tackle these problems, and this is sometimes called as exact WKB or Voro-Silverstone method of doing it, and this is supposed to be taking care of all the saddles, taking care of all the cycles. Okay. So WKB period, so if you take the cycle between x1 and x2, this is what is going to be the WKB period, and you know that because the px diverges, the WKB period is also diverging. So you need to somehow tame these WKB periods, and the way you tame these WKB periods is by this well-known prescription, which is called Borel transform. Okay. So Borel transform, basically, if it is growing like n factorial, so you divide by that n factorial, and since I am implicitly assuming that only the even powers were required and odd powers can be related in WKB, I just put the even powers here. So you need to tame this by dividing by that growing factor, and then this will be a convergent function. Okay. So the yeah.
Px is, sorry, I got it wrong. Okay, sorry.
Is that okay? Yeah. Okay, so I'm just trying to stress the fact that this pi hat is called the Borel transform, and it's a convergent function. Okay, so this one, this convergent, this is divergent, but you can divide it by 2n factorial, and then it become a convergent series, and that's a convergent function. And in the complex plane, okay, so I have taken the complex, not work out with h cross, which is real, but I'm taking psi to be a complex coordinate. But the first thing you have to notice is that if I plot this, does this have singularities? Okay. So you can go and look at this function and see whether it has singularities. It could have poles, it could have branch cut, it could have logarithmic singularities. So everything in that singularities means that there are perturbative expansions around those cycles. This kind of indicates, if you don't find any singularity, then it would be, you don't even need to do a Borel transform. But if you start seeing these singularities, you know that there are instantons, there are non-perturbative effects. You know, various things are embedded in the conventional perturbation series which you do around the trivial solution. Okay, so most of the time when we do path integral, we just expand around a trivial solution. But we need to know that from that you get all the information. If you do the Borel transform, you get all the information about other singularities, other non-perturbative effect. Everything is incorporated in this. Okay, so depending on if it does not have a singularity along, let's say, a specific ray in the complex I plane, then you can do a inverse transformation which is called Borel resummation, and you can write the Borel resummation along a particular ray which you take it along the angle phi. So these things are systematic, and you can regenerate the perturbative series and everything goes through. Okay. Okay, so just as a warm up, yeah, I said that if it doesn't have a pole along that ray, you can do the resummation.
Also, when it goes from the original inverse Borel transform is from on the positive real axis.
Not really, no. This phi angle is what I meant.
Yeah, but I mean, when you go from the positive real axis to the this ray, you should not
have any pole or any
inside this
singularity.
region.
Yes,
inside
yes.
the
Exactly,
region.
exactly. Along this ray, if there is no singularity which you hit.
No, not only along the ray. I thought that in this whole region, from the positive real axis to this ray, right? Because the original Borel transform
really.
is in
So this is the path I'm going to take to look at this. So, like, let's take a simple case of classically forbidden and classically allowed in the first region 1, region 2, region 3, which I'm showing. You can see that it will not be Borel resummable along the real line for classically allowed. It will not be Borel resummable along the imaginary line, which is pi by 2, and so on. It is a very systematic exercise. Yeah, it won't cross. I'm saying if there is no singularity, then only this will be a Borel resummable. Otherwise, you have to do the Stokes discontinuity. All this systematically has to. That's all I meant.
So we started with a divergent series, this capital Pi gamma H hat.
This is a divergent series.
Yeah, the left hand side.
And then I'm trying to make a Borel transform.
Right. So
that series is a convergent series.
that series is a convergent series.
Yeah,
So
but
am I
it can have poles, singularity, branch cuts, logarithmic, all these things can be written, right? Let's take a simple, I don't know which board I can use. Let's take it as summation over some -1 to the power of n times n factorial z to the power of n.
Okay.
So, and then now I'm dividing by n factorial. So then summation over -1 to the power of n z to the power of n is 1 by 1 plus z.
Right.
That z equal to -1 has a pole singularity.
Right.
So I cannot take it along the real line in doing this Borel resummation.
I see.
As simple as.
Okay. Thank you.
Okay. Fine. So another warm up which is also interesting, that you take, since I was saying it secretly captures the other saddle information from one saddle where you do a perturbation theory, we can look at this kind of a polynomial potential just to see how things are happening. I must say that many of these things, both Archana and Aditya have been helping me, and we have been learning together in the last 1.5 years. So many of these details they also know. Even if you are stuck, you can talk to them after lunch and so on and get various details. Okay, so extremize this. So when you extremize it, one is a trivial saddle, and usually we do around the trivial saddle all the perturbative expansion. Okay, and that series is also divergent. So which means it should give us information about the other two saddles which are in the imaginary line. Okay, so this is what I'm going to illustrate here, which at the saddles the actions are 0 and -1/4 on the other two saddles, and you do a perturbative series around the trivial saddle. So this series, explicitly the coefficient turns out to be the factorial form. The explicit form is this for this particular S of Z, and then you can series expand it, where K is the coupling, so you can series expand it in 1 over. Okay, and clearly the radius of divergence, convergence, if you see, it is going to be 0 because you have to take the an plus 1 and an that turns out to be 0, and this implies that the series has to be, we can do a Borel transform of this. So the Borel transform can be done, and the Borel transform, if you do, it becomes a neat function which is the hypergeometric function. And the hypergeometric function, you can see that where it has a singularity, and the singularity will be at xi equal to -1. Okay. So that's a hypergeometric function, and here I've written the earlier series by dividing it by n factorial. Nothing more I did, and singularity is at xi star equal to -1/4, and this -1/4 can actually be reinterpreted as the original function at z2 star minus the function at z1 star, and that one was 0 and this one was -1/4. So the Borel plane singularity actually captures those instanton or non-perturbative effect, which can be written in terms of the xi. Okay, so what I'm trying to say is that it captures the other saddle. The Borel plane singularity captures the other saddle. The other saddle is at value which is -1/4, and you can expand. So this Borel transform value, you can expand around the saddle, and you expect that that gives you the series of the other perturbative expansion around Z2 star or Z3 star. So it is embedded here, even though we confine ourselves to a trivial saddle and do thing, because it is divergent, it has that embedding of the other information about the saddle. If it was not divergent, you can assertively say that there is no other non-perturbative effect in the theory. Okay, so this is what is the series which you can write in terms of this curly xi, and this series is nothing but, yeah, the S of Z value. Actually.
Is it a general phenomenon that the location of the singularity of the Borel plane gives you the action of the other saddle?
Yes, exactly. The difference in action, if the trivial saddle is 0, then it is giving you this.
I see. Okay.
It happens for every theory, at least the Chern-Simons theory and other theories.
But weren't there two saddles, or their actions was the same, so that's why there was
It
only
is coincidentally, it turns out by this symmetry that both of them have this.
And instead of a pole, you make some cut or something like that also. In that
You
case,
can have logarithmic singularities with many, a chain of things you can.
what does it mean? What is it? What about saddles is it telling us then?
So it will get shifted, no? It will get shifted by an integer, and then you get a Q series and so on in our. Yeah. Okay. Oh, I'm still not crossed this. Anyway, so my idea is that essentially that's for showing for data that this was the series, and if you did a perturbative series around the other saddles and do a Borel transform, this is exactly same as this one, which is the expansion around -1/4. In some sense, they're all interconnected. You can do perturbation series around Z2, or you can do perturbation series around Z1, but you can get one from the other very beautifully using this Borel transform and looking at the singularities and expanding around the singularity. Okay, so that's the upshot of this. And another toy example is something where you will see the black swan. This is one of the footnote in Bukov's paper. Very interesting to see that this has much more. So what we'll do is, first of all, I've already conveyed to you that you cannot be on the real x, real y, and real z if it's a three-dimensional integral, because you get new physics by taking an analytic continuation of x, y, and z. Okay, so don't confuse the z with, this is the 3-coordinate Cartesian coordinate, but you can promote it to the complex coordinate. So that's the first thing. So S should be seen as a map from C3 to C. You should not see it as a map from R3 to a real value, but it is from a complex three-dimensional space to a complex number, and take this and extremize it. If you extremize it, then you get it as only 0, 0, 1. Okay. So that's the only critical value I see. So that's what we call it a saddle. The same argument we'll do. We take the saddle, do a series expansion, do a Borel transform, try to look at the singularity. If this was the only unique saddle, you should not get any more singularity. Right? If you find one more singularity, then you know there is another saddle, but it is not visible. That's the black swan. Okay? Is that? Am I conveying what I am trying to say? It's not visible by extremizing it. But there are something which is beyond extremizing.
Of the you're calling, what are the black swans? Singularities of the Borel
Let
transform?
me proceed this and then I'll come back to your.
Thank you.
Yeah. So critical value, once I put x star, y star, z star, I get it 0, 0, 1, then the action becomes half. Okay. But if you do a perturbative expansion around that critical saddle, okay, I can do it for this function form. If you write it out, then that asymptotic series turns out to be, you can try and do the Borel transform and ends up getting this. It has a singularity. Yeah.
In the whole complex plane, you are saying there is a unique saddle.
This is, as far as extremizing is concerned, there is only one saddle I can see.
In the full complex plane, there is not a saddle.
That's the only saddle I see by extremizing it. But after I do a Borel transform, I see a singularity in the Borel transform, which means there is one more saddle.
Yeah. Yeah, that's sort of same.
You check it. I have checked it, but you can check. There is no other solution by extreme. You just have to extremize it and put them to be 0. That's all I'm saying. Yeah, but whatever you do, this is the only solution you can.
Sorry, but
yeah.
What does the Borel transform of the around this unique saddle will give then?
It gives you a function, a convergent function. Borel transform means whatever is the divergent, I divide it by that n factorial and I get a convergent function.
But let's say,
and that convergent function can have poles, branch cuts, logarithmic singularities. If I have, I know that there are non-trivial saddles present there in the theory. Some could have been found by extremizing that. Ashok thinks that by extremizing that he will get the other saddle, but you can check it's not possible. But, but what I'm trying to say is that there are new things which emerges from the Borel transform, giving us a new saddle, not a conventional saddle, which is what I call it as a black. Not me. This was Sergei Gukov in one of his talks said about this. Okay.
After Borel summation, as naively speaking, as the regularized version of a series that is divergent.
Regularized you can call it, but these are called as a Gavre series of type 1, where you make it into a convergent series by dividing by that.
Right, right. But I could have divided with something even bigger. I could have divided by 1 by n cube, for example.
No, you have to do this systematically. Depending upon what is the type of divergent series, you have to do it. If it is Gavre series of type 2, then you have to divide it by 2n factorial and so on and so on.
I see.
So
I see. Oh, it's fixed. Okay.
Yes, that's the procedure by which you.
Okay, thank you.
Okay. Okay, so I'm just trying to say that the Borel transform ended up giving us one more singularity in this case, and then this means that there is one more saddle, and that saddle should give you the difference between the new saddle is what I call it as beta, and then this was alpha, so that should give me the difference in the action between both of them.
Quadratic term.
This one, this is the S.
Yeah.
So I'm treating this as a perturbation XYZ as a perturbative series.
No, I'm just.
And then integrate on all of these.
Yeah, simultaneous solution of 3 equations, but they'll have quadratic terms. Is it not normal to expect that I'll have more than one solution?
Okay, you can check it. So I'm just giving you the flavor of what is black swans in this period. Okay, but you can check and you can some of the examples can give an insight, so that's why I put in some examples. Okay, so what I'm trying to say is that the Borel transform on a trivial or a specific saddle, if you do, it encodes information about other saddles which may be conventional saddles, which may not be conventional saddles. That's the way we can spot many other non-trivial saddles, which is called, and they are important because they will have this instant on effect, non-perturbative effect. We can't ignore them when we do the final computation.
But why are you calling them
Classical solution. That is, extremizing will give you classical solutions, but you will also see that there are more solutions which will satisfy this. That's all I am trying to say.
But solutions to which equation?
Solutions to which equation mean what?
Normally, you extremize it to derive the classical equations, right?
I agree.
And these are not solutions to those equations, right? Because you said that's a unique solution.
They will turn out to be like an asymptotic way. Let me continue, and then you will get the feel of it. So what I am saying is, consider a point parameterized by epsilon as 1 over epsilon epsilon 0. This is not actually a classical solution, but in the epsilon tending to 0 limit, it will be a classical. So this is what is called as asymptotic ends. So black swans will not be seen if you fix a finite domain, but if you start going to an infinite dimensional or infinite domain, there are asymptotic ends where classical solutions are not satisfied, but they will be satisfied in the limit when epsilon tends to 0. Okay. So in the limit epsilon tending to 0, beta becomes a saddle at infinity with s beta being equal to 0, and so Borel plane not only captures information about usual saddle but also extra saddles lying at infinite distance region. There it will not be a it will not satisfy equation of motion, but in the limit epsilon tending to 0, they will satisfy the equation. So it's very interesting that there are some asymptotic ends, and these can be seen in. Yeah, so it will not converge if you are in the XYZ, which is a real plane.
Yeah, x is equal to y is equal to z.
You have
doesn't
to make a
converge.
choice being on the C. That's what I said. It's a map from C cube to C and not R3 to R. Yeah, you choose your coordinates in the complex plane and do the appropriate integrals, and it will converge.
But
Yes, in the thimble, left-read thimble. I didn't want to use too many terminologies, but there is a specific thimble you have to take and do the.
But how do you see it when you do the inverse Borel transform? I mean, there's an ambiguity there. How you are?
No, right now I'm not really doing the inverse Borel transform, but you can do that also appropriately by choosing.
No. My question is there's some ambiguity, right? And this contour that we're choosing to make to define the original integral, right? Original. Yes.
Okay, sorry, I'm going to really fast forward here, but let me just. So this whole theme can be tested. In fact, some of the questions were asked whether surgery, rational surgery or integer surgery, which gives you various 3 manifolds, whether such solutions are possible as asymptotic ends. At asymptotic ends, they don't satisfy classical equations of motion. Classical equation of motion for Chern-Simons theory is that it should be a flat connection or the field strength has to be 0. Okay, so let me just run you through. So observables are knots, expectation values are not invariants, and the partition function which we work in Chern-Simons theory are the 3 manifold invariants. And SU2 is something which you can start with, SU2 with A being, the SU2 value, but because of this making the divergent series by Borel transform, you inevitably has to go to SL2C flat connection because it becomes a complex phi Chern-Simons. Okay, there is no way out that we have to, and you have to choose a thimble which is going to be the middle dimensional manifold with a holomorphic function to do various calculations. Okay, so this is the theme, and equations of motion is space of flat connection, Usually you take a trivial flat connection and expand around it, and we can do a perturbative expansion. And the observables also, you have different spins you can choose of SU2 and write the observables for any node as expectation value of Wilson-Loop boundary. This is just a crash way of saying that SL2C cannot be. It is going to come anyway from your research and analysis. Even if you confine to SU2, SL2C will come as a consequence. So the theme is the Chern-Simons coupling. When you do SU2, we say K has to be an integer, but it has to become complex. Okay, this is analytic continuation of the SU2 Chern-Simons coupling, which was integers, but now it will become any complex value. So, and there are some interesting conjectures also between topology and geometry. All the things which we do in Chern-Simons is topological in SU2. All the invariants are topological invariant. Doesn't matter whether the size of the knot is this or this big, but there is some connection to geometry in SL2C Chern-Simons. The geometry is the complement of the same knot. You know, there is a simplicial volume for it, and the simplicial volume can be captured from the topological invariant, and that is what is called as a Keshev. So if you take the knot, take a tubular neighborhood, remove it out, that is what is called as a knot to complement. That is also 3-manifold, but the 3-manifold has a boundary which is a torus boundary. Okay, and yeah, so the thing is, this volume is a simplicial volume which is stacking the tetrahedron on a surface of a knot complement, and that can be worked out per the volume of 2 tetrahedrons are required for figure 8 and so on. So this is simplicial volume. Okay, and this simplicial volume is showing up as a part in the action in SL2C. The leading order term will come with a simplicial. Okay, so this is one of the interesting conjecture. The topological invariant captures the geometry of this SL2C leading order simplicial volume for the same knot complement. If you take the knot K, then the knot complement is a three-dimensional manifold with boundary. Moreover, since I said the classical solutions are the flat connection, I need to know what are the space of flat connections. And the space of flat connection, there is a systematic procedure, and that space is given by the 0 of this A polynomial, and this A polynomial can also be worked out systematically by looking at the fundamental group and with finger representations, finding the longitude, and since the knot complement has the 2 boundaries, 2 cycles are there on the torus boundary, longitude and meridian, we can work this out. Okay, I'm very quickly saying things. And then there is also an alternate way in which one could do this by taking the colored zones, expanding in this limit, and try and compare terms and pull out these terms. So this will also give you the 0 of the A polynomial, which is what gives you the space of flat connection. Okay, it's very defined. We know what is the space of flat connection for a knot complement, but I want it for closed manifolds without the torus boundary, which means I need to do a dense surgery. So take this knot complement, I need to glue it with another disk cross S1 so that it gives you a closed 3 manifold, and that closed 3 manifold you need to do by a homeomorphism between these 2 boundaries. Simple homeomorphism people do is the S transformation of relating A cycle to B cycle or meridian to longitude, longitude to meridian, but in general you can take P times meridian plus R times longitude to be related to the meridian here. So if you do that, then they are called as new 3 closed 3 manifolds, which is by a P by R surgery of a knot in S3. So, and this is the shorthand notation for such 3 manifolds. Okay, yeah. Yeah, so can I go to asymptotic ends? Sorry.
Now you take your time.
Sorry, I am on a complex time now, but I'm almost done actually. So this is what I mean by, for closed 3 manifolds, you have to take an intersection of the 0 of the classical A polynomial with the surgery constraint. Surgery constraint for a P by R surgery is this, and then we have to work out a number of solutions, which will be a finite number of solutions. And what about asymptotic ends? Okay, and asymptotic ends, there is a systematic procedure by writing those holonomies for the meridian longitude and the generators of the fundamental group for the knots, and these can be done, and we can end up getting. So the upshot is that we have asymptotic ends. Okay, when epsilon tends to 0, then those asymptotic ends satisfies the field strength to be equal to 0. So it means it becomes a flat connection, and we call that as flat connection at infinity. And there are cases where A infinity may become singular, but there is a modulo gauge transformation freedom is there. If we do that, we can make the Chern-Simons action to be a finite value. Okay, so these definitely leads to extra contributions to the path integral and show up in the study of non-perturbative physics. And this is formally to show you that for any 3 manifold, a perturbation around one saddle you can do, and then you write the Borel transform, and once you write the Borel transform, you can show that the singularities will capture the other saddles, including the saddles, asymptotic end saddles. Okay, and some examples, we have worked it out for knot complements which are twist knots, and we do have, and I urge you to take a look at these details from the poster by Aditya, who is a postdoc and will be applying for more postdocs very soon. Thank you.
Right, Raman, they understand that for some of these knots you knew the answer by surgery techniques. You didn't. But then if you then want to, you know the answer exactly, not in an expansion. But then you take the answer and expand it in 1 by k, and you want to give an interpretation to the various singularities of that.
Yes.
Right. Okay, thank you.
So it was handleable in this particular, any field theory, it is not that easy to handle. Yeah.
So this,
even in string theory, you do face this, right? The D-brane can be seen as a non-perturbative. Yeah.
Yeah. So these asymptotic ends that you're saying, can I add some deformation of the saddle point problem itself so that this becomes an actual saddle point at any epsilon? Like, can I add an epsilon times something? We can even go back to this toy model. I can take this polynomial and add some term, epsilon times something, which goes to 0. Can I take epsilon to 0 so that I get
it's
new?
Just that I cannot figure out that it is 1 by epsilon without actually finding out what is the singularity in the Borel transformed function. I don't know how you will deform. Are there many ways to deform? All those things, say, I'm not even bothered. I just do it like formal expansion, do a Borel transform, and I look at whether it's singular or non-singular. If it is non-singular, I know there is no other saddle.
Yeah.
If it is singular, you know there is, it could be conventional, it could be not conventional. That's all I'm saying.
Yeah, but I was trying to see whether the asymptotic saddles can be understood as real saddles by deforming it a bit.
I don't think
in epsilon, by perturbing it a bit.
It can't be that easy.
Yeah. Okay.
Sorry. When you do Borel transform of any polynomial, how much of the information about the polynomial is retained or thrown away?
No, all the information is there. It's just that you scale it by n factorial, divided by n factorial. So when you do the Borel resummation, you put back by integral over e to the power of minus I by h.
Okay,
so
then my question is, if you do a Borel transform about some non-trivial saddle, do you get information about all the saddles of the polynomial?
That's a very good question. Some of the saddles you get from one of the Borel transforms, so you can do it cyclically. So once you get those saddles, then you do the perturbative expansion around the other saddle. Again, do a Borel transform there. It can give you this saddle or it can give you a new saddle. Then you can completely converge whether you get all the saddles.
Is it systematic? Like
it is systematic. It is systematic. Sometimes you can overlook these black swans which we find may not be seen. Or
Okay.
equivalently, I don't even know how to do a perturbative expansion around such asymptotic n saddles.
like
That's still
1
an
by
open
epsilon saddle.
Yeah, I don't know how to do
So
that.
you can't do Borel summation about that.
Yes, Borel transform.
Borel
around that,
transform.
I can't do there.
Okay.
Right?
Okay.
There are still open questions. One needs to figure it out how to do this. Yeah.
Thank you.
Yeah.
Yeah, you kind of answered part of my question, but I think I was wondering whether there could be many more saddles than
there could be. There could be.
In the Chern-Simons case, even SU2 Chern-Simons. You think even in the SU2 Chern-Simons
No,
case?
SU2 has to promote to SL2C. There is no way out.
Huh.
Because perturbative expansion just being on the real line, we do see non-trivial cycles on the, even for quantum mechanics. So I'm saying even if I work with SU2, you are inevitable, you have to go to SL2C. There is no option.
Right.
The singularity will tell you that it is a flat connection in SL2C. Yes.
That's fine. No, I'm saying that about that other new saddle.
Huh.
Can you find further saddles, or do you know whether that is the case or not?
So the thing is, there are systematic methods by which we do find this additional saddle which we find for these knots. We do find exactly by both independent methods these extra saddles. We have not found anything more. But of course, this closure property of doing perturbative expansion around these asymptotic end saddles and all is still an open question. We don't know how to do it. If we could do it, then we can fix the closure. Yeah.
Thanks for the great talk. So my question, actually, it's two-part question. So somewhere you had a square root of pi that showed up in your.
Somewhere
you had a square root of pi in your expression.
Yeah, that's because of the gamma function.
Yeah.
N plus half will have a square root of pi.
Okay, because I wanted to ask if that square root of pi was something deeper, whether it comes from evaluating hypergeometric series at something.
Yeah, I don't think so. That's the overall factor, and that comes from the gamma half piece.
Okay. Then the other one was you took this P of x.
Yes.
This P of x, it's a power series over Q and Z, or is it over Q bar, or is it just C?
So P of x is just a momentum. In some sense, it is.
No, but you had P of x as a power series, right?
Yeah, I can write because if I plug it into the Schrodinger equation order by order, I can correct what is the correction to the.
Yeah. So
P naught will be the classical momentum, which is related to square root of E minus Vx. But then P1 will come from the correction from order by order computation. And you can keep going, P2, P3, and in the Schrodinger equation.
My question is P of x valued as a power series over Qx, or Z of x, or Q bar of x, or C of x? Is it a power series with constant complex coefficients, power series with rational coefficient, power series with integer coefficients?
It's just a coefficient. I don't know whether I can say it as real complex. It just pops out from the Schrodinger. I don't think it will be complex.
Okay. Could it be algebraic?
Yeah.
Because the question
It could be a general function. It could be a log function. All the P1, for example, will be related to P naught, involving log of P naught or something. So it could be a log function.
The reason I'm asking this question is because if you do this P of x and you truncate it at some order, and then you try to compute this WKB period, then your WKB period, if P of x is in fact a power series with Z coefficients, Q coefficients, or Q bar coefficients, that WKB period actually is a motivic period. It actually has something deeper geometric structures to it.
I see.
So
I'm not really doing so deep things, but I'm just telling you that quartic potential harmonic oscillator with a quartic potential added can be systematically done by a complex WKB. You need to be on a complex coordinate. That's all I say.
So then one interpretation I had as a follow-up was that when you add these higher and higher, like if you truncate them at higher and higher orders in H, can I ask the gentleman to kindly keep quiet? I'm not able to concentrate. Thank you. So when you add higher and higher order terms, then basically you have this integral. You're doing this pure integral basically.
Yes, yes.
And at some point, your integral, the cycle of integration, it's sort of, there is a cycle of integration that vanishes. So there's a D module that develops some sort of a perversity basically. So which is why I think you should see some of these extra saddles when you. So I have that way of interpreting it. Do you think that is a correct interpretation or is it an incorrect interpretation?
I see. No, the extra saddles is seen from the Borel transform of this series.
Yeah, so exactly. That's the
is
D
what
module version of what I'm saying. So
that is what we see. That's why we have to do a Borel transform of one of the WKB periods, and we'll see singularities there, and that tells me that there is another cycle with perturbative.
Exactly. So this is because there is some perversity developing in some D module. That would be another way of thinking about it.
I see.
I think.
I see. I need to see it. Yeah. I didn't follow. Okay, can you take the mic and?
Is there any systematic understanding on when critical point at infinity appear?
Frame?
When critical point at infinity appear, is there generic understanding?
Infinity, you mean?
Yeah. In the, for example, your toy example, you had a.
So I don't have any understanding. It just comes from the math. Yeah.
Or is there?
No, I don't have any understanding.
Yeah, or is there a way to?
It's something like, you know, this is something which in the recent times of this AI ML, we still feel that many of these, we logically think that these saddles have to be seen, but there could be contribution from such invisible saddles which we may miss, but the AI ML could actually capture them. This is the feeling people have. And it can topple the most of the things that this is very important. It's a very interesting way of viewing things.
And then how about without looking at the Borel transformation explicitly, is there a way to notice the existence of the black swan without yeah, in the toy example, so you noticed the existence of black swan by looking at the Borel transformation.
Correct.
Yeah. But is there any way to notice?
I wouldn't have inferred before doing the calculation. That's all I'm saying.
Okay,
I don't have any insight before.
Okay, great. Thanks. Now
it's lunch.
कैमरा ऑफ कर
Justin also wanted to check.
Yeah, this is a.
Looks okay. It's okay.
Yes, sir. Is that clear? Have a look.
Okay. Yeah, it's
Fine.
file. Yeah. How many pages?
Can I see this from here? Yeah, 92 is showing.
Okay, it's fine. Yeah, it's roughly that. I don't
Okay,
even
that's
know.
fine,
that.
that's
Yeah,
fine.
yeah. Okay.
Okay, thanks.
Yes.
Hello.
Yes. Right. Yeah. Okay, that works, and that also works.
Can we begin as soon as people settle down? Settle
Sorry?
down? Can we begin right about now? As soon as people settle down?
Yeah, yeah, for sure, for sure.
Hello, okay, welcome to the post-lunch session. We now have Dominic who will tell us about the flat limit of ADS coupled to a bath.
All right, so hello, welcome back from lunch, and thanks to the organizers for inviting me to give this talk. Yeah, it's my first time in India, so far I'm having a great time. All right, so I'm going to talk about a paper, like a short paper which appeared on the archive a bit earlier this year, which is sort of like goes a bit in line of the previous talks that we've heard, which were like more about Carolian, or we'll hear something about celestial holography, except that I'm not going to ascribe to any of those notions, but going to study flat space a bit from the flat limit of ADS. Now, I don't think I really need to give like a large introduction that, you know, ADS is great and we understand loads of things. In particular, over, well, the last, let's say 20 years, what has emerged is that quantum information theoretic tools seem to be very important to understand quantum gravity, and in particular also the way degrees of freedom are arranged in quantum gravity. And so here's an example of a time slice of global ADS. And I think, as everybody knows, if we are looking at some subregion of the boundary where the CFT lives, and we're interested in something like the von Neumann entropy, we can get this answer by doing a geometric computation in the bulk, by finding the smallest extremal surface homologous to A. But so this doesn't only tell us what the von Neumann entropy is, but it also tells us that degrees of freedom, which are in the bulk in this region A, can be reconstructed from access to this region capital A on the boundary. Okay, and so the whole point here I want to make is that we have all those nice tools, and we don't really have them in flat holography. And so there's like some popular approaches, celestial and Carolian CFT, but it would be nice to have those tools. And one way you might hope to get those tools is to start in ADS CFT, which arguably we understand best, and then see what you can learn by taking the flat limit. Good, and so this, of course, is not an entirely new thing, but here's like a little reminder for how this works. So here again, I have global ADS with a metric given down here. And so what I mean by taking the flat limit is, well, roughly speaking, taking L, the ADS curvature radius, to infinity. Of course, this doesn't make sense. So what I mean is I'm focusing on physics which happen on scales much smaller than A. And in practice, what I do, I define some new coordinates, t, like tau, the global ADS times, t over L, rho, the radius, is r over L. I sub this in here, and then I take L to infinity, and what I get back is the flat metric. In practice, what it means, I'm just zooming in on the center of ADS. Now, how does this look like from the boundary point of view? From the boundary point of view, it looks like this. So this is what we end up with, some Penrose diagram of flat space, where maybe some excitation tries to escape to Scri plus. And this was already mentioned by Arjun. What this maps to, or like what Scri plus and Scri minus map to, are these little like ring-like or fringe-like regions around boundary time pi over 2 and minus pi over 2, which are of the order of 1 over L. And so if I'm taking this flat limit, what's really happening is that in the strict limit, future and past time like infinity reduce to simple lines. Moreover, like it's a bit of a weird limit. Like the number of degrees of freedom goes to infinity essentially because it's controlled by L over G Newton. I want to keep G Newton finite. And so as I scale L to infinity, N goes to infinity. And similarly for the Tovt coupling, or generally like a coupling in holography, this is typically controlled by L over L string to some power. And so here again, we want to keep L string fixed and scale L to infinity. And so this also diverges. Yeah, and then there's like a couple of other things which aren't necessarily like problematic, but are sort of like a bit icky in the sense that I think we would like to understand them a bit better. I have some better language to talk about those things. For example, if I want to scatter, like do a little scattering experiment here, I need to prepare some states in these fringe-like regions. But the relation between an excitation, or the energy of an excitation in the boundary, and the energy of an excitation in the bulk goes like this. So E boundary is E bulk times L. And so if I want to have scattering at a finite energy, I need to inject infinite energy into the boundary. Then on top of this, there are some other questions you might wonder about, right? In ADS, we typically choose some type of Dirichlet boundary conditions at infinity, excitations reflect. But that's typically not how we think of Scri plus. Rather, we think about it as like a place where radiation can now leave space-time, or you might ask, well, here we have this large region between these fringes. What does this actually map to what happens here? Good, and so the sort of plan of the talk is just to give a little presentation of this, of a new bottom-up toy model where we can now study the flat limit of ADS, but we don't just take the flat limit of ADS as I've done before, but we couple it to a bath before, and this will sort of resolve conceptually at least some of these questions I pointed out. So the hope is, give some maybe interesting new perspective. And then in the second part of the talk, I'll show you how this can be fairly easily applied to take stuff like entanglement entropy to carry it over to flat space and ultimately, but I'm not going to have much to say about this. Hopefully this is perhaps a hint for how to take flat limits in top-down models actually get some interesting flat space physics from ADS, from true top-down models of ADS CFT. Okay, so when I say I want to couple ADS to a bath, what do I mean by this? Really what I'm talking about is a class of models which have also now existed for like more than 25 years, and depending on when you did physics or started doing physics, you might know them under Carr-Trendle-Sundrum model or ADS-B-CFT or double holography. So that changes somehow every 10 years, but it's the same theory, just slightly different emphasis on different things. And so the idea is that we start with an ADS-D+1 space. So that's depicted here, a time slice. And we introduce some brane which cuts off part of this bulk. And we give this co-dimension 1 surface here an action which is essentially an integral over t, so some cosmological constant. And once we derive the equations of motion, we impose Neumann boundary conditions at the brane. And so that tells us that the extrinsic curvature at the brane is proportional to the induced metric times this, or like the proportionality factor is essentially this tension parameter that I've introduced. And if I want to keep this configuration here, then this tension is bounded from above by some critical value. And roughly speaking, t controls the location of the brane. So if t equals to 0, the brane just sits here from the north to the south pole. And as I increase the tension, it wanders off towards the asymptotic boundary. When it's the critical value, you could think of it as sitting exactly at the asymptotic boundary. Good, and so if you do this, and then you look at the induced metric of this brane, you'll find that the brane itself has an ADS metric. So I'm working in vacuum ADS here, with a length scale which is set by the bulk length scale, and then a prefactor which diverges as I take t to t critical. Good, and so this model now has not one, but really two different descriptions, or two dual descriptions, if you will. So one is what I've just explained. It's ADS-D+1 with some d-dimensional end-of-the-world brane. But then what I can do is I can integrate out the bulk. And what I get is a CFT, but now not living on a compact asymptotic boundary, but on an asymptotic boundary with a boundary. And so the way I want to think of this is a boundary conformal field theory in d dimensions, where at the boundary of the BCFT, I perhaps have some additional degrees of freedom living, and the boundary central charge is essentially controlled by the value of t. So as I increase t, the boundary central charge here will increase. Good, so this is, if you will, like the fundamental non-gravitational description. But then what I can do as well is I integrate out the spacetime between this asymptotic boundary and this brane. So I pretend in a way that my brane is part of my bulks of my boundary spacetime, and I get this what's called brane picture. And so what we get here then is, again, essentially a CFT living on the spacetime. So the space here consists of part of this asymptotic boundary, and then here an ADS world volume of the brane. So this is where a CFT, or technically speaking, like a cutoff CFT, would be living. But due to the fact that my brane in this gravitational picture here is dynamical, it will also remain dynamical here. And what I get that this theory here on this green brane is coupled to some type of massive gravity in ADS-D. Okay, so what I get here is some part of my spacetime, which is ADS, which has a CFT or cutoff CFT living on it, and it's coupled to gravity. And at its asymptotic boundary, it's coupled to some non-gravitating bath where the same CFT lives. And so the way I want to think of this is that excitations on this brane here can change into the bath and vice versa. Good. And so when I say ADS coupled to a bath, it's precisely this picture here I'm talking about. Now the gravitational theory has some interesting features. It's has a slightly massive graviton, and the action is some higher derivative action, but as you see, so there's r plus 2 lambda, so it's basically standard Einstein's equations, and then here we have r squared terms. But the strength of those terms is controlled by the bulk ADS length scale, whereas r is basically controlled by the boundary ADS length scale. And so as I move my brane sort of closer to this would-be asymptotic boundary, those terms here become small and I can neglect them. Okay, and so this is sort of like the limit we want to think about. We want to have the brane somewhat close to this boundary. And then in this brane picture, or intermediate picture as it's called sometimes, we have ADS coupled to a bath. Okay, good. So now how do we take the flight limit? And so this has been discussed. One particular reason why people like to I wanted to discuss this is that for some reason, I mean, these models appeared when you were computing page curves. You want to get rid of the mass of the graviton, of this massive gravity theory, and one way would be to take the flat limit. But so what's typically being tried then here is the following, right? So the naive thing you want to do is you take L to infinity by taking t to the t critical. And so this, however, turns out to be too naive. And the reason essentially is this, that as your brain moves off towards this asymptotic boundary, certain things diverge. So one thing that diverges, for example, is the wave function of the graviton. The role of the graviton on this brain is played by some particular mode, which diverges towards the brain. And as you move the brain towards the asymptotic boundary, this becomes a non-normalizable mode. And so you have to remove it from the spectrum. Okay, so what we have to do is instead to take this limit slightly differently. And before I sort of like show you the full details, let me just sort of give you like a bit of a basic example of what's in essence going to happen. And so what we can do is we can start by, so what I've done, I've zoomed in here. So this is the Poincare patch. This is the asymptotic boundary, and then part of the boundary is cut off by this brain. And now increasing the tension towards this critical value basically just pushes down the brain all the way to this asymptotic value. And as I mentioned, this is problematic for a variety of reasons. Your partition function will diverge, et cetera, et cetera. And so what we want to do instead is this. We will pick some point here on the brain, and now we will increase the tension. So what the increasing the tension does, it makes this angle here flatter. But at the same time, we want to shift the location of the defect in the BCFT such that this point here remains fixed. Okay? And so if we do this, then what we get is sort of like a smooth limit from this Karch-Rendel model to now something which is known as the Rendel syndrome 2 model, or essentially that's what it is. So which is the Poincare patch that's cut off by this near boundary brain. Good. Now, with a bit more detail in the general case, if we start with the CFT, the isometry group, or like the global conformal group is SOD, 2. And by introducing this defect, we break this to SOD minus 1, 2. And so now we have this D+1 broken generators. And what they do, acting with them, they, from the bulk point of view, generate new solutions to the same equations of motion. From the boundary point of view, they map you between different theories, or like theories where the brain sits in different locations. Now, for the purpose of this talk, I will just play the game in ADS3. But in principle, everything I'm saying just goes through for like arbitrary D. Good. And so the way this works is, or one nice way of implementing this is you start working in embedding space, and you choose a particular set of coordinates shown here such that your bulk spacetime is foliated. So it's an ADS bulk spacetime, and it's foliated by ADS-D slices. And mu is the slicing parameter. And then you see if you choose mu to be large, then this prefactor here multiplies elsewhere to give you a large prefactor. And so in those coordinates where the brain sits at constant x2, meaning at constant mu here. And so yeah, what you do is if you want to know the induced metric on the brain, you just pull this back for some particular fixed value of mu, and mu is related to the tension over the critical tension, like so. Okay, so mu large means the brain is close to the asymptotic boundary, and the prefactor, the effective ADS curvature scale, is large. Okay, so now in the case of ADS3, from the bulk point of view, we have the conformal group with 6 generators, SO2, 2, and then introducing this brain or the boundary breaks 3 out of those 6 generators. And those which involve acting on x2 will, of course, change the location of the brain, and so will give me some additional solutions. And it turns out that in the case we're interested here, it's useful to act with this L2, 3 by boosting the configuration in embedding space. Okay, and so if you do this, what happens? Now, you start in this configuration where on the boundary, you have a boundary conformal field theory, with a defect or with its boundary here in dashed green, or in this brain prescription, there would be a brain which is dual to these defects. And now as we increase this boost parameter, what happens now is that the defect goes on some accelerated trajectory. From the bulk point of view, what happens here, I'm showing the tau equals to 0 slice, so that would roughly be here, right? The region where my BCFT lives, here it gets smaller, but also the brain moves away from my asymptotic boundary. So the left diagram is basically an unwrapped cylinder. So I have a two-dimensional cylinder, which is the boundary description of my BCFT. And here where it says BCFT, this is, well, the geometry on which my BCFT lives. The dashed lines are the boundaries of my BCFT. And then if I dualize those boundaries, I get a brain. Okay, and so if I increase this thing to infinity, what I then get is a boundary conformal P theory with a boundary which is now piecewise null. And this here really, I mean, it's not there anymore. It's a point. Good. But so in principle, you know, this is some nice class of solutions, but the point is they're not very useful in this brain picture, simply because the brain moves away from the asymptotic boundary. And so these curvature corrections become large, and this interpretation of some cutoff CFT coupled to essentially Einstein gravity breaks down. Okay, so now the main observation is that one can combine those two things. So yeah, exactly. So what I'm doing is I'm constructing new solutions by just basically boosting my brain configuration in embedding space. And so this is just a family of solutions you can construct. And I'm just basically like going now, so it's a one parameter family, and I'm going through this one parameter family of solutions. So from the bulk point of view, these are solutions to my to the equations, like Einstein's equations plus the equation which controls where the brain sits. So k mu nu equals to basically th mu nu.
So this is like some constraint on some constraint equation on the brain.
Yeah, so there's an equation of motion for the brain, and all those solutions will solve that equation.
Okay.
From the boundary point of view, it's sort of like a family of Lorentzian BCFTs. Okay. Good. So right. So it turns out that if you now do both things at the same time, so one sending t to t critical, you know, which before gave you this problem of divergent wave functions, et cetera, and at the same time also taking this boost parameter to infinity in some sort of like well-coordinated way, as shown here, then what happens is you can fix a point on the brain. So for example, this point here. And so you see what happens now is that the brain, here again, the tau equals to 0 slices, cut off the Poincare patch. But and where exactly this brain here sits, how close this sits to the boundary, is determined by some constant t0 you can choose. Okay. Good. So how does this look like now from the boundary point of view, instead of like a scaling limit where you scale the defect entropy and some Tove coupling to infinity? What you do in addition, you have this boost parameter, and you boost the boundary of your BCFT to infinity. Well, there's a couple of things to say about how points move along here, but let me skip over this. The upshot is that now on the brain, what you get is some flat metric times some prefactor, and this prefactor can be reabsorbed into the definition of your coordinates, and this will make your higher derivative correction small. And so effectively now what you have is you have a CFT living on a flat brain, which with some CFT coupled to gravity, coupled to Einstein gravity to a good approximation, and CFT excitations can enter through scri minus and leave through scri plus. Good. So how does the geometry look like? I've tried to draw this here a bit. So this is again global ADS, and my defect, you know, runs piecewise now here, and this is the brain. So you could imagine like gluing this here into this cutout shape. Okay, and then you can like compute all sorts of things. You can, you know, relate exactly points on U to points in your BCFT. Good, but so I mean, two nice things about this is that, well, first of all, null infinity is completely resolved, so we don't need to, you know, write right? Sort of like some corrections to tau equals to pi over 2 plus u over L, but we just have access to a square naught plus. Now I've solved this problem of asking, well, what should my boundary conditions be? Instead, now matter excitations, which are just CFT excitations, they can leave or enter the brain through scry. And so in particular, I can ask questions about, well, what's the entanglement entropy of modes which have left through, say, scry plus with the rest of my geometry? Good. And then you can ask some more questions, right? So for example, you should be able to get the symmetry algebra of flat space from this. And again, this is done by Inunu-Wigner transformations, except that here it comes out very naturally. So what you can look at the unbroken SO1, 2 algebra and see how this transforms under those boosts. And you see that it, turns into like a sum of two generators, and the one generator has a large prefactor, the other one a small one. And so we want to keep this generator here. So we strip off this prefactor and call this combination P, and the generator which doesn't transform on the boost M. And so the resulting commutation relations for any boost are this. And now if I send eta to infinity, this here becomes 0. And so the whole algebra becomes that of ISO 1, 1 in the strict limit. Good. Yes? Sorry, this is for two-dimensional flat. This is for two-dimensional flat space. So this is, I mean, the time and space translation is the piece here. This is just the piece here. Like, P1 and P0 are time translations and space translations, and M are boosts. Okay. Good. So let me just skip over this slide a bit, but essentially what this says is, what's also nice here is if you prepare some scattering state in the bath, then you can show that as it enters onto the brain, it will, so if you prepare it with finite energy, it will retain finite energy. And so there's a very simple explanation why in the usual flat space limit of ADS-CFT, we saw some infinite energy on the defect, and that's simply because the defect is relatively boosted by an infinite amount to excitations which try to enter the brain. Okay, good. And so let me come to the last part of the talk, and that is so like give a very brief overview of what you can do with entanglement entropy here, or some simple example. Now, you can consider regions in your BCFT here called A in all those pictures, and you can compute the same quantity in 3 different ways, one for each of those pictures. So in the boundary picture and in BCFT picture, you might be interested in the von Neumann entropy of A. In the bulk picture, that translates into the usual RT formula, now with some modified homology constraint, where your RT surface is allowed to end on the brain. And in the brain picture, this turns into what's been known now as the quantum extremal island formula. It takes a bit of a more complicated form. So the rule is, if you want to know what is the entropy of A, what you have to do is you have to compute the von Neumann entropy of the region A, or the state reduced on the region A, union some piece I on this gravitational region. You pay some penalty, the area of the boundary of I divided by 4G Newton, and then you extremize this with respect to choices of I, and then you might get several extrema, and the smallest one gives you the right formula. So then those 3 numbers all should agree. Good. And so in particular, this will also tell you something about the entanglement wedge. Good. And so at the very, very basic level, one can ask one of 2 questions. Namely, we can ask, well, what is the entropy of like the full system? And so, of course, the answer is 0 in a pure state. Or we can ask, well, what's the entanglement entropy between the bath and the defect? So this now is in the ADS CFT picture. And for those who followed the literature, right, they will know that the right-hand side here is basically the question you're asking if you want to see a page curve of evaporating black holes in ADS coupled to a bath. Good. And so the nice thing then is, if I ask these questions now here in the brain picture, I can do a holographic computation in the bulk. That's the nice thing about these doubly holographic models, which give me an answer. Okay, and so now if I take the flat limit without any proof, right, then I can ask, well, what does this question translate to? And the question of what is the entropy of my full system translates to a question which asks, well, what is the entropy of my defect union, like the section of my bath? And then, of course, I can use unitarity of time translation to turn this question into this question, which says, well, what's the entanglement entropy of a subsystem which starts at scry plus minus here and goes all the way up to some cut on scry plus? Well, and as argued, this entropy is simply 0. Now, instead, if you're more interested in the entanglement entropy between modes which have left flat space versus the remaining spacetime, then this here would be the question you want to ask, and this is the entanglement entropy of some subsystem which is defined on scry plus at a particular cut. Okay, so the first answer is 0, and this in fact is something which nicely rhymes with something that Surat Raju has been saying for years, that if you have access to a neighborhood of scry plus minus all the way up to some point, then there's no page curve entropy 0, and that's exactly what you find here. Now it turns out that this computation can, through a few steps, be reduced to a computation which was done by Cassini, Huerta, and Myers, and that's the entanglement entropy of a polar cap region on a sphere. And the reason, roughly speaking, is that what your defect traces out, well, your defect goes along a null line on the cylinder, and so it's like a little cap region which grows in size or shrinks in size. Now if you do the holographic computation, you'll see there are no RT surfaces in the appropriate limit that connect to the brane, and so it's really only the computation of some polar cap region on a sphere. And so you can translate this to retarded coordinates, and you'll get, for example, here, the leading order divergence, which increases initially and then goes back down to 0. Okay, good. Yeah, so, and then of course, one question you might want to ask is, well, people have done this for black holes, so can we take some limit where we start with some ADS black holes coupled to a bath at the same temperature? And so in that case, right, here's an ADS black hole coupled to some bath at the temperature. If you do the computation, you find this page curve here, which flattens out. And what you do is you start with topological black holes and the bulk. And of course, what you can now do is you can take the flight limit. Good. And so how this looks like, right, is you start in this configuration where here's your BCFT, so your bath region, here's your brane in the middle. And as you now boost, what happens is that you end up here. So your bath region now turns into this region past scry plus. And there's two effects now at play. So one effect is that as you increase your tension, the page time gets delayed. But on the other hand, as you boost, it turns out that points here, so say the page time were to happen here, as you boost, those points get mapped to I0, or gets pushed towards I0. So there's like a competing effects, right? Increasing tension delays your page time, boosting advances your page time, and then you can study, well, which of those effects actually wins. And it turns out that unless D is equal to 2, the page time still diverges. And so, well, you don't get a nice page curve, but this is really is consistent, since if we start in these topological black holes and we take the flight limit, we just end up in Rindler space. Rindler space doesn't radiate, so that's fine. Now for D equals to 2, you can arrange things such that the page time remains finite, even in the strict flight limit. Now it turns out in the strict limit, you won't find RT surfaces. So if you go a bit away from the strict limit, you will find RT surface, and you'll also can describe now the theory of the brane as some gravitational theory, some interesting gravitational theory, namely JT gravity on the flat. Yeah, I'm done now. Okay, good. Yeah, so then, good. I think I'm good in timing, so let me just add some final comments. So there's a new way, I hope I convinced you to look at this flat limit of ADS. It only applies to a bulk theory with conformal matter coupled to gravity. But that makes it nice, and this is sort of like also future plans to study in detail the entanglement entropy, for example, of modes which have left scry to the rest of the spacetime. And also, it seems to be useful to carry over some well-established tools from ADS CFT to flat space. Right, and then in terms of next step, so there's, of course, more work necessary for these entanglement entropies. One thing I would like to point out is this paper, which appeared about like a month or so after the paper I was talking about, appeared by the group of Takiyanagi, and they, in essentially a similar model and a variance of this model, they studied some entanglement entropy
Another thing which I think this here illustrates is that, well, maybe studying null defects in holographic QFTs, CFTs is interesting or is useful in order to understand flat holography. And there's surprisingly little work on this question somehow in the literature. Yeah, and then of course, it would be nice to relate this somehow to Carolean and celestial CFT. Okay, thanks.
So is there a way to get the, like, let's say you start with the Virasoro generators in this context, and then taking the flat limit, would you be able to get the infinite dimensional extension of the Carolean algebra, for instance?
Right. So, I mean, yeah. So here I've only discussed the global part. Now the question is, how do you get the Virasoro generators in, right? Because what you would want to do is you want to start with, let's say, like a 3D CFT with a 2D boundary. But then when you couple like a 2D CFT to the boundary of a 3D CFT, then generally speaking, you won't have the full Virasoro symmetry because it's going to be broken by this coupling. So yeah, the short answer is that would be nice, but I don't know.
Yeah, if I may, I have some sort of answer to what he is asking in a sense. So in a paper from earlier in the year, we and I mean some more people in the audience, Priyadarshini as well. We did a boundary CCFT. I mean Carolean meter that was in D equal to 2. Smells very, very like what you might get here. So,
right.
So we sort of identified half the modes, and so it should be so, and we also in a sense, if you started off with a boundary CFT, and if you took the limit, you landed up in this this algebra. It looks a little funny,
right? So let me just understand. Yeah. So what you did a boundary CCFT. This is like a CCFT with a boundary.
Yes.
Yeah. Okay.
Yeah.
Yeah.
So you sort of introduce. So you have null selector. You introduce two defects at sigma equal to 0 and sigma equal to pi, and then you sort of keep half the modes basically.
Yeah. This is slightly different, right? Because here the BCFT itself is just your standard BCFT. It's just that the boundary is null.
Yeah.
And so there, there you would have to hope that in this limit you have like a new emergent symmetry if you really wanted to keep the full.
I guess there should be some way to link this up. It's not maybe exactly the same setup, but yeah, just
yeah, no.
I have a small question. So these large L, so you did not talk about the internal space. So the internal space is also sort of expanding, right? I mean, when
yeah, good. So I've just swept this on the rug completely, right? So you mean the compact?
Yeah, the compact space is also growing.
Yeah, no, exactly. Like so, I've swept this completely under the rug, right? So these theories, they're somehow models of BCFTs, but very crude models, right? If you build some top-down construction, then typically how these geometries look, well, what you think is that these end-of-the-world branes, they model regions of a boundary CFT where some, say you're like an n equals to 4, right? And the S5, you write as some S2 and some other S2, and they're fibred over some like Riemann surface, and they pinch off near like the duals to the defects, right? And so you would think you're somewhat close to this region. Now, whether it's possible to keep, how good of an approximation that is unclear.
Mm-hmm.
And whether you can arrange things like, provided it's a good approximation, to sort of like keep one or both of the S2s shrinking in this location. Yeah, I don't know, but it's this is so like that's a totally valid criticism for all of those bottom-up models, right?
Yeah.
And
Okay, thanks. Yeah.
Hello. Yeah. Okay. So when you say 5 minutes, it's 55 or 55 minutes.
Now we have Ramesh who will tell us about things from diagrams.
Okay, thanks very much, Apratim, and thank you to all the organizers for bringing us back to Bhubaneswar. As I think some of the senior people mentioned, for us oldies, I think Bhubaneswar, Puri have a very strong emotional sort of connect to for the string community. So it's great to be back, and thanks for all the effort that it took, especially coordinating between IIT and NISER. So I thought I'll not inflict a heavy talk in the afternoon, and rather just show some pictures. So it's a scrapbook of pictures. The scrapbook was actually assembled by my great collaborators. Unfortunately, the names can't be really read. I see in this thing there's Rishabh, who is here, my student. He's not yet looking for a job, but he will next year. So, but anyway, you can keep him in mind. So there's Shota Komatsu, Edward Mazenk, with whom I've been having a very long and fruitful collaboration, and Deb Malya Sarkar, who was a visiting student at that time and now working with Jaffaris. It's also that I will mention probably, but not very much, go into some work to appear with Alessandro Giacchetto, Edward Mazenk, and my former student Pranabesh Moiti, and some other work which is still in progress with Matthias Gabardil, Wei Li, and Edward Mazenk. So anyway, so this is, I think several of you have heard me talk about my obsession for several years about sort of going explicitly from quantum field theories to string theories in the context of starting from free field theory or perturbative field theory and reconstructing string theory. So, so this is in that context, but it will be for a very specific case, a very simple case, a matrix model. Sort of zero-dimensional field theory in that sense, and where I think a lot of things can be made very explicit. But the reason to, so you might think it's a very simple, very toy model, but I think it has a number of features. I think one is that it is very explicit. Second, that it is, it gives you an idea, I think, of more general lessons of how this might work. And thirdly, it's also a sector within something interesting like n equals to 4 Yang-Mills theory. And through that, I think it might give you a handle on the more general case. So that's the thing. So I have the first few pictures are the pictures to take away in some sense. So one big picture I'd like to convey in the talk is that you start with some Feynman diagram like this. There's a very, at least in this particular case, an explicit way in which you can actually do two things. One is reconstruct a closed string worldsheet associated to each Feynman diagram in a certain unique way, and you can also reconstruct the target space that the string theory will be seeing. And so in that sense, it's a way to sort of go from the Feynman diagram to a worldsheet with a map to the target space. And the Feynman diagrams, one message is that they know a lot about the dual closed strings. What these theories are and so on, I'll try to flesh out, but this is the big picture. So yeah, so this is the statement a little more in detail of this very simple gate string duality. It's a two matrix model, if you wish, two n by n matrices, K and M, with basically a quadratic action. but you consider arbitrary correlators of matrices, so products of traces, multiple of them. So in fact, you can view these as the generating function of a two-matrix model with perturbed by a polynomial in K and a polynomial in M. So in some sense, it's you're looking at the perturbed two-matrix model of that kind, and hence looking at the correlators, a generating function of correlators like this. So there are two things what we'll sort of do here. We'll start with this and the Feynman diagrams associated with this theory and reconstruct, like I said, the world sheet and the space-time. So the world sheet in this case will be, for this particular case, will be Feynman diagrams that correspond to very special points on the moduli space of Riemann surfaces. So associated to, in the conventional 't Hooft way, to correlators of genus G, an endpoint function of such correlators will be a certain set of points, special points, which I'll describe later. There are some sense lattice points or arithmetic points of this moduli space. So that's one, that's the aspect of reconstructing the world sheet. There'll be the space-time target space, which will be that these Feynman diagrams, the Feynman diagrams here will be essentially doing a very simple count, because as you see, there's no space dependence. We've stripped things down to a very minimal set of information, and these will be counting some special holomorphic maps to P1, which is of the two-sphere. And these are a special set of maps which go by the name in the mathematical literature as Belly maps. They're basically branched over 3 points. So if I denote P1 by this line here and the world sheet by some kind of a covering space of that line, there are only 3 branch points, and that's what these intersections are kind of denoting, the places where the covering space is branched over the base space. So the world sheet, this is the world sheet and this is the target space, and there are exactly 3 points. And so that's the sense in which we'll, what I said in the previous slide of going from the gauge theory to the both the world sheet and the target space will be realized. So it's a proposal at that stage, but the interesting thing is that one can really talk about this dual string theory that for which one is reconstructing this target space. One can think about this as an independently defined topological string theory, which is on a coset, an SL2R mod U1. It's essentially a cigar-like geometry, and which is closely related to this sphere. And the claim is, which is something I won't go into that in detail over here. I'll more stick to this aspect of it, but we are close to showing in this work with Gabardiel, Whaley, and Mazeng that this A-model theory exhibits these same features, namely that it counts these holomorphic maps, it has support only on these special points, etc. There are certain correlators in this topological string which correspond to the correlators of this matrix model. There's also a B-model version of this, which is the one that will appear in the other paper, which is in terms of Landau-Ginzburg topological field theory. These are all related also to the C=1 theory at self-dual radius in different ways, but I won't go into those aspects of it. But the only reason to mention it is that this proposal is supported by independent evidence from sort of a world sheet, traditional world sheet methods, traditional constructions of relatively familiar string backgrounds. So that's the one slide summary of the talk.
Was there a reason you didn't have mixed insertion?
Yeah, so in this thing, yeah, those would be then, I think, very, this is a subsector. So I think this is in some sense, that would be much more stringy. As you know, a two matrix model, you can have arbitrary words, and then you would get a much, it's probably, this is sitting probably as a subsector of that, but at the moment we can say things only about this. So this is a topological subsector perhaps of a bigger dual which has a much more stringy set of states. But this is all we can say at this stage.
Is there any element of holography, the bulk boundary?
It's in some sense, yes. So you can think of these as in some sense actually inserted at the end of the cigar, at the tip of, not the tip, the infinity of the cigar. And there is a sort of a one complex dimension that grows out of it, which is the cigar, the radial direction. So yeah, there is a kind of a crude version of holography, I guess, in this.
But two additional dimensions.
One complex dimension in some sense. But you can, it's a bit difficult to really identify the dimension at some level, because even in the cigar there's a circle at infinity. Okay. In a physical string theory you would really think of these as vertex operators inserted on the boundary of that cigar, but in the topological theory effectively they are squished. Yeah.
Okay. Thank you.
Yeah. I mean, they're all algebraic curves. No, I meant arithmetic curves. There are equations which I didn't mention that, but yeah, the equations would be over algebraic numbers.
And why only algebraic? Why not any number field?
That's what this is. This theorem is about that. I mean, we didn't put it in. This is what is the statement that comes out. So I can't say why something else didn't come out, but this is what comes out.
And what are the degrees of the Belly maps that you get? Are they?
They are related to the total number. So if the degree of so you just sum up all these this sum over LIs or the sum over NIs. That basically is the degree. So in this case, degree 4 cover. Yeah, so I mentioned that these are also some kind of special set of operators. You can view them as correlators of some giant gravitons, some determinant-like operators, a special set of correlators which preserve half the supersymmetry, and which is why you can reduce it down to a matrix integral. And effectively get this sort of determinant insertions where you have simply these single traces of K and M. And that's another reason why, I mean, that's the protected kind of a subsector that you're say more generally you would have had things that would have mixed K and M, but that would also not preserve the supersymmetry. So it's sitting inside this n equals to 4 Yang-Mills. It's a very small but I think interesting subsector. So these K matrices and M matrices you can view as some kind of essentially built out of fields of the super Yang-Mills, the n equals to 4 super Yang-Mills, if you want to keep that in mind. But I won't say anything more about this. Well, yeah, exactly. Yeah, you can show that they are, because they're preserved, they don't depend on the Yang-Mills coupling, and so just the free theory. So there is something else which I probably won't have time to this thing, but maybe on another occasion I'll. But there's actually in this case an instantiation of something I have called an open-closed open triality, which is the existence of two different open string theory descriptions for a single closed string background. One will be this, which we'll be talking about mainly, but there is actually in this case you can see this is yet another case, and by now I think there are a handful of cases which show this sort of dual vertex type versus F-type open-closed string duality. But in some sense, that's really a subject for another talk, and I don't think I'll get to it, but I just want to say it out there. So, so as I said, I'll show pictures. So the first set of pictures I want to show is about how to build Riemann surfaces, very much like in a Lego fashion, like from basic building blocks. And it's something some of you have heard me say talk before, but I think I'll try to illustrate it with these pictures, which will show you that this construction is a very pretty mathematical construction that seems to be tailor-made for gauge string duality. So the key object is something you define on a Riemann surface with genus G with n punctures. It's a quadratic differential, so it's essentially and it's meromorphic. It can have poles, but otherwise it depends only on z. And so locally it will look like phi of z dz square. So I'll spell out what is special about this differential. So one of its important properties is that it has only double poles, and the double poles are at the n marked points of this Riemann surface. So supposing I tell you in some local coordinates the positions of these marked points, the phi in those coordinates, in those local coordinates, will have double poles of this kind. And a double pole is a coordinate independent object for a quadratic differential, just like a single pole is a invariant under a local change of coordinates. For a single differential, for a quadratic differential, the double pole is what is the invariant object. And so it's just like the more familiar single differential, which we all use in Cauchy's theorem and so on, where you have the notion of a residue as multiplying the coefficient of the pole. Here also you have a residue, and this object, or rather the square root of this coefficient at this pole. So in some local coordinates it will look like du square by u square, and this coefficient, or rather with a minus sign, etc., so that essentially you want 2 pi I times that is the residue. So this is what we'll call the residues, and these will be real numbers, and they will have an important significance. So I have this is one property of this differential. The second thing you need to know about a quadratic differential is that you can define a set of trajectories on the Riemann surface which are called horizontal trajectories, which are, and I think this is a very nice electrostatic picture behind it, because it's essentially the set of trajectories z of t, so t is some real parameter parameterizing the trajectory, such that phi dz by dt the whole square is positive. So in general, of course, this would have this is a complex, these are all complex, so stating that it's positive is basically choosing a particular sort of at any point it's choosing a particular direction where this would be true. And the simplest case, and that's where the name comes from, is if you just looked at the complex plane and you looked at the simplest differential dz square, and you ask when is dz by dt the whole square positive, it's for the lines which are horizontal parallel to the x-axis. So that's why they're called horizontal. So locally, that's why these are kind of parallel to each other, horizontal. But near one of these double poles, if I go to some local coordinate like this, in terms of theta and a radius, then this just becomes d theta square. And then these are just actually concentric circles. So this is positive when theta, along the trajectory where theta varies and r is constant. So, so there are concentric closed curves around each such point. So you can think of these as some kind of isotherms or whatever, electrostatic equipotentials, if you wish. If you place some charges over here, then these are like equipotentials that are created around this. So you have these equipotential lines or isotherms or whatever, however you want to think about it, around each of them. So you can see these concentric circles. There'll be at each point there will be, so you can foliate the whole surface by these trajectories, and around each pole there will be these, and they'll keep expanding, and you can compute them. You can put it on it's a fun thing to play around. So the special thing about quadratic the Strebel differentials is that these horizontal trajectories really close. They form closed curves. In general, if I just had a generic quadratic differential, the behavior of trajectories is quite chaotic and it's quite strange. But the interesting thing about Strebel differential is that most of the trajectories are just closed isotherms like this. Yes, Abhijit. Yeah, this is locally. So it's locally, you can always change coordinates so that it looks like dz square as long as you're not at a pole or a zero. If you're at a pole or zero, other things happen. But as long as you're not at a pole or zero, you can just make a smooth change of coordinates so that the differential looks like dz square. So locally, they'll be parallel. So if you just zoom in somewhere here, they'll be in a small band, they'll be parallel, but it certainly fails near the poles.
And what is happening over there, where three of these, there would be
yeah,
a junction?
I'm coming to that. So that's precisely the next picture here. But I think I said everything I want to say here. Yeah. So what happens? Yes, indeed. So these things, like if you can imagine, like it sort of emanates from each of these poles, but then they collide at some point, right? I mean, and that's what Abhijit was asking. So what happens when they collide? You get a trajectory, horizontal trajectory, which forms a graph. It doesn't form now a closed loop. It forms a graph. And in fact, these graphs have vertices. And you can see for yourself, it's very easy, small calculation, that these vertices are the places where the Strebel differential has a zero. So when this has a zero, and in fact, if it has a zero, a simple zero, then the vertex here is cubic. And in general, if there's some higher order zero, the valence of the vertex is the order of the 0 plus 2. So if it's, of course, if this is 0, then of course there's no vertex. I mean, there's no vertex, it's a regular point. But the point is that near a 0, the horizontal trajectories have this sort of a structure, like a cubic structure, near a simple 0. So that's what happens. And so for a Strebel differential, what is special is that almost all the trajectories are closed circles, these isotherms, except for set of measure 0, which is where these things collapse, and you form a graph on the surface. I've drawn just a genus 0 surface with 4 punctures, but in general, this is true for a general Riemann surface with n punctures, that you have these, that you have a graph, and this graph is in some sense a double line graph, because it's the graph that you draw on a Riemann surface, and this graph has the property that each of the faces contains a single pole, because each face is what, it grows and grows, and then at some point it collides with another face, and that's where these graphs are kind of sitting there. So there are generic horizontal trajectories like this, and these are what are called critical horizontal trajectories in the literature. They are graphs and not closed curves. They are edges of graphs. Okay, so Strebel has a theorem which, okay, I'll come to it. So you can now think of this, so this picture of this Riemann surface. And by the way, this residue, which was essentially the contour integral around any of these poles, this is, of course, the same regardless of which horizontal trajectory you take, because of the usual Cauchy theorem-like thing that it's just if I take the square root of the differential, it's a regular differential, so square root of phi dz, is a regular thing, and it's gives you this number L, which as I said, we take to be positive and real. And this surface itself you can think of as basically built from the cylinders of this circumference L2. So this is conformal to the following. You think of a cylinder in which these horizontal trajectories are these sort of equally spaced lines, and then you're sort of just gluing them at this graph. Okay, is the picture clear? So you're building this punctured Riemann surface from gluing these half cylinders. So that's the sense of this Lego surface that I was. So you start with just punctured half cylinders, half because it's going off to infinity this way. This is pole is at infinity. So you have these half cylinders, they come and meet at this edges of this graph. And each cylinder has a specified circumference, which is specified by the residue at that pole, by this number Lk. In some sense, there are some similarities to light cone gauge, etc., but it's slightly, yeah, that's slightly away. I've tried to draw it as a double line graph, just to emphasize the fact that it's a graph that you draw on a Riemann surface, because if I don't draw a double line graph, the genus is not, you cannot assign an unambiguous genus to a graph unless you sort of specify the orientation, unless you kind of thicken it and form a ribbon graph. So that's the only reason to thicken it. But indeed, it's really just a line. Yeah, on the Riemann surface, it's just a line. I mean, that is, yeah, if you specify a clockwise orientation, then you can see, yeah, it will turn out to be opposite, exactly. Yeah.
Or you have to
You can okay.
I mean, what is the order of the how do you define?
Okay, let me first state this theorem of Strebel, which is the main result which we'll be using. So right now I just told you that there are certain differentials, these Strebel differentials, which have this property that they have double poles at these mark points with some specified residue. So and that their horizontal trajectories have this this thing that they give rise to some graph. That's all I told you. So now what Strebel showed many years ago is that you can define these edge lengths with respect to the square root phi. So you have edge lengths for each of these edges of these graphs. So you basically go from each. I told you that these vertices are these zeros, ZA, ZB are two zeros, two adjacent zeros, let's say. And you take this edge length will be just this integral along the sum integral along this horizontal trajectory. It's a real number because the definition of a horizontal trajectory, I should have said that the square root is positive. You take this positive square root, and therefore it's a real number, and you integrate it along that trajectory, you'll get a real number, and you've taken it to be positive. So this is a positive real number. So you have associated to each of the edges of this Strebel graph and a length, a real positive length. And now these lengths are not all independent because the perimeters of this the edges of this graph are fixed by the residue. So the perimeters are these L's, the capital L's, which I gave as my input data of my Strebel differential, the residues, some real numbers. So the sum of, let's say, this edge plus this edge length must be equal to this L1, let's say, over here. And sum of this edge plus this edge plus this edge plus this edge must be L3 or whatever that one was. So there are some constraints. So the edge lengths are not all independent, but it's at least by counting, you can convince yourself that there are as many edge lengths as yeah, exactly. If you do the sum, then you get this full contour residue, which is just the sum of that, sum of this edge plus this edge will be this one, L2 or whatever it is. Yeah.
Rajesh, do you want your moduli space to be compact?
No, I'm not yet looking at, I haven't told you anything about the moduli space. I'm just going to, but it will not be the compactified moduli space. It is so there's some technicalities about how to go to the compactification, which I will not go into. But the theorem, the very nice theorem proved by Strebel, is that there is a parametrization of the moduli space of Riemann surfaces of genus G and n punctures together with the data of the parameters, so that's some r plus to the n, which are given precisely by these edge lengths. So these, if I just tell you the lengths of the graphs, lengths of the edges of the graph, that gives you a Riemann surface in a one-to-one unique way, provided I specify the parameters. Okay, so 30 minutes. Okay, so in other words, another way to state it is that if I give you a Riemann surface with at some point in the moduli space, I specify, let's say, these numbers Lk. I can give you a unique Strebel differential, a unique quadratic differential on that Riemann surface. And that quadratic differential, its lengths, these particular lengths that you construct or compute from that quadratic differential, these lengths will essentially parameterize the moduli space. So I can view it the other way around, that if I give you a graph and these edge lengths subject to maybe some parameter condition, I have a unique complex Riemann surface, a unique point in this moduli space. So that's the meaning of this equivalent, this Strebel's theorem, or this equivalence between, so you give me a graph, I'll give you give me a graph with these edge lengths, I'll construct for you a Riemann surface. Basically, it will be the Riemann surface whose unique quadratic differential will have these as the Strebel lengths. Or vice versa, you give me a Riemann surface, I'll construct for you Strebel differential, a unique Strebel differential, which will have these edge lengths, which I can specify. But the interesting thing is that the graphs will have all the possible topologies that the Strebel graph, I drew one topology. I could have had another for another point on the moduli space of 4-punctured sphere, I can have a graph with a different topology, for instance, in which these S channel becomes T channel, for instance. So I have to, if I have to cover the moduli space, or I have to sum over all those different graph topologies, exactly like what we do when we sum over the Feynman diagrams. So so that's the mathematical theorem. Okay, so and this was famously exploited by Kontsevich in his proof of the Witten conjecture, this particular parameterization of the moduli space. But yeah, so yeah, this is basically elaborating on that statement that if I have a genus G Riemann surface with some n marked points, then and I give you the r plus to the n, the parameters, then basically these edge lengths are coordinates on this moduli space. N is the number of marked points, which translates into the number of faces of this graph. So this is a dictionary between the graph data and the Riemann surface data. So you have a graph which has the usual v minus e plus f is 2 minus 2g, that corresponds to a genus G Riemann surface. It has n faces, that corresponds to the n marked points here. It has some edge lengths from the Strebel differential, those give you some coordinates. and the perimeters that are fixed are just essentially the r plus to the n piece. So each graph gives you some point on the moduli space, and as you, let's say, vary these edge lengths but keep the topology the same, you'll cover some part of the moduli space or some top dimensional cell of the moduli space. Now, some of these lengths can go to 0, in which case you can have something like this. You can have a quartic vertex. That's sort of a boundary between two cells. And then you expand in the opposite direction. Then you go to a different cell. And then you keep doing this and you cover the moduli space. So as you change the graph topology and the edge lengths, you cover the whole moduli space. It's a very non-trivial theorem. But so basically each topology of the ribbon graph plus all the possible edge lengths parameterize one cell, and then different topologies allow you to cover the whole moduli space. Okay, and there are you were asking earlier about explicit this thing. It's very hard to write down explicit formulas for even 4-point function this thing, but in special cases you can, and you can see all this very clearly, and numerically people also construct these treble differentials, etc. Yeah, it has something, I think, to do with the stress tensor. In the ADS3 CFT2 case, it is closely related to the world sheet stress tensor. Yeah, so exactly, it transforms. In some large C limit, I think it is the case, but it's some okay, large C of the, we'll talk about it later. Yeah.
So
different topologies like this. So I change the topology, meaning I let this edge length go to 0, like here, and then I sort of, so think of edge length non-zero being somewhere in this blue region. As the edge length goes to 0, I go to this dashed line. And then as I then change the topology to this, I go to the red region.
Is this a theorem or?
This is the Strebel theorem.
This is Strebel, okay.
Okay, so this was purely mathematical at some level, but I think it's very pretty maths and very significant for us, yeah. R plus is basically this because positive real number. So these lengths, these perimeters or the residues, those you specify. No, it is not. Yeah, it's not. So you give a Strebel differential with specified real numbers, real positive numbers, LK. There's a unique Strebel differential on that particular point in the moduli space. You will be overcounting, right? Because, okay, you have to keep this perimeter fixed. As long as you keep it fixed, it's okay. So basically, if you just count the number of edges, you'll get 6G minus 6 plus 3N. Whereas the moduli space dimension is 6G minus 6 plus 2N. So if I were to specify, keep edge lengths such that the sum is fixed, then that's okay. Yeah, you're essentially picked a point on R plus to the N, and then you're parameterizing the moduli space as you vary, subject to those constraints. No, it's just a direct product. Yeah, so that's why individually each of these are not really this thing. It's the whole thing that then factors. Anyway, so this was all this thing, and you might be tempted to, I mean, okay, I've associated a natural graph with a Riemann surface, and so you might be tempted to think that I'm going to now identify them with the Feynman graphs, but not quite. So again, so now let's go back to our 2-matrix model. And I've just written down a trivial correlator, trace k square, the whole square, just a 4-point function. It has just 4 Wick contractions. There's nothing much to it. But the main point is that if you, in our conventional ADS CFT dictionary, we think of this 4-point function of this matrix model as some 4-point function of a string theory. And so essentially, the vertices of these Feynman graphs are really the insertions of your closed string operators. So we expect the vertices of the Feynman graph to correspond to the punctures on the closed Riemann surface. So a 4-point function on the field theory is a 4-point function of the string theory. N-point function is an N-point function. But that's not quite what we have, right? What I showed you was that the faces of the Streble graph are actually the punctures on the dual Riemann surface. And so in some sense, you have to actually, so the proposal is that you look at the dual graph to the Streble graph. So there's always associated to a ribbon graph, there's a unique dual graph in which the vertices get exchanged with the faces, and the edges are transfers to the dual edges, and the faces, vertices and faces get exchanged. So for the simple graph, I've drawn the dual graph. These are the dual vertices in black, the dual edges in yellow, and the faces, whatever they are. So indeed, but this is actually interesting that there are canonically, in some sense, a graph and its dual associated to a closed string amplitude, and this is related to this picture I just showed at the beginning, but I will not get to talk very much about open-closed open triality, as that there are about 2 different open string descriptions, which I think have very interesting ramifications, which will be a subject of another talk. So in any case, so the proposal here is that you identify the Feynman graphs with the duals to the Streble graph. And that actually also gives a very nice physical picture for how to build up the Riemann surface. So to elaborate on that Lego further, let me draw some more pictures. I mentioned earlier this notion on the Riemann surface of horizontal trajectories. There's something called vertical trajectories, which is just flipping the sign of this inequality. So phi dz squared dt square is less than 0. Again, going back to the C example, complex plane example with just dz square, these are just the vertical lines, and that's why they're called vertical trajectories. So for any quadratic differential, you can associate horizontal trajectories, and you can associate perpendicular or transverse to them vertical trajectories. So just to, as an exercise, if you go back, you remember the horizontal trajectories were these ones which were concentric circles. The radial directions are the vertical trajectories. So you can think of many vertical trajectories emanating from these punctures and then meeting at the poles. So it's again like the potential and the dual potential, if you wish. But again, there is a special set of vertical trajectories which start from a pole and end at a 0. So there are infinitely many vertical trajectories, but then there are these special ones which come and start at that pole and end at the 0. And this, so you can use this to carve up your Riemann surface into triangles, into spherical triangles like this. So like each triangle like this, where one end is one of the edges, the horizontal one, and the other 2 are these, because remember each face has one pole, so I can, from that pole, I can draw these special vertical trajectories. And if I complete it and look at the other side of that edge, that will give you another half triangle. And so basically you're carving the Riemann surface now into infinite strips. And each strip has a width, which is the Streble length that I said earlier, this LAB. So effectively, what you're doing, if you now do the same conformal mapping I showed you earlier, how to draw it, build it up into cylinders. But now I'm saying that each cylinder is built out of strips. And those strips are basically each of these strips. And that indeed is the sort of picture of a string bit picture of a world sheet that you build out of the Toft. So these, remember, I'm associating the Feynman diagrams with the transverse, with the dual graph, and these strips are basically those dual edges. So these strips are the double line graphs of my original Feynman graph, and I have as many strips building up my cylinder as there are edges, or the valency of that face, which is also fits with many things. In particular, it tells you like trace m to the k will actually create a face with k edges. So the vertex associated with trace m to the k in this picture will be the Strebel graph will have a face of valency k, which corresponds to essentially k strips being glued together, which is the picture one has of composite operator building up a closed string world sheet, if you wish. You can think of these as sites of the spin chain in the n equals to 4 Young mills. Yeah.
Just a few minutes ago, you said it has some interesting ramification. So clarification.
Which?
You said something has interesting ramification.
The open triality, I think I was saying.
Do you mean ramification in the belly map sense, or
ramification? No, ramifications just in the pure English sense.
Okay.
that it has many consequences. I think that it's to do with basically the giant graviton picture. It's, as I said, it's a separate talk, but yeah, physics ramifications. It, I think, also has mathematical ramifications, which I will also not talk about. But so these strips can be naturally identified with the ribbon graphs of the large N theory. So this is really the Lego-like picture of the Feynman graphs I wanted to convey, that you can assemble this closed surface with these strips of these length of this width L. So you build up the whole Riemann surface. You can think of someone, you can give like lots of strips of paper to someone, and they can glue up and they can build up the whole moduli space. If I just allow you to vary the different lengths of the strips and the topology of the graph, you can build all the Riemann surfaces. It's a very nice origami-like way of constructing Riemann surfaces. Yeah. Yeah, so in fact, we will associate the same length, because there's the length and the dual length. So this, in fact, as I said, this strip here has width LAB. So now I associate a width with the same Strebel length. I associate as the width of that Feynman graph. The length I think of as infinite in some sense. Yeah, I mean, there are many ways to equivalently think about it, but yeah, you can think of it as the width or the length, either way. You can associate. Yeah, I think it's many ways. It's because the length is in some sense infinite, because these are infinite strips. The width is what is finite. Yeah, because you're going to the pole. So these are semi-infinite strips, but the width is finite. Whereas for the dual graph, it was the length which was the same. I mean, the same number, but one I associate with the length and the other I associated with the width. Yeah. So now, I mean, you can again view this picture of this Feynman diagrams in a very concrete way. As I said, it's like giving a child these strips to glue together, and basically you just have to glue together these Feynman graphs and form this by the prescription that I just gave you. It's a very explicit prescription. You just have to give an algorithm to a child. I think they'll be able to glue this and make a closed surface out of it. So you can so you have to give this length assignment. So these are the pictures. So you think of basically the strip as this strip, this Feynman edge as as this strip, this Feynman edge is this strip, this one is this, and this one is this, and then you're gluing them in some way just with the prescription. So in some sense, you have this is the width of the strip, and these are the semi-infinite strips, and you glue them. So this is again very general, and the proposal originally made was that these should be essentially thought of as the Schwinger proper times, or the inverse Schwinger proper times associated to the Feynman graph. But now we have a matrix model where we actually don't have anything, and in fact, Razamat at that time had sort of simply guessed that for a matrix integral, these L's should, because there are no times, you just should be integers. They are just the number of Wick contractions. That's the natural edges number that you can associate it to a matrix model. These lengths are positive integers. So you just look, so for instance, if I consider some more complicated correlator like this, I have 3 Wick contractions between these two vertices. So I associate a length 3 to this edge. I have 2 Wick contractions here, so I associate a length 2, a length 1, a length 1. So there's just a simple way in which for a matrix integral or for a correlator like this, I associate some Strebel lengths to these edges, and you can see the sum of the 3 plus 2 is 5, which is this trace k to the 5 over here. 3 plus 1 is 4, the trace m to the 4, and so on. 2 plus 1 is 3, trace m cubed, and that's trace k square. So the number of the powers is basically related to the total valency here, which is what I was also remarking earlier. But so anyway, there's so this is the proposal, and now something very nice happens, which is that these, if the lengths are not any real number, but they are actually integers, then there are these special points on the moduli space which correspond to arithmetic Riemann surface, which gives a very nice natural way to lattice or discretize the moduli space. And in fact, people have used the counting of these points as a way to give a discrete volume. If people compute mathematically, people are interested in computing the volumes of moduli space, and this gives a very natural way to discretize, just like you can count the volume of a sphere by just discretizing it and then taking some kind of a continuum limit. You can do the same thing actually over here. So each Feynman diagram corresponds to one point on this moduli space with integer Strebel coordinates. And this fits in very nicely. By the way, again, I want to emphasize that this is a latticization of the moduli space, not of the world sheet. The world sheet is a continuum world sheet, which I've built by gluing these strips. So I think in the old literature on the matrix models, people took this double scaling limit because they wanted to get a sort of, they thought that's how you would get a continuum Riemann surface. That's not necessary. What does happen in the double scale limit is a continuum limit of this discretization of the moduli space. You cover the whole moduli space, but you get a string theory regardless. You get a string theory even when you're away from the double scaling limit. You just have a string theory with this funny property that it gets contributions only from special points on the moduli space. String theory lives on a proper target space. It's a world sheet theory of the kind that you would conventionally define. It's not latticized, nothing. So of course, so right now I'm going at it from the reconstruction point of view, but as I said in the very first slide, independently, this is a topological A model. I think we have by now, I think, good reason to believe it's the A model on SL2R mod U1, the cigar model of this Kazama-Suzuki model for the sequels to 1 that Sunil and Kumran Wafa had studied in the context of the sequels to 1 string theory long ago. So it's basically that A model theory. There's a dual B model description also, which is another, I can tell you that separately. But if you want, what is relevant over here is that it's the A model theory, because it has a target space, which is a cigar, and you're looking at world sheet maps from the world sheet to the cigar, holomorphic maps, because it's a topologically twisted A model. And that's in fact necessary for this localization. The holomorphic maps don't always exist from a world sheet to a target space. So you pick up special points. On this. By the way, this picking up of special points was also a feature in the ADS3 CFT2, where what we found with Lawrence Eberhardt and Matthias Gaberdiel was that in the tensionless limit, you picked up special points. And indeed, in a later paper with Pranabesh and Bob Knighton and Matthias, we showed that in a sort of a large twist limit, in some kind of a Gross-Mendel-like limit for ADS, you get precisely these integer points. So in some sense, I think the integer points are very universal points, and which capture the high energy sort of behavior or in ADS in some way, but in the tensionless limit. So that's why I think it's the matrix models are the simplest case where that feature is captured, but I think it's there in the physical string theories, and we see it specifically in the ADS3 CFT2 case. Okay.
Sorry, question. What is an arithmetic notation?
Yeah, so as I said when you asked earlier, there are surfaces over Q bar. There is a presentation of the Riemann surface where you write it as an algebraic equation with coefficients which are algebraic numbers.
But arithmetic about them is that there's always going to be some k rational points or something, or what's the
this is this thing that mathematicians use. I mean, I think they have many ways of thinking about it as arithmetic, but I think there are some other ways of characterizing it which probably bring that out. But at the moment, I think of it as just some things which the coefficients are algebraic. So it's in some sense special as opposed to a general Riemann surface where it could be any complex number.
I also have one question on what this latticization means. You're free to defer to later. So if you ask me later, I can come find it later. But I don't understand what this latticization actually means. For me, a lattice is a freely generated Z module or OK module.
You can think of this is also an integer, this thing, right? It's the lengths are integers. So I can look at how the moduli, I just look at points with the Strebel lengths being integers, and that is because they're equally spaced, so in some sense a lattice. So yeah, so it's in that sense a discretization, but it's a discretization that mathematicians have also studied, as I said earlier, to compute volumes and so on, because it's sort of uniformly distributed at some level.
But these are integer or integer, right? Like ring of integers or
positive integers, yeah.
Integer like ZZ, not Z of some number field.
No. It's just this thing. Now, I'm not talking about general number field, just integers. No, not necessarily. Okay, in this particular case, yes. In this particular case, because I have two matrix model, I have the same. But no, actually, yeah. So each point has two other things as its neighbors. Yes, in that sense, bipartite. You can color it such that adjacent vertices are of opposite colors. Correct. That's special to the graphs that appear for these correlators. No, a general Strebel graph need not be. So you don't have to get all the Strebel graphs. So you may get, for a given correlator anyway, you get only a finite number of Feynman diagrams, unless you take the size of the operators very large. There are only a finite number of Feynman diagrams, and so you get a discrete set of points, a finite discrete set of points on the moduli space. So in any case, you're not spanning all the possible graphs or all the possible yeah, for each ln n, you get a class of bipartite graphs, I mean a subclass with the LNC specified by these L's and N's, yeah. But it's a finite set of graphs which happen to have this bipartite property. What makes this very compelling is that just purely again from the point of view of the reconstruction from this, that I told you about this mathematical theorem, I told you about a proposal to associate the Feynman graphs to this thing, to the Riemann surfaces. And what's very nice is that it fits in very well with what the correlator is computing. So there is the correlator itself as Feynman diagrams, which gives you a certain, tells you what kind of points on the moduli space you have, but what is the weight that you associate with that correlator. And the interesting thing is that this is a sum over what these correlators are counting are basically sum over various holomorphic coverings of a P1 by the world sheet associated with this correlator over exactly 3 points. And this is this is the world sheet. I have this is the one that I build out of the Feynman diagram. So I haven't drawn the edges of the Feynman diagram, but these are the K vertices, and the other ones are the M vertices, and these are the dual vertices. So those are the same points that I had earlier, but the point, now we are talking about a map from that world sheet, a holomorphic map to a P1, such that so branched over 3 points on the target P1, such that the K vertices correspond to one of these points. I think, yeah, if you, and this cross vertices correspond to W1, it should have been W1, and this vertices correspond to W2. The inverse images of W2 are these three, and the inverse image of the third point is the dual vertex. And so the claim is that basically these correlators are counting exactly the number of such holomorphic maps, and these are admitted. And this is another theorem of the Belly, that these branch covers of P1 are admitted only by arithmetic surfaces. So there are such holomorphic maps only if the Riemann surface is one of these points. So that's why this string theory has support only over these points. As if you have a topological string theory which is localized onto holomorphic maps, these holomorphic maps exist only for these particular integer points on the moduli space. Yeah, that's one way to no, okay, understand what? Yeah. Yes. That's right. I mean, you'll have a triangle built out of these three different vertices. These two, this thing, and so the inverse image, you can triangulate this Riemann surface, and then you get this. Yeah, but the point is that at the level of a picture, that's correct. But at the level of a Riemann surface, such a triangulation or such a holomorphic map exists only if this world sheet is arithmetic. So it's again a very non-trivial theorem. I mean, it's actually not a very difficult theorem, but it's quite a non-trivial theorem in its implication. And you can actually see this target space from the matrix model itself. And I think, but I don't have probably time to explain it in detail. But basically, the combinatorics of Wick contractions is nothing other than counting these curves, because the combinatorics of Wick contractions is basically a way of counting permutations, and counting permutations is another way of thinking of branched covers, because a branch cover is basically sort of a permutation of the sheets of the Riemann surface about a point. And so So basically, there is a cycle structure that is associated with each of these correlators, each of these insertions of these operators. And so those correspond to the two branch points, the K and M ones. And then there is a dual one, which is associated to the face, which is the dual vertex. And that basically depends on the specific Wick contraction. So for a given Wick contraction, you will have one cycle structure that contributes. And so that's what I tried to pictorially draw over here. There are it's like trace k square, trace whole square, trace m square, the whole square. You would have some kind of a cycle structure, a permutation like this. So basically, this Wick contractions are computing these belly maps. And as I said, the topological string with this target space P1, or more precisely this SL2R mod U1 target space, is what would reproduce this, which we are here proposing from this reconstruction point of view. Yeah, that's the non-trivial part, which we are currently, I mean, okay, I can tell you later, but basically you'll see the it has to do with the same kind of things that worked in the symmetric orbifold. So in the symmetric orbifold, you had these operators of different twists, and they corresponded to the branching, and you had so all of these sort of branch points coalesce into one, all of these coalesce into another, and in some sense the dual vertex gives you the another. So each of these, they correspond to different spectrally flowed sectors in the worldsheet theory, and each the spectrally flowed sectors correspond to a branching of a specific kind. But I think, yeah, I don't have time for this open-closed, open triality, which I think would take me further apart. So what I wanted to show with these pictures is that these pictures have a very precise realization in these matrix models and their topological string duals, but I think are more broadly applicable. And this treble gauge, this mathematics of the treble differential, I think not only gives you this very nice way to parameterize moduli space, I think it's something very physical because it's a particular gauge choice. So what I think one is seeing here is that there's a worldsheet gauge choice. There's a locally flat metric you can choose given a treble differential, which has curvature singularities only at the zeros and poles. And I think it gives you the string theory in this treble gauge. It's not a gauge we normally use, but I think in some sense quantizing the worldsheet theory in this gauge is what naturally would give you this. It's a version of a sort of a light cone gauge like description in which I think these features become manifest, which are probably obscured if you look at it in a more covariant way, but this is in some sense a physical gauge like light cone gauge. And yeah, as I said before, that some of these elements are also in limits of the ADS3 CFT2, and there's some interesting statement I think about this arithmetic localization also, because another way to say what these correlators are, which the B model theory actually describes, is that they compute some kind of generalized intersection numbers, generalizations of what Kontsevich studied or what Witten had conjectured, which give rise to the standard sort of intersection numbers. But this seems to be a rather interesting localization to arithmetic points on the moduli space, which I think indicates some interesting role for these arithmetic in this tensionless limit, which I don't fully understand. But okay, thanks very much, and sorry for going over time.
Thank you, Rajesh. I have two quick questions. One is you partly answered. You said that these points are uniformly distributed in the moduli space.
Yeah, in fact, that was a result some years ago. Some people showed, yeah.
When for the stub part, which is the length of the semi-infinite cylinder, it's easy to understand. But the interior, I thought, would be a compact moduli space. So, I mean,
interior.
The interior of the moduli space, meaning not the m and not the length of the semi-infinite cylinder,
not the perimeter, but these edge lengths. No, they can also go from 0 to infinity.
Yes, but the moduli space is supposed to be compact there, right? So you can still fit in some.
I mean, the total length, if you fix, then of course they can't go to infinity because they're all positive numbers. But they'll go over a range. So yes, that is compact.
And still, all these numbers from the matrix model that you have, you can have arbitrary powers of the trace, right? So it seems like those numbers go from also 0 to infinity.
No, for a fixed correlator, it will go up to a maximum bound.
Okay.
Because the perimeters, those L's, are the fixed numbers. But it is true that to get the continuum limit, if you want to see the points distributed uniformly over the whole moduli space, you have to take this continuum limit, namely consider what we call the BMN limit, where the operators are very large, trace m to the infinity, I mean, different this thing. So that in that limit is where you see the double scaled old matrix models, you see a continuum, I mean, you see the whole, I mean, this edge of the matrix distribution, everything. So in that limit, you recover that, you recover the conservate volumes, etc. But in general, it's a discretized version of everything people did at that time.
Other thing, very quickly, is in the context of this, say, 4 punctured sphere, there are these boundary points where suppose you fix 3
the degeneration
points. Yeah, the degeneration points. Do you get that?
Yeah, so that I think Abhiram was also asking earlier about this Deligne-Mumford compactification. It's a very tricky thing. I think, in fact, many people point that as a hole in Konsevich's original proof, which I think some people say that he didn't completely prove it from a mathematical point of view because he didn't completely take into account. I think what I understand is that you can get some of those compact degeneration points by allowing these treble differentials to degenerate. There's a slightly general class called Jenkins treble differentials, which allow for sort of some single poles also. And so there is some degeneration limits, but again, these are mathematical niceties that I don't fully understand.
Yeah, hi. So how much of this treble differential construction, is it very specific to the 2 matrix model, or we can also use it for 1 matrix model?
So the mathematics is of course universal, but so in fact we started with the 1 matrix model, and the 1 matrix model can be recovered from this 2 matrix model as a special case where you just deform by a trace m square or a trace k square, let's say, and then you integrate out k, you will get a 1 matrix model in M. So the 1 matrix model and all its correlators is a sub case of this, is a special case of this. So so that's why I didn't specially talk about the 1 matrix model, but everything you can say can be said for that.
Okay, thank you.
Hello?
So now we have Justin's talk.
Yeah.
You'll tell us about the large edge vector model on S1 times S2.
Okay, I want to thank the organizers for bringing us together again, and echoing Sandeep and Rajesh. My first international meeting was here as a student actually. and it was the time of M theory and the matrix model. So now it's very different time. Yeah, there was a matrix model just before, in fact. Yeah. So yeah, I'll be talking about this model, and let me just go ahead. So because of Shiraz's talk, I don't have to introduce the subject actually, but let me just do some heuristic motivations for the subject again, just to get our bearings. So the ADS-CFT correspondence, as all of us here know, that it relates physics of gravity to asymptotically antidissociative spaces, I mean, with these boundary conditions, to the physics of conformal field theories. And this duality, just like all duality, is a strong weak duality. And let us just recall, just to set our bearings, the n equals 4 super Yang-Mills. So this is basically, suppose you take global ADS 5 times S5, the conformal field theory is on R times S3, and it's supposedly dual to string theory. And here is the map of the parameters, which all of us know. Here R is the radius of ADS, and that's related to the 't-Hooft coupling, square root of the 't-Hooft coupling. And if you measure the Newton's constants in an appropriate unit, it is 1 by n squared. And just this indicates the fact that if classical two-derivative Einstein gravity is good description, that the field theory is it's a large n and strongly coupled. Now, given this description, the first one of the natural questions would be to ask, what's the black hole in this description in the CFT? And if you look at the geometry and you look at the asymptotics, at least for the Schwarzschild case, it is R times S3. And just consider, just to study the thermal aspects, if one Euclideanizes this black hole, then the black hole is at some temperature beta, and therefore, one needs to study the CFT on S1 times S3, right? So this is the geometry of relevance if you want to study, simple thermodynamics of black holes. So of course, results from the gravity descriptions are valid at strong coupling and at large n, and of course they give predictions for the CFT, and there's been a lot of predictions over the years. There's been a lot of predictions, quite non-trivial predictions for this, but because of these non-trivial predictions, it motivates us to study the CFT at strong coupling and at large n on such backgrounds, S1 times St minus 1. But there are two possible directions which you can study the CFT in. One is, as was seen in Shiraz's talk, using symmetries, bootstrap at finite temperatures, and there are some versions of it called the Euclidean inversion formula, or the effective field theory methods, and so on. Or you can very well look at explicit theories, explicit solvable models, like there are, and try to understand them at finite temperature or on this geometry S1 times S2, right? But there are very few such theories, and one such example is the ON vector model with quartic interaction, and the Gross-Nouveau model, and as we heard also from a little bit of Shiraz's motivations towards the end, the Chern-Simons theory, fundamental Chern-Simons theories. Now, such theories, of course, are relevant in condensed matter physics. For instance, the ON model is used to describe the critical point of the Heisenberg magnets. Apart from that motivation, the ON model at large n and the singlet sector of the ON model is conjectured to be dual to the higher spin theories, and therefore it's of course interesting to study this model. So this is the focus of the talk, the ON model, and it, if we study it properly in the singlet sector, we would get some aspects of Vasiliev theory. Furthermore, when the theory is placed on S1 times S2, of course, as all of you know here, this geometry is relevant for transitions in the bulk if it is a two-derivative gravity. Right? And there is a transition from black holes to pure ADS and so on. So this geometry is relevant. I just want to motivate the fact that this geometry is relevant to study. So in spite of this extensive studies of the ON model, quite extensive, it has been there, the condensed matter people also study it. There has not been a systematic study on S1 times S2. And this is true even for the unconstrained model. And studying such examples will be useful as inputs for the general methods which have developed in the literature recently. Now, let me just, because this time is short and so on, I'll just present the main result. So we develop a method to evaluate partition functions and thermal one-point functions of higher spin operators of this critical ON model at large n, and strong coupling S1 times on S1 times S2 in the non-singlet sector. Now, thermal one-point functions, I might not get into it because I might not have time, but I'll try to present the partition function. So our methods result in a systematic large radius or high temperature expansion on S1 times S2. So that means in expansions of beta by R, right? So large temperature means small beta. So we also develop low temperature expansions of this theory on S1 times S2, and it is of this kind, it's exponential. And using Pade-Borel methods, and the low temperature expansion, we actually obtain a partition function for the whole temperature range, right? Whereas that's numerical, as you will see soon. So the ON model, let me just define now. I mean, we're going into the ON model. As everybody knows, it's a simple model. I mean, it's a model which people study in field theory. So here is the model. It's 3-dimension, and there is one scalar, fundamental scalar in the ON, and there is a quartic coupling. And this is the metric on the sphere, right? So it's placed on S1 times S2. And to evaluate the partition functions, we follow standard methods. So first, what we use is we use the Hubbard-Stratton-Mitch transformation to make the action quadratic by introducing an auxiliary field, just like Gaussian integration. You can introduce the auxiliary field and make the action quadratic. These are standard methods, and one can see that at large n, it's only the zero mode of the auxiliary field which contributes, and the non-zero modes are suppressed in powers of 1 by n. And now the zero mode, if you see, because you have to introduce a phi squared times the auxiliary field to get this quartic interaction, the zero mode functions as a mass squared, and therefore we will perform the integral. So we'll drop every else. So we'll just perform the integral over the zero mode of the auxiliary mass, and that is obtained by a saddle point method. Now, so this leads to the following saddle point equation. So you imagine that, okay, we forget the quartic interaction, or the quartic interaction and enters through the saddle point equation, and so we look at the massive scalar, and we have to solve this equation, which is called the gap equation, right? And the solution of this is called the thermal mass. Now, at lambda goes to infinity, the gap equation simplifies. This part drops at strong coupling, this part drops, and we just have to find the critical point of the partition function of a massive scalar. Now, to summarize, let's just have this summary in our mind. So what we need is basically to evaluate the partition function of a massive scalar on S1 times S2 and solve the thermal mass using the gap equation. So let's recall the results which are known so far. So on S1 times R2, there is the following solution to the gap equation. So here it's sort of the log of the golden mean, and the expectation value of energy, if you compute, it goes like a thermal theory, t to the cube with a zeta 3. And this was obtained by Sachdev and collaborators early on, right? So this is the known result. And in fact, if you can compare, this is similar to what you people know from n equals 4 Young-Mills. You can compare the energy density at the IR fixed point versus the Gaussian theory. The IR fixed point is this lambda goes to infinity, and this is 4 by 5, just similar to the 3/4 answer which you know in n equals 4 Young-Mills. So what we wish is to consider the theory on S1 times S2, and we need to evaluate the partition function of the massive scalar on S1 times S2, and of course minimize the partition function. Now, of course, this problem seems to be trivial. So you just want the partition function of a massive scalar on S1 times S2, but we couldn't find an expression in the literature for this, right? So let me just outline the method. So what we do is suppose you integrate out the scalar, you can imagine that you obtain this form. So this is the degeneracy of the Laplacian, and here is the full Laplacian, the Matsubara frequencies, and the L into L plus 1, the L squared of the sphere, right? So we got to do this sum. So first we sum over the Matsubara's frequency, and we are left with this particular form. So you can see the Bose-Einstein structure coming out. but there is the sum over the angular momentum. The sum over angular momentum occurs in this very weird fact. There's a square root and so on. The sum over angular momentum for a mass. So there are two terms. I will illustrate the method in the second term. Okay. So let's look at the second term. So here's the second term. You open up the log. And here's the log opened up. And then the square root you remove by introducing this integral. So you introduce this integral. If you do this integral, it's sort of like a vessel actually. It's one of the vessels. But if you do this integral representation of a vessel, so if you do this integral, you will wind up with this. Now you have linearized that square root. I mean, you've got rid of the square root, but you still have the L into L plus 1, right? So how do you remove that? You introduce yet another integral. I mean, you might think it is not great, but I mean, you're going into the integral. But let's do that. So you introduce yet another integral. You see, there is this L into L plus 1 here, or L plus half the square by completion of the squares. And what you get when you introduce that extra Gaussian is that it becomes linear. You see, if you integrate this green part, if you integrate the u, you will wind up with this expression. So you introduce this extra integral, right? Now the sum over L can be performed, introducing a small imaginary part, because it's just linear. It's a geometric sum, and you can do the sum over L. Right. So this simple trick, you might think it is quite, I mean, it's quite trivial actually, the trick, but it has been recently used in many other places actually to cast a partition function of conformal fields on spheres as Harishchandra characters. So let's go ahead. So once you do that sum, you will and you can do the integral over tau, you will wind up with this expression which you can integrate by parts, and then you are left with one integral. Right. So this integral has the radius dependence here in the sign. So it's 1 by sign, which you can, which people I think in mathematics courses, you know how to expand 1 by sign in terms of Bernoulli numbers, and you can do a term by term integration for each of these, and then you wind up with this expression. There are Bernoulli numbers, and you see the beta by r expansion here, right? So you have this expression. And if you perform the same tricks with the first term, you wind up with this partition function. So note the series is organized in terms of this beta by r and in terms of polylogarithms, right? And this was noticed for S1 times Rg earlier on, even Sachdev had noticed it, that you can organize these partition functions in terms of polylogs. Let me just have a sort of brief look at it. So you see this part, the first term is the term which was known. And then there is this sequence of terms which this method will give you. And so a simple test, let me just do a simple test. So this is the partition function of massive scalars organized in the high temperature expansion. And if you a simple test to set m equals to 0, and if you do it before the expansion, you can do the first term and the second term, and you get the answers which are known earlier. You can do it after the m goes to 0 expansion, and when you do that, you get this structure, and you see why do you get these structures over m over r? So you get it because of these extra terms here, but you might think these green terms look bad, but you can resum this using a Borel resummation, right? And there is a singular terms, but you can resum this by a Borel resummation. And this term becomes this. This log combines with the log which was here, and the mass disappears, and then the answer which reduces to a recent answer which was found by these authors, right? So it's a nice test that the expansion is right. Now, of course, let's proceed with the next step. That is basically solve the gap equation, which is equivalent to minimizing with this mass. And once you do that, so that gives you a perturbative equation to solve for the thermal mass, and you can solve this order by order in the high temperature expansion, right? And here is a solution. You see, the green term is the term which was obtained by Sachdev and collaborators, and there is a systematic set of corrections. And once you do this and substitute it in the partition function, you get the partition function, and there is these corrections you can systematically find, right? So this is a systematic method of finding high temperature expansion of the partition function or the energy. And in fact, once you do this, you get the stress tensor, for instance, or the energy organized in terms of 1 by beta cubed and a function of beta by r. And we, in principle, can find this function. The pressure also can be found and obeys, of course, the conformal relation and so on. Now, just comparison with the Gaussian theory, you see these coefficients are very different. This is the Gaussian theory, the m equals 0 theory, and this is the fixed point theory, which is quite different. There's one term even missing and there. Now, now we can go to the low temperature expansion. So we have the high temperature expansion, and we can go to the low temperature expansion. We'll start again from the beginning. So here's the log Z2, right? The term which we got by opening up the log. And you see that what we did was we did this, we linearized the square root and so on. So again, we linearized the square root. We got this term. And the way we did the sum over L was actually initially just doing a transformation on this to make it linear. But now we expand in small m. We expand in small m. And once you expand in small m, we expand the exponential in small m and perform the integral over tau. We result in this expression. And this is a Bessel with a half integer, which actually admits a truncated expansion. And here you see the exponential kind of terms, right? The exponential beta, the low temperature expansion. So by doing this kind of procedure, we can get a low temperature expansion of the partition function. And in fact, it is a exponential times some polynomial of R, like that. It's an expansion of that kind. It's an expansion of decaying exponentials. Again, go through the same procedure, find the minimum of the partition function and solve for the thermal mass. So just to illustrate, here is the thermal mass. You see that now the organization of the thermal mass is different. There's this exponential term, and m tilde r, that's the dimensional less, it was m tilde beta before, now it's m tilde r, and so on. So that's the low temperature expansion. And of course, we use certain domains to expand it, and that domain holds. So once you have the thermal mass, you can fit it, plug it back, and get the partition function. So this gives you the partition function as an expansion at low temperatures. So we went to some high orders. I'll tell you the orders soon. So this is the sort of free energy and the energy density. Now we have the high temperature. 10 minutes. Okay. So we have the high temperature expansion and the low temperature expansion. And are they consistent? I mean, we just did a lot of tricks. Are they consistent? And how does this ratio, you remember there was this 4/5 ratio which Sachdev and all found at the flat space. How does this ratio behave as a function of beta by r? Right. So for that, the high temperature expansion, we carried out this procedure up to beta by r to the power 32 or so. And here's some terms. And then what we did was, because this term, you see, it looks like it's decreasing, but it starts increasing again. It's very high. It increases again. In fact, it's factorially increasing. And what we did was we did a Padet-Borel resummation method on this series. Okay? And the results of this, because you have to truncate it to some order, so it's sort of a numerical Padet-Borel resummation method. And the results I'll show you soon. And the low temperature expansion, we went to quite high orders. I cannot show it here. So e to the power -6 beta by r, we got the low temperature expansion. And we can numerically understand this. So the expansion is known, of course, at low temperatures. There's a rough domain at which this was expanded. They terminate. At a given exponential order, they terminate. You can see it. So it's it was done in some domain and so on. So here is the results when you plot them together. It's the red has become green. Okay. Anyway, So this is the partition function. The blue is actually the low temperature, because I wanted the red to be high temperature and the blue to be low temperature. So actually the green is high temperature now, and you see that they overlap. They're good overlaps. But at low temperature, so of course, when you zoom into the low temperature, the low temperature is good, and when you zoom into the high temperature is good. So there's a good degree of agreement between this expansions. The expansions are organized totally differently, but there's a good degree of agreement. Here is the energy. That also is good degree of agreement. And this line is the domain in which the high temperature, the low temperature expansion is good. The low temperature is on this side. The high temperature expansion is on this side. Now let's look at the ratio. So here's this ratio, right? This ratio, you see at high temperature, let's get the intuition from the high temperature. You remember it was 4/5, it's 4.8, and then it sort of, this is the phenomena which it was quite unexpected. So it dips first, and then it climbs up from the low temperature expansion. You can see at low temperatures, it climbs up to unity. That means the interacting point or the critical point, and this is the same, the partition function. You can see that the reason why that happens also can be sort of understood, because if you see the thermal mass at low temperatures, you see it's exponentially suppressed. So the deviation from the free point is exponential, and that's how it becomes unity, because the thermal mass vanishes there, and it's consistently seen. This dip is consistently seen in both the low temperature and the high temperature, and consistently at the same point. And in fact, we have, like, you can see the increase, the test. I mean, like 4, 4, 6, 6, and so on, and you can see sort of the convergence of this. Let me just summarize. So the ratio of the free energy of the interacting theory and the Gaussian theory, it starts at 4/5 at 0.8, dips to this minimum, which we don't know why. I mean, we didn't expect it. We thought it was some kind of monotone. At beta by r is 1.5, and the ratio then climbs to unity. So this is one part of it. And how much time do I have? Yeah, so maybe I'll just indicate something which we did for the higher spin, 1 point function for the higher spin after this. So for instance, these 1 point functions are sort of the observables in this theory. And what we did was it was known for S1 times R2, and we could generalize this for S1 times S2. The reason, one of the good things about it is to develop that OPE methods for S1 times S2, which allows you to invert the 2 point function and get the 1 point functions, right? And it also serves as the cross check for the gap equation and the stress tensor which we found from the partition, because you can read out the gap equation from this inversion formula as well as the stress tensor. So it serves as a cross check, and we did that. So 1 point functions of higher spins given by these expressions, and these expressions are essentially due to symmetries. But to constrain this, we need the 2 point functions, which admit an OPE expansion of this kind, where the 1 point functions are hidden in this 1 point function of higher spin operators, and therefore to extract out the 1 point function, we need the 2 point functions on S1 times S2 of a massive scalar, and that was also, or so this is what I said. You can test it, but the 2 point functions of a massive scalar on S1 times S2, that was also not known in a very sort of compact form, in a form in which it was amenable for this expansion. And here is the 2 point function. So we have this 2L plus 1 degeneracy. The Fourier transforms in the YL space gives you the Legendre polynomials, and this is the inverse, the Laplacian. And you can perform these sums exactly like the way we had done for the partition functions. And there's this nice form you can write for the 2 point function, right? And you can test this also. You can put m equals 0, and it reduces to the 2 point function. So using this 2 point function, we set up a high temperature expansion, and we extracted out the 1 point functions of the higher spin operators, And let me just not go into that. I'll just present the results. In fact, the stress tensor extracted from this, as well as the gap equation extracted from this, coincides with the method. And let me just present the higher spin. So there is this expectation value of the higher spin operator and the corrections, finite size corrections, which we can extract from this method. And one of the things about it is that at large L, it's supposed to simplify to the free theory. And here, the simplification at large L is basically when you take the ratios of these large spins. When you take the ratios of these one-point functions to the free theory, it should reduce to 1. And that we notice in all cases. Here's one. Here's the example for the flat space where it sort of goes to 1. And here's the expansion of the finite size correction. So let me just conclude. I think I've sort of reached the point. So we developed an method to obtain finite size corrections of thermal absorbers to critical ON model as a systematic expansion on beta by R. It's of course a definite theory, not a very general method, but still it's useful to test the general methods. And we developed Pade, the Borel, the resummation methods, and tested the high low temperature expansion. And let me just say, so these results, of course, are useful to test the various general methods that are being developed. And in fact, they're generalizable. These methods of doing the sums are generalizable to other manifolds. And in fact, this paper was before Shiraz's work, and we can actually put in the angular momentum. Thank you.
Could you show that ratio of partition functions once again?
Yeah, that is a surprise. I mean, yeah, let me show the two different plots: the low temperature and the high temperature.
And I can't read. So which one is which is the numerator, the free or the interacting?
The interacting critical point
by free. I was wondering the following very vague thing. Suppose we did it in n equals 4 Yang-Mills.
Yeah.
Now, both in the free theory and the interacting theory, there's this phase transition, right? There's low temperature is gas, high temperature is black hole. I presume that the phase transition happens later for the interacting theory. So then there is this range of temperatures where the interacting theory is still in the gas phase, but the free theory has gone to the black hole phase. So in that theory, there'll be a range of temperatures where this ratio suddenly becomes 1 by n square. I was wondering whether that is,
that's the reason why.
That's the reason why.
Yeah, I guess we have to do the constraint model to see this. I don't know. I mean, we were very surprised to see the dip actually, and the dip is consistently seen at the low temperature and high temperature. That is what's amazing, because when you start doing the Pade, you don't see anything. See, green is the Pade. I mean, that's supposed to be red, but that's supposed to be Pade. Then it starts developing. Then the object starts developing the dip.
When model, the Hagedorn temperature is very high.
Yeah, it's very high. It's close to
That's not really what
It is an unconstrained model. Yeah. Yeah, you can imagine it. Okay, so let's just, I mean, we had a heuristic reason for why is the mass starting with exponential. You see, so m tilde r is the scale now, because, it's low temperature. M tilde r is the scale. If there was a constant in front, that means there's another mass gap. So that cannot happen. Yeah.
At 0 temperature, the mass is
0, yeah.
And there's almost no density of stuff.
Yeah. So it has to be the free theory.
Would it be possible to extend the analysis by introducing a small squashing parameter of S2? The squashing of S2.
Yeah. But it's a very small point, 8.7. Then it reaches the limit.
Yeah. Just want to check that the math is correct.
You can.
Until he comes back. Takes time, I don't know. Because I know we are on schedule.
There's still 2 minutes. You can come. Yeah, it's the button I think.
Oh. Hello?
Yeah, it's working, but I think now it will not.
Oh. Yeah.
You can try.
I think it's coming.
Tap it.
No.
Okay, but you will call. It's like exactly like done.
I don't know. You're the boss. Hello, everyone. I know everyone is tired, so I'm going to try and be as schematic as possible. But if you have any detailed questions, then please stop me to ask. I would just like to say that, yeah, it's my first time at Indian Strings. It's my first time in Bhubaneswar, and it's my first time in Odisha, so I'm very happy to be here. Thanks for the invitation. So today I wanted to talk about this work based on these 2 papers. Hopefully the second one will be out this month, but who knows? So these are my collaborators, and the title of the talk is Negative Geometries and N equals 4 Super Young-Mills. I think it's fair to say that most of the people in the audience, your motivation for studying N equals 4 Super Young-Mills is ADS-CFT. My motivation is maybe a little bit different, not that I don't like holography, but it is very scattering amplitudes based. So what do I mean by that? So if you think about like Peskin and Schroeder or Srednicki or whatever your favorite QFT textbook is, when you're trying to calculate QED scattering processes, then this is the method, right? You write down the Lagrangian, you extract Feynman rules, you draw Feynman diagrams, and then you calculate and you sum over those Feynman diagrams. And this is in increasing order of complexity usually. But yeah, the calculation is organized in some perturbative series in your coupling. So a famous example is this gluon scattering process. So this is 2 to 4, which is about 220 Feynman diagrams. This was solved in 1985 by Park and Taylor. And this is the solution. So these 8 pages are not, it's not the calculation, it's the solution. And the following year, they simplified that to this formula. Okay, so, and I want to also point out that this is no longer 2 to 4, it's 2 to n minus 2. So clearly using the correct variables and the correct approach helps you enormously simplify scattering process calculations. Right? And why is it simple? Because there's some symmetry property. So roughly, like this is the cycle of the virtuous cycle. Is that what you call it? Whatever. So like basically you have some new calculation that someone does. You stare at that calculation, you figure out that the answer has some property. You use that property to write down a new method, and then you use the new method to do yet another new calculation. And hopefully in this process, you learn something about QFT or particle physics, gravity, whatever it is that you want to learn something about. So in this talk, these are the properties, calculations, and methods that we'll be looking at. In particular, there is this question mark here that I would like to talk about the most, which is, is there some other property of n equals 4 super Young-Mills that we haven't seen or we haven't understood before? And that's just based on the fact that parts of n equals 4 have some nice scattering, simple scattering that we're going to see. So this is a list of reasons why one can like n equals 4 super Young-Mills if you like scattering amplitudes, or if not, these are the nice properties of n equals 4 super Young-Mills amplitudes. Yeah, in particular, we'll be interested in the fact that there exists a polytope description of n equals 4 called the amplitude-hedron. But yeah, we'll also be actually integrating things, which is always good. So it's not just at the level of the integrands, we will have integral results. And then I'll also briefly talk about the symbol of those integrals. But yeah. Yeah, so n equals 4 has color ordering, so we're in the planar limit. The tree level amplitudes have some recursive structure, but we'll mostly be at loop level. And yeah, we'll have dual conformal symmetry that will make things a bit simpler. Okay, so the alternate title of this talk was Loops in a Loop Expansion, which is what the, which is probably the catchier title for the talk. And I just want to go roughly the 3 things I would like to make sure I get through in this, however long it takes, is why we are expanding, what we are expanding, and how we are expanding. Okay, so let's, yeah.
If you're going to say this later on.
Yeah.
But you said that there was no IR divergence. Did you say that?
Good. This will be like very important very soon. But it'll be in number 2, so you'll have to wait. Yeah. Okay. So very powerful physicists have conspired to get lots of very high loop results in n equals 4 super Young-Mills. In particular, these are the 3 and 4 loop calculations done by the authors over here. And you can ask the question, can you resum these perturbative results to get something meaningful? Okay. Now, resummations, we saw a little bit in Siddharth's talk. And also in Siddharth's talk, where he actually brought up this exact paper, which is when you take phi cubed and you sum all the ladders, that's actually an all loop resummation that you can do. But then the answer that you get is e to the minus g square in the strong coupling limit, which is basically maybe not so surprising. You chose a measure 0 set of Feynman diagrams, you added them together, and you got something that was vanishingly small at strong coupling. Okay, no surprises. The surprising thing that I want to focus on is this calculation over here, which was in 2021 by Nima Alkani-Hamed, Johannes Henn, and Jaroslav Trinka. So they looked at diagrams like this. I know I have not told you what these are yet, but bear with me. So the thing to know is that each of these nodes is one loop. So this would be a 8 loop contribution to some n equals 4 amplitude. But despite the fact that in both cases, this is a very small subset of the Feynman graphs that contribute to the final result, here actually they did get a non-zero and correct order result at strong coupling when they summed over all such diagrams. Okay. So despite the fact that both of these are very ad hoc selections of graphs, in one case you did get something that contributed in a non-zero way at strong coupling, and in the other case you didn't. So one can ask why that happened. And in particular, this should now tell you what loops in loop space means, because what I want to do in this talk is basically go to loop order in this loop expansion. I'll tell you exactly what I mean by that. Okay. Yeah. Yeah, so that could definitely happen. Footnote, there are important examples and specific limits. So for example, there's like iconal limits you could take, or like classical limits, and then these would be, they would be the lasting contributions in that limit. Yeah. Yeah, 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 yeah. Some impact parameter, or yeah, what, yeah. So here we're really going to look at, we're not looking at a specific kinematic one. Okay, so now let's come to Shiraz's question. So in loop amplitudes in n equals 4 have a very specific IR divergence structure, which is that at L loop, the amplitude goes as 1 over epsilon to the 2L, where epsilon is the dim reg parameter. And in particular, Byrne, Dixon, and Smirnov had this ansatz for what the L loop IR divergence looks like for 4-point and 5-point, but we'll focus on 4-point. And it took this form where you had m being the exponential of this set of functions here. So the thing to note is that, okay, these are some things, but importantly, all of the like kinematic information is actually just sitting in the one loop answer. And further, the like actual divergence is just controlled by, or the leading order of the divergence is actually just controlled by this number called the cusp anomalous dimension. So the form of the BDS ansatz should give you a hint that maybe the correct thing to be calculating, which is finite, would be the log of the amplitude and not the amplitude itself. But that will still have this 1 over epsilon square divergence. So it's milder because now on the left-hand side, this is this is valid at any loop order. So like on this side, it's no longer 1 over epsilon to the 2L. It's just epsilon square, so it's milder, but it's still not finite. So instead, it's useful to look at the integrand of this 4-point amplitude. And normally, this would not be a well-defined quantity, except in this case, we know that this is n equals 4. It has it has many, many properties, one of those being that the amplitudes are actually just Wilson loops. So this quantity, FLZ, which is the integrand, so, okay, let me go back a little bit. Sorry. So every time I do an integral, I get a 1 over epsilon square. So if I want to get rid of this, I just have to do all but one integral. So that's what I mean by the integrand, and that quantity is actually just this, via this Wilson loop amplitude duality, this quantity over here is this ratio of Wilson loops, expectation value of these Wilson loops. Sorry, so there's this little x over here, which is a Lagrangian insertion at some point, and that point is exactly z. And this one is an empty one, and so that just cancels out any divergence that you yeah, and you can then, so once you have calculated FGZ, you can then use that to also obtain gamma cusp. All right. Okay, so because this is an integrable theory, there are predictions for what both of these functions are in both weak and strong coupling regimes. Yes.
You've now got some separate quantity that predicts the infrared divergent path. So you take the ratio of your amplitude divided by the separate quantity of that.
So I don't take the ratio of the amplitude. I take the all but one integrand of the amplitude. So if I'm at L loop, I do L minus 1 integrations and I have something. And that thing is this ratio of Wilson loops, if you prefer thinking of it as a, yeah. Over Z, yeah. Yeah. Choosing a specific contour for Z is exactly what's going to give you the cusp anomalous image. Yeah.
Suppose we were interested in the final
Of
the amplitude. Then you would take ratio.
No, then you would get this, right? You would get this 1 over epsilon square. I mean, unless you have a better way of thinking about S matrices with massless particles. Yeah. Okay. But that's why we want to look at this, because it is finite, and so it's well different. Okay. So both of these quantities are known. I mean, there are predictions for G less than 1, much less than 1, G much greater than 1, both for F and for gamma. And while we won't be able to reproduce the strong coupling behavior of F, we will be able to reproduce the strong coupling behavior of gamma. Yeah, and yeah, a lot of authors have worked on all of these calculations, and yeah, we are going to focus on a purely amplitudes-based approach to finding these answers, and hopefully we learn something about amplitudes and resummations in the process. Okay. It's because the Wilson loop here is null. Yeah, and it's polygonal, which is why there's a gamma cusp contribution. No, each of the separations is null. Yeah, so I think the strong coupling result for F you can also get from the bulk by looking at the surface that is homologous to that null polygon. Mm-hmm. Yeah. Yeah, sorry. So I should have this answer at the top of my head, but I don't. So if I can tell you later exactly how that dz integral looks. So I know that if you take the z integral along the contour that goes around like 0 to -1, like that keyhole contour is what gives you gamma. So the discontinuity across the negative real, that is finite, that is gamma. So it's not the log. Yeah, it must be in the z going to 0. Yeah. Sorry, no, I think it's z going to 1. So z is this combination of twistor brackets. So I think the collinear or soft limit is when these are equal, if I'm not wrong. But yeah. But we're really not interested in doing that last integral in this talk. Yeah. Okay. So yeah, good. So now I'll get to the third part, which is how we'll actually do this computation. And that will be related to then the title, which is negative geometry. Okay. So amplitudes and tree amplitudes and loop integrands in n equals 4 super Yang-Mills are given by some canonical form on a convex space, or yeah, a convex space in quotes, called the amplituhedron. Okay. So this is the cartoon picture. This is going to be the thing we calculate. So we just need to figure out what is this space exactly. And to figure out what that space is, you just have to say what are the boundaries of that space. So this is a fact about positive geometries, that if you know the boundaries, you know the canonical form. Traditionally, what you would have done to calculate that form is to do this triangulation like this. Now, doing a triangulation is it's high in complexity. There's no out-of-the-box algorithms that are particularly quick or useful. So instead, what we will do is use unitarity cuts. But yeah, okay. So in case people haven't thought about momentum twisters in a while, I'm going to be using momentum twister coordinates. So Z has this index I, and then I goes from 1 to 4. Any choice of that Z matrix conserves momentum. So everything is on shell manifestly. Yeah, so a point in Z space corresponds to one external momentum, and all of our invariants are just these 4 brackets, which are just determinants. Everything will be written in terms of these 4 brackets. Okay, so as I said, every Z is one external momentum twister, and now the prescription to give you the L loop integrand in n equals 4 is that you have these 4 external points, Z1, Z2, Z3, Z4, and then you look at L lines in that space. And those L lines need to satisfy these conditions over here. And that's it. Now, if I write down the canonical form on this space, it's the L loop n equals 4 integrand. That's including all diagrams, just that's the answer in the planar. So this is the integrand. Yeah, this is the integrand. Okay, so this was the prescription by Trinka and Akani Hamed. Yeah, an important difference here is, and this is why the talk is called negative geometries, is this condition being negative. I don't want to go into the details, but in the normal amplitude-hedron, this would be positive. We are looking at the log of the amplitude, and so you can reduce this to some negative links. The details are not important. It's just a set of inequalities that gives you a space, and the canonical form on that gives you the integrand of the log of the amplitude. So, okay, good. So I also want to say that when each of these is equal, you get you hit a boundary of this space, and that corresponds to some unitarity cut of your integrand. So some of these will be physical, and you want to keep them. Some of them won't be physical. For example, if I choose maybe all of these to be 0, then that's an unphysical cut. And so you have to make sure that the numerator of whatever form you wrote down cancels and doesn't make sure that that is not a singularity of this form. Yeah, actually. Yeah. So you can.
How do you avoid the polynomial time problem?
The
main problem with evaluation of triangulation is that it's not typically polynomial time.
Yeah.
So how do we avoid it here?
So
I'm just trying to understand, because then this will be used to actually write down programs to find triangulations. Right?
I'm not
if
sure.
If it's equivalent,
so
then I should be able to do that.
So
in lesser time, and I don't see that.
So it's not. So the thing is that we are interested in a specific set of graphs. Let's say graphs in this space. Okay, I've not explained this yet, but give me a second. So basically, what we are doing is saying that we have some ansatz. And we know that ansatz for the numerator. So we just put all of the boundaries in the denominator. Say we have an ansatz for the numerator, and I know that the numerator has to vanish whenever I'm doing I'm going into some unphysical region of my integrand. So I use that to figure out what n is. I stare at n for enough examples, and I notice that it becomes some all n formula. So it's not, in the particular cases that we solved this, so in the particular cases that we solved it, obviously that's easier than, I mean, looking at our formula is easier than doing the triangulation. In the cases that we don't know what the solution is, you have to do the triangulation. Yeah. But yeah, basically, yeah, our paper was that you don't have to do the triangulation because this ansatz way of looking at it actually uniquely fixes the numerator in some set of graphs. Yeah. So just to be clear, the graphs that I mean over here are just saying that, so each of these is a loop, and this is just saying that what conditions, so for every red line over here, this condition needs to be satisfied by the space. So so I'm just going to say that the omega that I'm interested in, the form that I'm interested in, that's going to give me FGZ is given by the sum over connected graphs. But yeah, okay. So all right, okay. Someone recently told me you shouldn't have the slide number over here. It gives things away, but okay. So anyway, hopefully this gives us a sense now of what tree level means in this story, right? Tree level means I have a space that's carved out by some inequalities, but those inequalities never form a loop, right? So the tree calculation was done in this 2021 paper. And as I promised, if you look at their gamma cusp for some set of graphs, so this is the integrability result, these are their results. Okay. And I mean, I don't know about what your standards are for close and far, but 8 over pi is basically 2. So I think you should be somewhat surprised that it came this close to, for a very arbitrary selection of graphs. So I want to emphasize that normally when you do like a loop expansion, you have the Tooft coupling that's telling you you should do some perturbative expansion. Here, there is no parameter that's telling you that the trees are separate from the loops. It's just that the trees were easier to calculate, so they calculated the trees. That was the reasoning in their paper, right? So the fact that it came so close could be one of two things. Either you're a very optimistic physicist and you say this means that this is an approximation, right? Or you're a pessimistic physicist and you want to do the one loop calculation to show that this was an accident. Whichever camp you fall into, you have to do the one loop calculation, I think. So, which is why we did the one loop calculation. But yeah, so then these are the numbers in case anyone wants to see the actual numbers. Okay, so I'm not going to go into how we fix I mean, roughly it's what I said before, that you have the numerator and ansatz, you're using physical and unphysical cuts. You fix the integrand. Yeah, so this is what the tree integrand looks like, just to get a sense of how complex the answer is. This is what a loop integrand looks like. Or we call it one cycle, just so that we don't get confused between loops and cycles. But yeah, just the cusp anomalous dimension. I mean, actually, you can even look at F here, and you see that it's very incorrect. But surprisingly, all of these go as G. Yeah, and these are the weak coupling. Okay. Yeah, so it's a little complicated, but it's not too complicated. And so, you might hope that you can actually do the integral. So I'll remind you that you want to do all but one of these integrals. So best case scenario, someone in the literature has already done this integral for you. And that was what happened to me, at least, is that I just found that someone else had done some of these integrals. And then you see how much mileage you can get out of integrals that someone else has already very heroically computed. Okay, so it turns out that these are the two cases that are known, the 3-loop, so the triangle and the box. So 3-loop and 4-loop one cycle. Okay, so, right. So generally when you're thinking about trying to integrate things and get integrated results, one of the best things you can do is write down a differential equation. So using a differential equation that basically, and the two boundary conditions that f needs to be 0 at -1 and it has this other property, you can get integrated results. So this is an example of an integrated result. I should have shown the graph, I'm sorry. So it's just one triangle with one little branch. It's this. So I don't know how many of you have stared at like a 3-loop integral, but this is actually not so bad. They're all harmonic polylogarithms, which means all of your singularities, your branch points are just at z equals 0, +1, -1. Not very scary. You have some log, you have some nice zeta values, like it's very tractable looking. In fact, it's so tractable that then one can go ahead and actually calculate this, which is a triangle with any number of things attached to it. Okay. You can also do this for the box. Sorry. So in the perturbative regime, this is what the answers look like. When I add the triangle, you can see I get a little bit closer to the actual answer. Okay. But this is not what I promised you. What I promised you was that we could actually do a resummation and maybe get something at strong cup. Okay. So, right. So the quantity we look at strong coupling is gamma cusp. You can take your n triangle, you can take this f of z function and pull out gamma cusp from that, and that gives you this. Again, I mean, not too unreasonable looking. It has uniform transcendentality, which is something that has helped people do like symbol bootstrap, etc. So it's a nice property to have. And yeah, you can write it all in terms of zeta values. It's not too bad looking, even though this is like an, in principle, n+3 loop contribution to gamma cusp. Okay. Okay. So this is kind of like almost at the end. One now wants to resum these answers that I showed you previously. Now, it's not a very well-informed thing to do, to just sit and try and write down a series expansion. Yeah. So instead what we do is use the already resummed ladder and attach that to the triangle. And that is actually a calculation one can do analytically. You have to read a lot of like old textbooks about series, mostly written by Russians, but in the end you do get closed form answers, and then this is what that looks like numerically. Now you'll notice that this has a g to the 5 over here. Okay. So at this point, I think when we only had the triangle result, I was like, okay, so then the earlier result that they found at tree level was an accident. What made me hope that that was not true is that when you do the box, you get g to the 7th. And actually, you can show that as long as the basic polylog structure of this type of integral continues to hold, this will just keep going. This will just go g to the 9, g to the 11, etc. So it's clear that we're doing the wrong resummation. We should be doing this resummation. So our next steps are basically to figure out so we have some notion of the structure of these integrals, but we need to more specifically understand the singularity structure and the actual functional space of these integrals. And then hopefully we'll be able to do the resummation in this direction, not just in this direction. Okay. I just want to say that we do have like other results. It's not just, I know this looks very similar, but it's not the same. In particular, you'll notice that there are these B's over here. So all of the results I showed you before this had these H's, which are harmonic polylogarithms. So they only have singularities here. But if you look at other geometries, you actually find singularities in other locations. but they all cancel out against one another. So that is also something that's telling you that there is some additional structure here that we haven't understood yet. And I think, yeah, doing the full like symbol calculation at higher loop is going to tell us more about when you have spurious letters and when you don't. Yeah, sorry if that was too much jargon, but yeah. Okay, so these are the features of our results. We have gamma cusp for tree graphs. We have uniform transcendentality. We don't get multiple zeta values, which is surprising. But as the number of cycles increases, the depth of those, we do get multiple zeta values, the depth increases. You can do some like fun numerology with the types of numbers that appear. Similarly, you can do functionology for the integrated answers. And this is something we're thinking about now, which is what kind of functions will appear at higher cycle. Okay, so these are some open questions, but maybe in the interest of not killing people at the end of the day, I'll just leave these up here and say thank you for your attention.
If I understand correctly, a lot of these techniques rely heavily on the theory being n equals 4 super Young mills. Can we learn something about computing amplitudes in general, you know, like gauge theories, SUN, QCD?
Yeah. So one thing is that I feel afraid of making eye contact with Shiraz at this point, but there does exist a ABJM amplituhedron. And so there have been, people have done the analogous calculation for that.
Sure, but
positive
that also
geometry,
has
but that is of course also a very
also very
supersymmetric specialized case. In general, I mean, I personally, I think that every time you do any like higher loop calculation, you learn something about how you would do this in QCD or how you would do it in non-supersymmetric gluons. It just tells you, yeah, what kinds of integrals appear, what kinds of functional spaces are there, and then every time you learn something about this functional space, you're closer to being able to bootstrap it at the next loop order. Yeah.
Thanks.
The cusp anomalous dimension, you can also calculate through integrability methods, isn't it?
Yeah.
Is there a way to map any of the? So in principle, you can follow it from weak to strong coupling.
Yeah.
So is there any way to map the strong coupling expansion there, the individual terms to individual pieces that you have?
Yeah. I mean, I think that's the dream. I think that would be very nice if we could do that. Right now, the best we have is just these kind of comparisons where whenever I say true, I just mean the actual, like the Bisert Eden Staudacher equation for the gamma cusp. So yeah, I think it would, you know that there is an asymptotic expansion at strong coupling. So there must be some way of writing the perturbative series from this direction. But what that looks like from the diagrams that we're looking at is kind of unclear, and that we're hoping that by looking more at these diagrams and studying them, that we can answer the question that you just asked.
Yeah, in particular, I guess each term is associated to some higher derivative correction in supergravity, at least the first couple of, in the 1 over G expansion, in the suppression is a higher derivative suppression. So you might want to be able to map individual those corrections to perhaps some set of diagrams or something like that. I mean, I was wondering whether this formulation gives you maybe some clue to how to reorganize super Young mills in a way which is perhaps closer to a gravity or dual.
Yeah, I mean, as I said, I think that's the hope, because the fact that, so for example, if this is true, that you can do this like vertical resummation, that kind of tells you that maybe this is whatever this is, whatever, I hesitate to say parameter, but whatever is controlling this expansion, maybe that is actually a reasonable expansion for some reason, and we have to understand then why is that the correct thing to do, right? But first, I think one needs to answer the question I set up, which is this actually an expansion, and does that bring you closer or not? Yeah. Yeah.
Sorry, continuing about these IR divergences. So you explained to us that these IR divergences are really simple. They seem more or less as simple as in, is it right that they're almost as simple as in QED, except that there are some numbers which you have to calculate order by order? Okay, so I'll just continue the question. The question was, in QED, there's been this noise about Faddeev-Coolidge amplitudes. This way of curing IR divergences by doing something different. I was wondering first whether that was correct, and second whether there's a chance that there's an n=4 version of that, making something completely finite.
Yeah. So my understanding of the Faddeev-Coolidge story is that it's like another way in which you can think of your asymptotic states. But say you didn't want to think of them like that, you just want to think of them in the just like a dagger, infinitely free photon way, then you can still think of all of those dressed states as just some loop corrections on your photon line coming in. So this is my understanding, that it is kind of like a rewriting of the S matrix, where now your asymptotic states contain the IR or soft collinear information. So it's factorized from the rest of the hard part of your S matrix. Maybe that's incorrect, or maybe you have a different interpretation. But in the case of n=4, I think that I'm not going to scroll all the way back, but the BDS-Ansatz way in which the IR divergence is exponentiate, I think that is special to n=4. In fact, it's more than that. I think at n=n meaning a 6 point. So at 6 point in n=4, it stops working. So you have some remainder terms that then you have to also include. So it's quite special to specifically 4 and 5 point n=4 super Yang-Mills that the IR divergences have that.
So you're saying it does not suggest that there's some new kind of asymptotic state which will have finite scattering in general.
I would be hesitant to say that is true. Yeah.
Thank you.
Oh, sorry, can I just say that this is what AI thinks negative geometries look like?
Am I audible? Am I audible? Yeah. Sorry. Okay. Yeah. All right. So, keeping up with the tradition, I would first like to thank the organizers for giving me a chance to talk here, and I would also like to thank the audience for their patience and the fact that they are still sitting here. So, thanks for that. At the end moment, I tried to I changed my title of the talk to make it less to make it humbling. So now the title reads Towards Engineering Celestial CFT and ADS CFT Perspective. Now this talk will be based on the work that was done earlier in this year with Shamik Banerjee and Sagnik Mishra, tomorrow Sagnik will also be presenting, day after tomorrow, he will be presenting the poster on this topic. So I urge you to go and check it out. And if time permits, I will also talk about some of the upcoming, some of the things that I am currently writing and putting up as an upcoming one. All right. So we were introduced by Carolean holography, which is an approach to flat space holography, by two wonderful talks by Daniel and Arjun. So I'm going to be talking or alluding to a different approach which is known as celestial holography, which states that the dual theory to d plus 2 dimensional flat space-time resides on d-dimensional sphere, which is present at a d plus 1 dimensional null infinity. So instead of the dual theory defined on this d plus 1 dimensional null infinity like in Carolean theory, this theory dual CFT is defined on this d-dimensional sphere. Now the symmetry of this theory is if it has to be a dual, then it should be isomorphic to the global symmetry of the Einstein's global symmetry of, let's say, some d plus 2 dimensional flat space-time. So the symmetry group is Poincare group, which is ISO d plus 1 comma 1, and it has a subgroup which is SO d plus 1 comma 1, which acts as a group of conformal transformations, and it is also a group of conventional d-dimensional CFT, right? But here's the difference with the celestial CFT, that there is an additional group, there is an additional generators corresponding to translations. Those are like those are sort of, they are not geometrically realized in the theory, so they act like an internal transformation. Now the celestial correlators are related to the scattering amplitudes in flat space, and this has been like a story for quite some time now, and they are distributional due to translations. However, there has been a limited understanding of the construction of celestial CFTs with full Poincare invariance. So there has not been any string theory example or like some dual CFT which has this full Poincare invariance. The cleanest examples are Liouville-based two-dimensional CFTs with Lorentz invariance, whose correlators reproduce flat space amplitudes in the maximally helicity violating sector. So in this particular approach, you start with a CFT which is just Lorentz invariance, and then you apply an algorithm and then combine these correlators in this theory in such a way that the Poincare invariance is back in, and that the Poincare invariance emerges, and these correlators then are related to the S matrix of the flat space time. Now our goal is very simple. We just want to study and we want to construct and study properties of these celestial CFTs without any reference to flat space holography. And I'm sorry if you are disappointed, but the goal for now is that I just want to study the celestial CFT in isolation without any relation to flat space holography for now. Also, so in this talk, we call any QFT with Poincare invariance ISO d plus 1 comma 1, where SO d plus 1 comma 1 acts conformally a celestial CFT. So that will be our working definition going forward. What we will do is we will provide a simple way to build the celestial CFT from ADS CFT correspondence, and our tool will be a near boundary scaling limit where we zoom in near the boundary of ADS. Okay, so I will now describe what I mean by zooming in near the boundary of Euclidean ADS3. So consider a Euclidean ADS3 background written as follows. This is also a metric which is conformally flat. The boundary is at eta equals to 0. Now, if I want to calculate the conformal killing vector fields associated with this background, there will be 10 conformal killing vector fields which can be categorized as follows. So curly M, curly L bar M, and PRS. You can see that M runs from 0 plus minus 1. So that means there are 6 CKVs here, and then PRS, RS runs from 2 values, so there are 4. The commutation relations of these vector fields can be calculated, and it was found that they obey SO4, 1 algebra. The first part represents this SO1, 3 written in terms of L and L bars, and PRS is basically just transforming like a vector under these Lorentz transformations. And now the important thing to see is that the two PRS, they close to L and L bar. So so this is our SO4, 1 algebra. Now let's zoom in near the boundary. To zoom in near the boundary, we have to take eta tends to 0. The way we do is we do a coordinate scaling where we introduce eta equals to epsilon eta tilde and we keep eta tilde fixed, taking epsilon tends to 0, effectively going towards the boundary. In terms of eta tilde, then the CKVs, they become as follows. So in the first two expression, the leading order is finite in epsilon, and in the last expression, it diverges as epsilon tends to 0. So we know there is a problem. You cannot take epsilon tends to 0, otherwise it will blow up. Now, yes, right, that's no, this is CKVs. Yes, three-dimensional ADS. So isometry is this first part, but then rest all other symmetries are you get from the conformal part of it. Yeah, I'll come with the proposal just a second. This is something just that I'm demonstrating. There's a point to it. So let's say if I define PRS as follows, I can just multiply epsilon here, make it finite, and then take epsilon tends to 0. All these terms will drop out, and I will end up with this particular vector fields that will follow this algebra Poincare ISO 1,3. Right. So again, these L's and L bars, they form this SO 1,3, and note that they are undeformed, and the thing that changes is the commutation relation between PRS, right? It just becomes 0. So what we can say is that in the near boundary limit, SO 4,1, it contracts to Poincare group, with SO 1,3 acting as the conformal group, or in this case, it's still an isometry of Euclidean ADS 3, right? This PRS then becomes translations. You can generalize the statement to higher dimensions and say that SOD plus 2,1 contracts to ISOD plus 1,1, and the subgroup SOD plus 1,1 remains unchanged. Right. Yeah, that's what. So now let's look at the geometry and the symmetries after the limit. So we started with this particular line element, and as you see in terms of epsilon, the second term will dominate over the first term, and therefore the resultant line element will become degenerate in the direction eta tilde. So the manifold that you get after this near boundary limit has this boundary line element as follows. It will become a three-dimensional degenerate manifold. SO 3,1 will act on these new coordinates z bar eta tilde as follows, like CFT transformations, Z and Z bar, these are Mobius transformations, and it will rescale eta tilde as follows. The effect of translations will be that it will keep Z and Z bar fixed, but it will shift eta tilde, and it will act like some sort of a Weyl transformation. So the take-home message from the slide is that the Euclidean D plus 1 dimensional ADS in near boundary limit becomes D plus 1 degenerate manifold. So after this, let's look at our proposal. So this is the well-known statement of ADS-CFT. On the right-hand side, we have a string theory, or you have a conformal gravity with SO 4,1 symmetry, or you have an Einstein gravity with SO 3,1 symmetry on Euclidean anti-de Sitter 3, right? According to the ADS-CFT correspondence, it says that these theories should be dual to two-dimensional CFT with SO 4,1 if the bulk theory is conformal gravity, or SO 3,1 if the bulk theory is Einstein's gravity. Now, what we did was we took the near boundary limit, and what we will get is I will have to explain this term later, so please disregard it for now. This is just, I will explain it, long strings. So the string theory will become a theory of long strings, and the conformal gravity or Einstein's gravity will become gravity theories on degenerate manifold with symmetry ISO 3,1 or SO 3,1. So note that this is still a three-dimensional manifold of what we begin with, but now the geometry of this manifold becomes degenerate. Okay, so now if we assume that this ADS-CFT duality, it survives the this near boundary limit that we are taking, we propose that this duality will suggest that to this geometry, to this bulk gravitational theories, the dual theory would be a celestial CFT with Poincare invariance ISO 3,1 or SO 3,1 symmetric group, right? So if it's a gravitational theory with SO 3,1, it will be just some celestial CFT with SO 3,1, and if it's with ISO 3,1, it will just be celestial CFT with pointer invariance. So yeah, that's like a really good question. That's the part of the thing. So I will probably try to show you, if time permits, one example of it. It's not entirely clear yet because the representation theory of two-dimensional CFTs with SO2,3 is like not well. Yeah, it will be some so they will be realized non-geometrically. So so it will be some internal transformation that we'll have to see. I mean, I'm still, yeah. Yes, probably there will be additional symmetry algebra. Right. So now with this proposal, let's look at the near boundary limit of a string theory. So conventional string theories, they do not have target space conformal invariance. So when I say target space conformal invariance, I mean that in the bulk, the conventional string theory, the low energy effective theory of the string theories are Einstein's gravity instead of conformal gravity. Yeah. Yeah. So SO for right. So SO 3,1 is your normal CFT, right? Now what this SO 4,1 is doing is that the higher dimensional symmetries are getting accommodated in this lower dimensional theory, so they act like internal transformations. Like there will be some extra fields, so they are not geometrically realized, but then you have to like the interpretation is still not clear in my yeah. Oh, so yeah, but I can write down how the field will transform under these transformations, like these extra symmetries. I mean, we'll see. I will show you the solutions of conformal gravity in 3D and see how these symmetry acts with them. No, I'm just considering a enlarged symmetry group of conformal gravity. Like you would have a. Oh, that is right. So right. Okay. So can we discuss this question towards the end, because there will be so then yeah. I mean, I would love your feedback. Yes. But I'm still not sure how it is manifested itself in this two-dimensional CFT. I have some hints because I'm looking at the asymptotic symmetries of 3D conformal gravity, which I will come to in some time, right after this. Right. So okay. So let's look at the right. So where was I? Yeah. Conventional string theories, the low energy effective theory is Einstein's gravity, and therefore you won't get the full conformal invariance. So according to our proposal, what we say is that in the near boundary limit, string theories on ADS should be dual to celestial CFTs with only conformal Lorentz invariance. Because if it's duality, then I'm assuming the first step is no. I mean ADS CFT. I mean duality. Why can't I study? I mean if the duality, it's a conjecture, right? Not really. That's why I'll show you. It's not SO 3,1. You get a larger group from the asymptotic symmetries of conformal gravity. No, not really. Why? I mean, I don't understand, because if the bulk theory that has that global symmetry group is SO 4,1, then I will assume that if your ADS CFT conjecture is true, then both the theories should have the same symmetries. Why would the symmetry break? True, but then I can also consider twistor string theories who were like low energy effective theories, some super conformal gravity theory like Berkovich-Witten type theory, and then one can see from there the symmetry, there will be conformal invariance, right? Like SO 4,1. And so this is still not concrete, it's just a proposal, but there are like it's nice to see that there are some evidence to it. I mean, you can decide after I present whether it's like good or not, but yeah. Phi 4 in ADS 4 dimensions, right? I'm talking about Euclidean ADS 3 here. 4 dimensions. So anyway, the isometric group is SO1, 4, right, in ADS. So that is true. But here I'm talking about, so there it will be SO5, 1. And then in ADS 4 there will be SO5, 1. Anyway, I mean the time is running out. So I'll just move. Okay. So right. So our claim is that the string theories on ADS should be dual, the near boundary limit of them should be dual to celestial CFTs with only conformal or Lorentz invariance, right? So for that, let's consider a bosonic string theory on Euclidean anti-dissector 3 times some compact manifold. And since it's bosonic string theory, we are considering the dimension should be 26. So this n is some 23 dimensional compact manifold. You can have any choice. So in the presence of this NS bimu field, with the Euclidean ADS3 metric given like this, right? So now I can write my bosonic part of the Lagrangian on the 2D world sheet theory as follows. So the target space is Euclidean ADS3. The coordinates of the target space on this 2D world sheet are like the fields. So phi, and gamma, gamma bar, they are the functions of this world sheet coordinates, right? And S int is the world sheet action for this 23 dimensional manifold N. So and one more thing, this WZW model, it plays an important role because in this West-Zumino-Witten model, if you parameterize your group in such a way, you you take a particular form of that group, you will end up with this action. So you can see from there, and that group will the element should be in this coset SL2C quotient by SU2. Okay, now the following previous action can be written as follows. What I have done is that I have added two auxiliary fields, beta and beta bar, and because of this measure getting renormalized, there is this dilaton is generated, which is linear in which is phi with this term, where R is the world sheet curvature, and then phi also rescale by this alpha plus. So beta and gamma are the holomorphic fields with 1, 0 and 0, 0 weight, and alpha plus is related to length of ADS and string length as follows. Okay, so now you can see that if I take phi tends to infinity, the last term will drop out, and you would get a free world sheet action, which is given as follows. And now, if I calculate the equation of motion for beta and beta bar, those are just dou bar gamma and dou gamma bar equals to 0. So that means that your target space coordinates gamma and gamma bar are the holomorphic and anti-holomorphic functions of this world sheet coordinates, right? So these are like maps from world sheet to the boundary sphere. Okay, so these are maps from the world sheet and the boundary sphere, right? So now what happens is that because you're taking the near boundary limit, your strings are stretched and it wraps the boundary sphere, and there is a well-known term for that. It is called long strings, right? Because it is towards near the boundary. Also, the world sheet theory has an affine SL2 times SL2 symmetry at level K, which is generated by these currents JA and JA bar, and the central charge is 3K by K minus 2. It was shown by these authors that the symmetries of a world sheet action can be lifted to the space-time, and it becomes the Virasoro algebra of the dual CFT2. So if you have any infinite dimensional affine symmetries, you can just lift it to the space-time, and it will become the, you can define the conserved charges corresponding to this space-time dual CFT. Now, this dual CFT2 describing these long strings has central charge 6 kp, where p is the number of times the world sheet wraps the boundary sphere. So what is happening is that as you are lifting your symmetries from world sheet theory to the dual space-time CFT, this sort of phenomena happens where the strings has to wrap the world sheet according to this winding number. If K is 1, sorry, if P is 1, then its string wraps around the boundary sphere one time, and so on. Okay, so and also if you solve the equation of motion for phi, you would find that phi, the equation of motion, is a Liouville field theory equation, and Therefore, what one can say is that the two-dimensional space-time CFT, which describes these long strings, it contains the Liouville field phi tilde and modes of the fields which describes the location of the string in this compact manifold N. And one can calculate the central charge corresponding to this Liouville field phi tilde, and it comes out to be this. And you would ask you can ask the physical significance of this Liouville field, and what it does is just describing this radial fluctuations of the long strings. Phi was, remember, phi tilde was the length from the center of the ADS towards the boundary. So they are those are like described by this Liouville field. And I would like to just end this slide by mentioning that what we show that you can see that this space-time two-dimensional CFT, which is dual to string theory described by the worldsheet action SNB as follows. This one is an example of a two-dimensional celestial CFT with only Lorentz invariance. So that's the claim. True. Yeah. But here I started with this. Here I won't get extra symmetry, right? Because the string theory has only Lorentz invariance. You have to start with the parent theory, which is. So yeah, I mean, but this is still a celestial CFT. You can consider twistor string theory, and then you would get a conformal, like you would get this ISO 1,3. So this is a way. We are proposing a method, and this is just sort of like a proof of concept for that method. So it has ISO 1,d+1, and where conformal group SO 1,d+1.
But your ISO d+1,
Yeah, true. That is fine. But see, according to this proposal, so what we said was that if your bulk theory would have a conformal invariance, so then your celestial CFT would have Poincare invariance. But here, my bulk theory has SO 3,1, which is like the string, long strings. So therefore, I get a celestial CFT with SO 3,1. I mean, you can argue that why this celestial CFT with SO 3,1 is celestial CFT, but I can answer you because you can see that the bulk theory changes. So bulk theory is not what you have started with. So for the conventional CFT, the bulk theory would have been this theory, but now for this CFT with SO 3,1, the bulk theory is something which is like defined on the degenerate manifold. So so it only makes sense in the holographic perspective. Other than that, I can't answer you that intrinsically what is different for this CFTs. Holographically, you can see that because they both describe different bulk theories, so they have essentially different nature. Right, so quickly I'll just mention something about 3D conformal gravity that I've been working currently. So a quick introduction of 3D conformal gravities are that they are higher derivative theory and they are while invariant. So if you rescale the metric, this action will be invariant. There is no local bulk degree of freedoms, and but there is a non-trivial boundary dynamics. Now the equation of motion is equal to this Cotton tensor, which is defined as follows, and all the locally conformally flat metric solve this equation. One important thing is that this solution to Einstein's equations are always conformally flat, but reverse is not true. This 3D conformal gravity, they admit a larger class of solution than Einstein's gravity, right? So, okay, here was the thing that Arjun asked. So now the global symmetry group is SO 1,4, and it should be embedded in asymptotic symmetry. So when we were trying to like understand this program, if we wanted to take the limit of, let's say, some conformal gravity theory, it would only work if that conformal gravity theory is SO 1,4 invariance. Otherwise, we would never get some celestial CFT with the Poincare invariance. So, right, there were some earlier work done by Daniel here and his collaborators where they investigate the asymptotic symmetries of 3D conformal gravity. And what they found was that the asymptotic symmetries contains two copies of Virasoro algebra plus U1 current algebra. But as you can, this but in these algebra, this no global SO1, 4 algebra was available. Like it was the asymptotic symmetry is in such a way that no SO1, 4 existed there. Right. So then we decided to revisit the asymptotic symmetries of 3D conformal gravity, and if let's take the solution in like ADS like Pfefferman-Graham gauge as follows. You will see that this gamma 1 ij is a new thing here, because for Einstein's gravity this gamma 1 ij goes to 0. What we also do is we impose additional gauge conditions, because in the bulk theory we have 3 diffeomorphisms and 1 Weyl transformations which are gauge transformations, and using that we can also set this condition where this diagonal element of all these gamma ij sub 1, 2, 3, they are 0, right? Additionally, we consider the following boundary conditions. We are considering Dirichlet boundary condition where we are keeping the boundary metric fixed. So gamma ij 0, it is fixed as follows, and gamma 1 zz bar equals to 0. This was true because of the variational principle. We wanted the variational principle to be satisfied, and therefore we put gamma 1 z bar equals to 0. Now the solution space is parameterized by these 3 functions a1 zz, t bar, z bar, and you can write the solution space as follows, and the dot 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 terms denote the subleading terms which will be given in terms of tz, t bar and a1 zz. But these free data a1, t and t bar, they have constraints. So this is one constraint on this del z bar square a1 zz equals to so this is the constraint. Now let's say I try to find my vector fields that preserve the solution space. So this is the vector fields that you can write that preserves the solution space. And one thing that is different from the previous literature is that somehow because of their gauge conditions or boundary conditions, this term was missed in the previous analysis, and they started with only the second term, and therefore you only get 2 copies of Virasoro algebra. Now if I want a Dirichlet boundary condition, then I have this additional constraint on my vector field y z bar, which can be solved as follows. So you can have a free function which is eta bar z bar, and there's some non-local term. Like this is one way I can solve this, and another constraint on f which is like which is this. So infinite. So what we found was that the asymptotic symmetries are infinite dimensional, which are parameterized by this function zz bar, yz and eta bar z bar, with the additional constraints of this del z bar square f plus t bar f equals to 0. Now you can, sorry, what? State dependent? You mean on t bar? Yeah. So it's field dependent. Yes. Yeah. But you can also consider spatial solution where this t bar is 0, and you can just solve that f chirally. It will be just linear in z bar with holomorphic functions also. But yeah, so far it is like background field dependent, and therefore because of this background field dependence, the algebra that you get is a Lie algebroid instead of a Lie algebra. And the global modes, they satisfy this SO1, 4 algebra. So these are the global modes. Now what we find is that asymptotic symmetries of 3D conformal gravity gives SO1, 4 and more infinite dimensional symmetries, and the background field under this asymptotic symmetries transform like operators of 2D CFT plus these additional symmetries. So I'm not going to go to the near boundary limit of this. I'll just show you how these transform, because I thought I would put it there. Right. So these are the transformations of the background field in conformal gravity ADS3. So this delta t, which acts like a Virasoro transformation, this is like a stress tensor Virasoro transformation, but because of this f, you get this additional term. However, you must be thinking that these f's are dependent on z and z bar. So how can a delta t, which is a holomorphic function, goes to some general function of z and z bar? But what you can see that if you take del z bar of delta t, and using the constraint that I mentioned earlier, this turns out to be 0. So in effect, delta t is still a holomorphic function, and delta t bar has just nice transformation. However, delta a1 transforms like a 3/2 minus half field, but these are the two additional terms. So minus 2tf plus 2 del z square f. So this, okay, now what we can ask is like, okay, how is this additional symmetries? They are many, they can come about from just 2D, just studying 2D CFT with SO 1,4 symmetries, and that's something I'm currently like thinking about. If you have any feedback, please tell me. And so, right. So now I'll just, okay. So what I'll just say is that in the near boundary limit, what happens is that the terms which were like inhomogeneous, they just drops out, and delta t has no anomaly term, so the central charge is probably 0, and delta, and because in the near boundary limit I had I was forced to take t bar equals to 0 if I wanted Poincare group in my asymptotic symmetries. So right, so the general, so the full solution of this near boundary, so this let's say this conformal gravity on this degenerate manifold is given by this, right, and the transformation, okay. So now the question is, if you want to connect it to 4D gravity, whether they are capturing space of this 4D gravity, right? So the concluding remarks are that because this we showed that this celestial CFT consists of this Liouville sector in this long string CFT, and therefore it suggests that this Liouville sector could be a universal feature for all of all celestial CFTs. Because earlier in the introduction, I told you that some examples of celestial CFTs have Liouville sector. Okay, so if we want a string theory with target space conformal invariance, we would require a twistor string theory, and if we take the near boundary limit, we would probably get a celestial CFT with Poincare invariance. And understanding additional symmetries of CFT2 from the intrinsic perspective, that is something we want to see. And also, we want a possible limit of CFT2 with SO2, 3 to obtain celestial CFT with ISO 1, 3 directly. So I don't want to go to this ADS CFT business. I can just have, if I have a CFT with SO2, 3, I just want to get a limit where I can just take celestial CFT with ISO 1, 3 invariance. So thank you.
Yeah, just to understand the symmetries a little better. I mean, you took this conformal gravity, but would you have said the same thing if in the bulk you had a conform field theory?
But conformal field theory,
because you would have those symmetries, right?
Yeah, but field, but then you can define a sort of a dictionary, right? Like the dictionary that you define for in ADS3, if you have a scalar field, you define a dictionary. You can define the same dictionary, but how does, like holography doesn't make sense for scalar field theories, right? Because there is no gravity theory in the bulk. So symmetries, yeah, you would have SO 1, 4. In that case, what will happen is that you would get a descendants, family of descendants. So if you have a one conformal dimension, so in the near boundary limit, it's not still clear to me how to make sense
without
of it.
Going to this complicated limit, just before even that limit, to understand the symmetries. So if you have a conform field theory in the bulk, now you have a conform field theory with a boundary, but it's not like this system preserves the entire symmetry. Having a boundary breaks this conformal symmetry.
But there is no dual to a conformal field theory in the bulk, right? I mean, I don't understand.
Just the symmetries.
Okay.
Consider a conformal theory in ADS. It's asking, would you claim that it has this inherent symmetry? Yes, sir. That's the question.
It will just have SO2, yeah, it should have SO2, 3. Yes, it will have SO2, 3.
No, but because it has boundary, it actually doesn't, right? It is broken to that subgroup which preserves the boundary.
But if I start with, let's say in 3 dimension, I write it's conformally flat. I write a metric, right? I write for a flat 3-dimensional, I write 2-point function, and then I take a conformally flat metric to this Euclidean ADS3 and write that 2 point, and there will be a conformal factor. Those are SO 1, 4 invariant,
no, but
right?
It has a boundary. It has a boundary, right? Finally, you have a conform field theory on a space with boundary. So now you have to talk about symmetries that are preserved by this particular space. And that preserves only the subgroup of it, namely the conformal subgroup, which preserves the conformal isometries of the boundary, which is one less, which is what you would expect for that two-dimensional CFT.
Right. Okay. So I get your point.
Okay.
But our initial goal was to see the Poincare invariance. So, so in this math, so what you're saying is that in the near boundary limit, what indeed happens is that I get Poincare invariance. So that was like the that was our first primary goal. But okay, for the conformal field theory, I'm not sure. But for conformal gravity, I get SO2, 3. I still have to understand like how can one get this for SO like for I don't know if that's. But for conformal gravity, I have shown that I can get SO2, 3. So if it is true for that, then
I mean, just at the level of symmetries, I didn't think about this conform gravity because it was some other difficult thing to. But the conform field theory, just look at the symmetries. I thought it should work in the same way.
Yeah, but that that is itself is constrained. The additional symmetries won't do anything to that. Right?
State dependency that you get out there and will spoil things, right? And in your next example, the state dependence that you.
But there are symmetries which are state dependent, right? So I mean,
Can we postpone this discussion after the last talk? So let's thank Nishant once again. Okay, so the last speaker of the day is Diwakar. Will tell us about complexity in confining gauge theories. Can you hear me? Can you hear me now? Okay, fine. Okay, so it's already 7. We're late. So it's pleasure to be here, and thanks for the invitation. So I'll try to wrap up as soon as I can. Okay, so this paper is in collaboration with Ali, with the postdoc, and Rashu Nastase and Carlos Nunes. So this is a holographic approach to complexity for confining field theories. So let me explain the plan of talk. So first I will give some introductory remarks. So the complexity we tend to think about it for this model is Krylov complexity, which we call the K complexity. And I will briefly explain different approaches. Just I will quickly mention them. And then what's the goal of our work. And then we'll present a gravity dual for this confining theory, which is this one particular example of this Anabalon-Ross model. And then the third part would be the calculation and results, where I'll talk about this calculation from the gravity side, which is the geodesic motion of the particle, and how to define a proper momentum. And that leads to this holographic complexity. And then there will be some closing remarks where I'll talk about some field theory counterpart, and there's some outline how one can do a field theory calculation for this model, and there are some open questions. So the K complexity we are thinking here is of the K complexity of the operators, which are very recently they are very paid attention because of for various reasons. So it's typically defined for you have an operator at some time t0, and then there's this Liouvillean operator, and then this operator gets spread over time by these cascade commutators. And so there are some papers recently, they show that if you have a confining theory and which is space is compact, then this K complexity is actually suppressed and exhibits an oscillatory behavior. So the plan of this work is to find a gauge gravity setup to find some oscillatory behavior for this Krylov complexity and show that it comes from a gravity calculation. Okay, so there have been two approaches mostly. One is this computing this wormhole length, and this is mostly done in this context of jetty gravity and double scale SYK. There is some reference, as you can see, but mostly what we will be following this proposal by Powell and his collaborators last year eventually. So they find this for this ADS3, and they have a proposal that the rate of growth of this complexity is nothing but this proper momentum along the geodesic of a particle, and we shall follow this second line of approach. So we propose that these calculations can be extended for non-ADS geometries if we can properly define something called the proper distance along the geodesic, and this I will emphasize as we go on. Okay, so the gravity dual that I have in mind is that this is a in a type 2B setup. So it's a supersymmetric soliton, and which has a dual. It's a n equals 4 followed by a twisted compactification. So the 4D theory, so the UV is a conformal theory in 4D, which is the dual to some ADS5, and it flows to a gap 3D quantum field theory preserving 4 supercharges in the infrared. So so the theory is UV is a conformal and is a gapped in the IR. So this background is given by this solution was given by this paper by Annabalan and Ross. So here you can see, so this is the metric, and this is the background gauge field, which is this fiber over 3 U1 cycle, and this is the function f, which actually goes to 0 at the tip of this soliton. So for our calculation, we will set this mu to be 0, which is the supersymmetric case, and so this is the typically this soliton looks like. So this UV is the theory in the UV lives on Minkowski 3 times S1, and this circle shrinks to 0 at the tip of the cigar, and so this case we set mu to be 0 throughout the calculation, and this cycle phi is periodic, so that there is no conical defect at the tip of the cigar, so it's a smooth geometry, and this value is fixed by the supersymmetry. So if you want to preserve the supersymmetry, the periodicity is just given by this 1 over 3q, and this gauge field generates a non-trivial holonomy for the boundary theory, which takes a specific value for the supersymmetric point. So that's the gravity setup for our calculation. Okay, so we take a probe particle actually, and we place the particle in the UV and allow the particle fall under gravity. So the yes, the UV is ADS5 times S1. Yeah. So the particle falls, and this is the simple. Yeah. It's a background gauge field. One of the SO6. Yes, it's required to preserve the SUSI.
So it's one of the SO6.
Yeah. So and then this is the action of the massive particle. So it's a very simple action, and then we have this mass. So sorry, this parameter m of z, which is this quantity, and to begin with this calculation we set phi dot 0 at the beginning, and that's the boundary condition we impose, and that sets L phi to be 0. So L phi is 0, so this angular momentum we don't consider, and we just allow the particle to flow along the radial trajectory. So the Hamiltonian of the system is given by this quantity, and we take this as a boundary condition where it's take the initial velocity to be 0, and this sets the Hamiltonian as 1 over epsilon, where this epsilon is the UV cutoff of the theory. Okay, so what one needs to solve is an integral to know the trajectory of the particle in the bulk. So this integral can be solved actually exactly, and it has an exact analytic solution in terms of cosine elliptic functions. So this is an exact solution, and if you expand this very early time, which you expect something in ADS, a motion in ADS, you get in the UV you get a solution like this. So these are all approximate solution. If you expand close to the tip of the cigar, which is a very late time expansion, then this TE is the time that the particle takes to reach the tip of the cigar. So this 1 over QL is basically the IR cutoff of your theory. Okay, so so this is the time that the particle takes to reach the end of the space, and this you can calculate exactly, which turns out to be, this K is the elliptic integral of first kind, and here is the parameter alpha, which we noticed is a nice parameter, because this alpha is basically, it's a ratio of the scale of two scale H and QL, and these are like the UV and by IR, so it's a scale. So if you keep this scale epsilon, let's fix, and you take this quantity QL goes to 0 for fixed H, this means that you are taking alpha is very large, and that is the point where your cigar actually transits into pure ADS. So you recover your ADS case in this limit. Okay, so so this will result in an ever increasing momentum, and we expect this will correspond to an ever increasing complexity, and complexity will never saturate.
If alpha was finite, the particle will fall and then come back.
Yes, it will reflect, and that's we see in this plot. So if you plot this trajectory, as you lower the value of Q, you see that the particle moves more and more inside the bulk, and for larger values of this Q, there are reflections at precisely these points, and the particle is reflected and going back to UV again. So you expect some sort of so you find some sort of an oscillatory behavior. So this keeps happening. Okay, so now what you have to define, what you identify, that if you want to extend the definition to non-ADS geometry, what you have to define is something called a proper radial distance, and this is defined by this condition that you have to fix. Yeah. Alpha is a parameter that defines the size of the cigar. So it goes. If you take alpha very large, and if you are at alpha equals 1, it means the IR and the UV are very close, and the particle doesn't move. So the shape goes to, so the size goes to 0.
On the field theory, you've got a circle with some holonomy for the.
Yes, that's a circle I compactify.
And how do you see alpha in the field theory data?
Alpha in the field theory data. So, okay. I have to think a little bit. So, so this alpha. So this is a ratio. So this Q is the value of the background gauge field that I have in my field theory. So that's.
Is it the size of the holonomy?
It's a holonomy, yes.
It's the extent of this holonomy is not periodic.
So the holonomy is a particular value for this supersymmetric case. So this holonomy is a periodic over this thing. So I take this. So okay.
But it feels like it's constantly increasing. Shouldn't the holonomy be a periodic function? Shouldn't it be a periodic function?
So holonomy is a fixed value when you preserve the supersymmetry, because you fix Q. You fix Q.
Oh, so it's 2 pi. It's pi or maybe
Yeah.
So then
No. Is the thing is that, so this is the thing. So this R is 1/3Q, and if you calculate this will come out to be some 3/2 or something, some number.
So sorry, you should go on, but I'm just
Yeah.
trying to understand the
Yeah.
Field theory is just n equals for angles.
In the UV.
In the UV, yeah. Field theory is n equals for angles on a circle.
And then you compactify on a circle, and then you go to a from a 3+1 to a 2+1.
Yes, but just the field theory is n equals for angles on a circle with some holonomy for SO6, right?
Yes.
So what other data is there? The circle size makes no difference because of conformal invariant.
Yes, but the
only the holonomy matters, right? And the holonomy is 2 pi periodic or no? I'm getting this.
No, holonomy, I don't think it's periodic.
Well, if,
I have to check. I can't say it right now, but I have to check. But it's so as far as I can remember, it's just a number. Once you fix your Q, it gives you something, some 2/3 or something like that.
What was Q in one last?
Yeah, so Q is the background gauge field in n equals 4 that you put.
That's the holonomy.
That's the holonomy. Okay, so and so we have a proper distance which we call this d rho bar square, and then so we define this new coordinate in terms of the radial coordinate. So this is the definition when you map your old coordinates to the new coordinates. So z and rho bar are related. So if you perform this integration, you find a relation between z and rho bar. And notice that if I take rho bar is very large, then this rho bar very large gives you something e to the power minus rho bar by L, and this behavior this is precisely the prescription that if you want to have a Krylov basis on the dual gravity, so this mapping should exist, which we actually recover in the UV. Okay, so now the thing is that we have to calculate the proper momentum, and that's what we claim is the rate of growth of complexity, and then you can integrate this quantity. If you integrate this quantity, you get is the complexity of the theory. So as you can see, the particle falls in the so it starts from the UV, it goes to the infrared, and then it reflects back. So as it goes, the complexity increases, and then it reflects and it decreases, and so this complexity exhibits some oscillatory behavior. And you can calculate this proper momentum at the very early time and at the very late time. Very early time, if you calculate, you find some linear behavior with time of the proper momentum, and this is the result one expect for the ADS case. And at very late time, you get something finite, and it's and these two behavior are completely different, but these are like some expansion in very close to t equals to t, and this is for very small t. Okay, so so proper momentum is finite in the infrared, and the particle bounces back to the boundary after hitting the end of the space, and once it reaches the boundary, it again falls, and this continues and generates a oscillatory behavior. Okay, so I think I'm almost there. So I'll close with some remarks. So the 3D theory, it in these papers it was explored that the perturbative Lagrangian has this massless gauge fields and a massless gaugino, and the non-perturbative theory, which actually is the theory for us to explore if somebody wants to calculate on the field theory side, it has the glue balls and the glue ballinos. So this spectrum of the theory, for the complete spectrum of the theory, is not known so far. So what we propose is that the full spectrum has to figure out, and what are the this bound states or meson-like states we have in the field theory. And once we identify those states, then we can calculate what is the correlation function between these these 2-point correlators, and then which will lead to something called the return amplitude and the Lanczos coefficient. So this is the outline or the speculation that we think one can carry out with careful investigation. Okay. So I think that's that's all, and I have some open questions that we also list in the paper that we think is worth looking at. So one of these questions is that it would be interesting to understand these Lanczos coefficients from holography. This has not been done yet. How to obtain these Lanczos coefficients from the holography, and the supersymmetry, how it affects the complexity actually. So this in this calculation one can check that if you turn on mu, then you can perform a similar calculation, and it really does not give you something qualitatively very different. So you get almost the same thing. So which I don't put here because it's there in the paper, so you can look, take a look. It would be nice to go beyond the probe approximation, because this we kept in mind that the particle doesn't back react. So this would be nice to go beyond the probe approximation, and then this last point is that we are thinking that if we can instead of particle we took some extended objects like strings, and what if they have some interpretation in terms of the complexity in the dual field theory. So we look forward to things. Yeah, thanks for your attention.
I don't have a question per se, but just a curiosity that suppose instead of this enavolent model, I take this Sakai-Sugimoto model or maybe Gubser model and apply a double Wick rotation, so it becomes a solitron background. And if I instead of particle I take a string, and then the computation will become more complex. I think we will have to use the numerical computations, but can then it extend to the QCD aspect of the?
We have not done the calculation, but
just like a
yeah. So you can think string wrapping this cycle,
because the open string it correlates with the meson pair.
Yeah. It should work out, but so those will be different operators. So this is a different operator. So if you take a string, it will be a different operator, and the complexity will be different.
And computation, I think, will be more complex.
Yeah.
Okay. Thank you.
Just a general question about your background. N equals for Yang-Mills theory is circle compactification of that. If you take it on S3, the supersymmetric circle compactification of that is basically superconformal index. So is this background somehow related to the superconformal index?
I don't know. I don't know.
Thermal circle?
Yeah.
Yeah, it is the same background that has also been used to study the superconformal index in the Cardi limit. It's the same kind of twisted reduction.
So the thing is,
and sorry, and I thought he had, like, instead of S3 he had an R3.
Yeah, in a limit where the S3 goes to infinite radius. Yeah, exactly. Instead of taking the circle small, you take the S3 large.
Okay, thank you.
দেখো